Hey guys, welcome to this session by Intellipaat. So, have you ever shopped for shoes online and got relevant advertisements on Facebook and other websites? And let's say you're chatting with your best friend and the keyboard suggests you the exact words to use in your sentence. And how does YouTube actually suggest your favorite videos on your home screen? Well, all of this is possible because of data science, and that is why today's session is dedicated to data science and how to implement data science concepts with Python. So let's have a quick glance at the agenda. We'll start off by understanding how to do data manipulation with the Pandas data frame, and then we'll look at what is machine learning and look at the different types of machine learning algorithms. And then we'll start with our first machine learning algorithm, which is linear regression. After that, we'll see how to do binary classification with the logistic regression algorithm. Going ahead, we'll work with two classification algorithms, which are decision tree and naive Bayes. And finally, we'll work with an unsupervised learning algorithm, which is k-means.
So let's start with what exactly is Panda? Well, Panda is an open source, simple and powerful Python library, which is mainly used for data manipulation and data analysis. Okay, now you might be wondering, where does this name Panda come from? So what do you think? Is the name of an animal? Is it? Wrong. The name Panda is derived from the word panel data. Okay. Now what is panel data? Well, this is our panel data. It's a multi-dimensional data involving measurements over time. Okay. So it consists of various attributes with different attribute value. Okay. So this is how the name Panda came from the word panel data. Okay. Now the question arises, who created Pandas? Well, Pandas was created by an American software developer and a businessman named Wes McKinney in the year 2015. Okay, so this is the guy who created Pandas. Now let's move ahead and see some of the features of Panda. So on number one we have is series object and data frame. Well, this is the primary and one of the most important features of Panda. It allows it to deal with one-dimensional and two-dimensional label data in the form of series object and data frame. Don't worry, we'll discuss about them in detail later in our session. Okay. Next, on number two we have is handling of missing data. Well, whenever you have a missing data, Panda represents it as NaN. Okay, so this is how Panda easily handles the missing data. Well, no matter where your data is a floating point data or it's a non-floating point data, Panda handles the missing data very easily by representing the missing data as NaN. Okay, next feature is data alignment. Well, this says that the object can be explicitly aligned to a set of labels, or the user can simply ignore the label and let series, data frames, etc. automatically align the data for you in computations. Okay. Next point we have is group by functionality. Well, this is a very powerful and flexible function provided by Pandas. It is used to perform split, apply and combine operations on data for both aggregating and transforming the data. Okay. Next on number 5 we have is slicing, indexing and subsetting. Well, using Pandas, you can perform intelligent label-based slicing, fancy indexing and subsetting large data set. So we'll see in this module how we can perform all these functions using Pandas. Okay. Let's see some more features of Panda. Next we have is merging and joining. Well, using Panda, you can perform both merging and joining operations on your data set. Okay. Next is reshaping. Well, you can easily reshape your data and pivot your data points using Pandas. Okay. Next is hierarchical labeling of axes. Well, this hierarchical labeling of axes allows you to have multiple labels per tick, and this can be done using Pandas. Next is robust input-output tool. Well, Panda is a robust input-output tool for loading data from flat files including CSV and delimited files, from flat files like CSV or Excel files, databases, and saving or loading data from the ultra-fast HDF5 format. Okay. And finally, the last feature that we have is time series specific functionality. Well, this time series specific functionality include date range generation, frequency conversion, moving window statistics, moving window linear regression, date shifting, lagging, etc. So all these types of function can be performed in time series using Panda. Okay, so these were some of the features of Panda. Now let's move ahead and compare Panda with Numpy. So you might be thinking there are so many functions and features that make Pandas and Numpy quite similar. But what exactly is the reason that we are preferring Panda while dealing with some of the data then? Let's discuss that with the help of a comparison between Panda and Numpy. So the first point that we have is Panda works better with Numpy while dealing with data which has more than 500,000 rows. Okay, and when you are using Numpy, so it performs better for 50,000 rows or less. Okay, so in working with large real world data, you would need Panda for computation. Okay. Next we have is Pandas series object is more flexible as you can use it to define your own label index to index and access elements of an array. On the other hand, element and Numpy arrays are accessed by their default integer position, correct? So this is how Panda is different from Numpy. So now that you know how Panda differ from Numpy, next we'll see how we can import pandas in Python. So for that we have a command import pandas as PD. That's it. Okay. Next is what kind of data does suit pandas the most? So we have tabular data, time series data, and arbitrary matrix data. All of these kind of data you can feed it to the pandas. So now that we have learned the history, features, and how to import Panda, let us dive deep and see what kind of data suits pandas the most. So it deals with tabular data with heterogeneously typed columns as an SQL table or Excel spreadsheet. You can also work with ordered and unordered time series data. And it also helps you to work on arbitrary matrix data with rows and column labels. Okay. Let's see what are the different types of data set in pandas. So we have one-dimensional and multi-dimensional data. So you can work on one-dimensional, two-dimensional, or any multi-dimensional data set in pandas. If you are working on a one-dimensional data set, it's known as a series object. If you are working on a two-dimensional, the Panda will create a data frame for it. If you are working on more than two-dimensional data, Panda would create a panel data for it. Okay. Now you might be wondering what are these terminologies, right? So let's have a look at them one by one. So for this session, we'll be mainly focusing on series object. So what exactly is the series object? Well, a series object in Panda is a one-labeled array which is capable of holding any data type like integers, strings, floating point number, Python object, etc. Okay, it can contain data of similar or any mixed data type. You can also say that a series in Panda is quite similar to a list or an array in Python, but yet it's more powerful. It represents a series of both numeric and non-numeric values as a column of data containing any type of mixed data. So you must remember the fact that a series can contain any type of data even if it's of a mixed data type. Okay. Now let's see how we can create a series object in pandas. So here in this example, we have a list of numeric data stored in data. Okay. And now we want to create a series object out of it. So for this, Panda has a function series with capital S. So here we are calling that function using pd.series of data, okay, and storing it in a variable or a series object name series1. If you print it, you'll notice that in the output you have one-dimensional array labeled as 0, 1, 2, and 3. Let's make it more clear using my Jupyter notebook. First topic is series object in pandas. So the very first thing that I'll be doing up here is importing my pandas library. So import pandas as PD. Next, I need to define the list of the data. So let's say data equal 1, 2, 3, and 4. Fine. Now I want to create a series object out of this one-dimensional data. So how will I do that? For that, let's define a series object name. Let's say it's series1. So series1 equal pd.series. Make sure you are using capital S, not small. Series, and inside that pass data. Okay. Now if you print your series1, you will see that you have one-dimensional array of 1, 2, 3, and 4 which are labeled as 0, 1, 2, 3. Okay. So this was about series object in Panda. So let's move ahead. Next is how to check the type. Now what if I want to check if it is a series object or not? So you can do it simply by typing the command type, and inside that pass the name of the object. So here we have passed series1 as the name of the object. Let's check it in our Jupyter notebook, what it has to say. So in order to check the type, all you have to do is mention type, and inside this write the name of the series object, which is here series1. So if you execute it, you'll get the output as pandas.core.series.series. So definitely it's a series object. Okay. Now coming back to our PPT. Next topic is how to change the index name. Now what if I want to change the index name from 0, 1, 2, 3 to ABCD? So how will I do it? So let's see. So for that, all you have to do is add a new parameter index over there and define the index inside it. That's it. Let's see how. So what we are doing up here, changing the index of a series object. Okay. So I don't want to write the entire code. So let's just copy this thing. And all you need to do is specify index parameter over here. So index equal inside this. Let's say first is A, next is B, next is C, and the last one D. Okay. And now if you execute series 1, you'll see that the index name is changed. So here we had index name as 0, 1, 2, 3, which here changed to A, B, C, D, or customize index name. Okay. So I hope this thing is clear to you. Well, next is create different series object data type. Well, Pandas is not just about the list. You can use different arrays, you can use dictionary over there, or you can use any scalar or any constant value to create a series object out of it. Okay. I hope the concept of series object is clear to you. Well, as I told you earlier, in Pandas, two-dimensional data is found in the form of data frames. So now the question arises, what exactly is a data frame? Well, a data frame is a two-dimensional label data with columns which can contain data of different types. Correct? Let me show you an example. So here in this example, you can see we have a two-dimensional data with the column label on the x-axis and the index on the y-axis. Correct? So this is an example of a data frame. So now that you know what exactly is a data frame, let's move ahead and see what are the different features of a data frame. So a data frame contains column of different type. We can even change the size of a data frame as it is mutable. You can even have data axis labeled, and you can also perform various arithmetic operations on rows and columns. So these are the various features of a data frame. So now that you know what exactly is a data frame, let's see how to create one. So you can create a data frame using this command, pd.dataframe, and inside that mention the data. Okay. Let me just open my Jupyter notebook and show you how exactly it is created. So this is my Jupyter notebook, and this is where we left in our previous session. So today we'll learn how to create a data frame. Okay. Let me just change it to Markdown. So again, in order to create a data frame, the very first thing that you will be doing is importing the Panda library. So import pandas. Let's say I want to import pandas as PD. I don't want to use the name pandas again and again. Okay. So now that I have imported my library, let me just define some data. So let's say data equal 1, 2, 3, 4, 5. Okay. And now I want to create a data frame. So let's say df equal pd dot data frame, and inside that what I need to pass is the data. In this, make sure that your D and F is capitalized. Okay, and let's print the data frame. Let's see what is the output. Okay, so here we got the output of data frame. So as you can see, on our x-axis we got the label as 0, and on the y-axis we got the index as 0, 1, 2, 3 and 4. Okay, so there's a simple example of a data frame. So this data frame was created using list. So let me just add this, creating a data frame using a list. Okay, so next what I'll do, I'll show you an example of creating a data frame using a dictionary. Okay, so let's define our dictionary. So let's say my dictionary equals, inside this I'll write fruits, and my fruits consist of array of different fruits like apples, banana and mango. So let's add one more key value to it. So let's say I'm adding count. So count equal, I have 10 apples, 20 bananas and let's say 15 mangoes. So here I have defined my dictionary. Now I need to create a data frame out of it. So let's say data frame equal panda pd dot data frame DNF capital, and inside this I'll pass my dictionary, and let's print it out. So as you can see here, we got a data frame with the labels as fruits and count, and the index over here as 0, 1 and 2. Okay, so this is how we create a data frame using a dictionary. So now that you know how to create a data frame using a list and a dictionary, Now let me show you how you can create a series. Well, the series is the same which we learned in our previous session. It's a one-dimensional labeled array which is capable of holding data of any type. You can have any integer, string, float, or any kind of value in it. Okay, let me show you how you can do it. So here what we are doing, so here we are creating a data frame using a series. Okay, so let's define our series. Let's say series equal pd.series. Inside this, let's say I have 6, 12, and also let me specify the index. So let's say index equal a, b. So there's my one-dimensional array with its defined index. Okay, now I want to create a data frame out of a series. So how will I do it? So let's see. So df equal pd.dataframe with dnf capital, and inside this I'll pass the series. Okay, now let's just print it. So as you can see here, we got this output. So here our one-dimensional series got converted to two-dimensional data frame with index as a and b. Okay, so now that you know how to create a data frame using a series, next we'll see how we can create a data frame out of a Numpy array. Okay, so let's see how. So here, creating data frame using a Numpy array. Okay, so here the very first thing that I'll do is import my Numpy library. So import Numpy as np. Since I have already imported pandas up there, so I don't need to import it again. So after importing the libraries, next what I'll do, I'll define my Numpy array. So let's say my Numpy array equals np.array, and inside this let's have some salary value like 50,000, 60,000. Let's say these are the salary of employee whose names are, let's say, John and James. Okay, so now that I have defined my Numpy array, let me just create a data frame out of it. So data frame df equal pd.dataframe. So let's add a name of the employees over here. So name, and this will fetch data from Numpy array with cell, first cell. Okay, and next let's define salary. So salary will fetch data from Numpy array 0th index, right? So my data frame is created. Now let's just print it, execute it. Data type not understood. Okay, so I've missed this opening and closing square bracket over here. That's why I'm getting this error. Let's execute it. Okay, let's resolve. So here you have just created a data frame out of a Numpy array with column name as name, salary, and here's the index numbers 0 and 1. Okay, so moving on ahead, our session will be on merge, join, and concatenate operations that can be done on the data frame. You will see how you can perform merge operation on two different data frames using pandas, how you can perform join operation between them, and how you can perform concatenation between them. Okay, so without delaying any further, let me just switch back to my Jupyter notebook and let me show you how you can perform these operations. So here's my Jupyter notebook, the way we left it in our last session. So today what we are going to do, today we are going to see how to perform a merge operation between two data frame. Okay, so for this, the very first thing that I need to do is create my data frames. So first of all, let's import the libraries. So import pandas as pd. I'll be needing this library only. And now let me just define two data frames. Now once I've imported the library, so next thing I'll do is define few lists over here. So let's say player equal player 1, player 2, and player 3. Okay, next let's define a list of points. So point equal, let's say 8, 9, 6. Okay, let's also add a list of title to it. So title equal game 1, game 2, and game 3. So now that I have defined three lists over here, I need to create a data frame out of it. So let's say my first data frame equal pd.dataframe And inside this, let's create a dictionary. Let's add a label, let's say player, and this player contains all the values from my list of player. Okay, comma points, and this points consist of all the values from the point list, and the title which consists of all the values from the title list. So I have created my data frame over here. So let's just print it. So this is my data frame which I just created. So one of the data frame is ready. Now let's define another data frame. For this we'll be needing different list. So let's say here player equal player 1, player 5 and player 6. Let's define another list as par. So par equal punch, kick and elbow. Fine. Next I'll define a list of title. So here title equal player is from the game 1. Next is this one from the, let's say, game 5, and this one from game 6. Okay, here all our lists are ready. Now let's create a data frame for it. So here df2, that is second data frame, equal pd dot data frame. So inside this, let's define our dictionary. Say column name is player, which consists of the values from player list. Next is par. So my next column is which consists of the values from par list. And the next is title, again which consists of the values from title list. So there's my second data frame. Let me just print it. So here my second data frame is also ready. So this one is my first data frame and this one is my second data frame. So now that our data frame is ready, so the very first thing I'll be performing on it is inner merge. So what exactly is this inner merge? Well, the result of this inner merge would be that it will return you the row which is common in both the data frame on the basis of any key value. So let's have a look at our data frames. Any common value over here, like any common column you can say. So we have player and title in both our data frame, right? So we can perform the inner merge using any of these two columns, either player or title. Let me show you how. So let's say I want to merge my data frame 1 with data frame 2. So I'll write data frame 1 dot merge with what? Data frame 2. Okay. And on the base of what? You have to specify your key value over here. So on, let's say I want on the base of title. Okay. And how I want to merge them? So how equals inner. So this will give you the inner join. So we got this result over here. So here player underscore x represents that this attribute is from data frame 1 and player underscore y represents that this attribute is from the data frame 2. Okay. So why did we got just one value over here? Let's explore it. So on the base of title, so we are merging on the base of title. So what are the common values in it? As inner merge give you the common set of values in both the data frame on the base of what attribute you are choosing. So as we have chosen title over here, so common attribute is game 1. So only game 1 is common, right? So whatever values are associated with game 1, you got that. Okay. If I change the value of title to player, let's see what's the difference. So here I got the value of player 1 as player 1 was only common in both the data frame, right? So here player did not get split into player underscore x or player underscore y. So instead of that, title got splitted up to title underscore x and title underscore y. Okay. So here title underscore x is game 1 and title underscore y is also game 1. So this is how we perform an inner join on two data frames. So just to tell you, by default, if you merge two data frame, it will perform an inner join. Okay, see. So this was all about inner merge. Now let's move ahead and see how you can perform left merge. So even performing left merge is quite similar to the one which you performed in inner merge. Just have to write data frame 1 dot merge data frame 2 on player, and instead of this inner you have to mention left. That's it. So in case of left merge, both of the table would be merged together, but in this case all the values from table 1 would be there. So our table 1 has, or the data frame 1 had player 1, player 2 and player 3, right? So all these values are over here, And apart from it, what else you will get? You will get all the values from second data frame. And here you will get all the common values from your second data frame. So here my player 1 was in both the data frame, right? So it merged both the table and it showed me these values over here, punch and game 1. Right? But for player 2 and player 3, they were not in the second data frame, right? So that's why Panda was not able to identify what value should it give in power and title. So that is why it mentioned NaN over here. Okay, so this is how you perform a left merge. Now next, let's see how to do a right merge. So again, you don't have to do anything, just change left to right. So left becomes right. So you got this value. So why I'm getting this value? So similar to left merge, now it's performing right merge. So all the values from your right table would be here. Okay. So player 1, 5, 6. I'm getting all the values from my right table or right data frame or second data frame, right? So 1, 5, 6 are over here. 1, 5, 6, punch, kick, elbow, and game 1, game 5, and game 6. And apart from it, what are the common values from the left data frame, right? So from our first data frame, we got this value as player 1 was common in both of them, correct? And apart from it, we didn't had any value for player 5 or player 6. That is why we got NaN, 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 and NaN values over here. So this was about the right merge. Now next is how to perform an outer merge. Let's see. Outer merge. So here all you have to do is change this to outer, execute it. So in this case you will get all the values, and wherever the value is not common you will get NaN over there. Okay, so this was about the outer merge. So guys, this was all about the merge. Now next, let's move ahead and learn about the join operation using Panda. There's a slight difference between the merge and join in case of Panda. Let me tell you what. In case of merge, the two data frames were getting merged on the base of their attribute name or the column name, right? So it's a must that both the data frame must contain at least one common attribute name, right? But this is not the case in join. It's a bit different. In case of join, the two data frames are joined on the basis of their index value. Join is generally used when two tables have completely different attributes. And this is the reason why you have to specify the set index while performing join. Okay, so here you can say that it's must to have a common index between the data frames. Okay, so let's move ahead and let me just show you how you can perform join operation. So here, how to perform join operation in Pandas. So similarly, the very first thing that we need to do is define our data frame. So let's just copy the one which we already created. So here I need to make some changes in it. What change? Here I have to add index value for it. So let's say index equal L1, L2 and L3, as this is my left data frame. Okay, and let's define our fourth data frame, and in this let's change the name of the attribute. So here let's make players and titles, and also let's change the index number. So let's say we have L2, L3 and L4. Okay, so our data frames are ready. Here I'll be performing the join function. So first let's perform inner join on it. Well, the concept of inner join and inner merge, everything is same. Okay, just the difference is how it is used. In case of join, the two data frames are joined on the base of their index name. In case of merge, two data frames are merged on the base of their attribute name. It's the only difference. Okay, and it's same with inner join, left join, right join, outer join, everything. Now let's see how to perform an inner join. So I want to join my data frame 3 with data frame 4. Okay, we have to change it. Let's name it 4. So I need to join data frame 3 with data frame 4. So df3.join inside this data frame 4. And how I want to join? So how equal, I want to perform inner join between them. That's it. Execute it. Okay, we are getting error of columns overlap. Okay, I guess we missed one value over here. Okay, now both our tables are also different. Okay, now let's perform inner join on it. So while performing inner join, you can see that it has joined both the tables on the base of their common index name, right? So L2 and L3 are common part over here. So that's why we got these values. So this player is from the left data frame and this player is from the right data frame. Fine. So this was about the inner join. Now let's change it to left join. So left join, let's copy it and just change inner to left. That's it. So here you can see that we are getting some null values over here. So why we are getting null values over here? So it's the same reason what happened in case of merge. So in case of left join, it is merging both the data frame with all the datas from the left data frame and all the common datas from the right data frame, right? And wherever the data in right data frame does not matches that to the left one, so there we are getting a null value. Okay. Similarly, right join, have right. In this we are getting all the values from our right data frame and all the common values from the left data frame. Fine. Next is outer join. Just write outer over here. So what it did, it just merged both the data frames. Wherever it was not able to find the common values, it assigned null values to it. Okay. So this was all about join. Now next we'll see how to perform concatenation using pandas. So here we'll write how to concatenate two data frames in Panda. So we already have defined data frame 3 and data frame 4, right? 3 and 4. So let's just concatenate them. So for concatenating data frame 3 with data frame 4, all we need to do is pd.concat and inside it mention what all data frame you want to concatenate. So here data frame 3 with data frame 4. That's it. Execute it. So you got this value over here. Okay. So it is basically concatenating both the data frames. Okay. So in this session, you'll learn about how to import a dataset using pandas and how to analyze various attributes of the data. So without delaying any further, let's start and see how we can import a dataset using pandas. So for importing the dataset, the very first thing that you'll be doing is importing the pandas library. So I'm importing pandas as PD. So next we are going to read the dataset and store it in a data frame. So I'm defining a data frame named cars, and inside this I'm passing the path of my CSV file, which is emptycars2.csv. At this point you can specify the path to your CSV file. Okay. And finally we are printing it. Let's see the output. So this is my entire data. So let's move ahead and see what are the various analysis we are going to perform on it. So first is type cars. So this type car is used to check the type or check the data type of the car. So it's a data frame, right? So as a part of output, we got pandas.co.frame.dataframe. Okay. So the type of cars is, it's a data frame. Next is cars.head. Well, this is used to view only the first 5 records of your data frame, which in our case is this. Okay. Next is if you want to view first 10 records from your dataset, you can pass the attribute over here as 10. And so as an output, you'll get first 10 dataset from the data frame. Okay. Next is what if you want to view last 5 records, then you can use the parameter dataframe.tail, which in our case is cars.tail. Okay. So this will give you the last 5 record of your data frame. Okay. Similarly, if you want last 10 records from your dataset, you can specify a value over here. So dataframe.tail, inside this I pass 10. So this is giving me last 10 records from my dataset of cars. Okay. Next is cars.shape. Now if you want to view the total number of rows and columns in your data frame, for that you have dataframe.shape. So cars.shape gave me the output as 32 and 13, which means I have 32 rows and 13 columns in our dataset. Now if I want to concise the summary of the column of my data frame, for that I have dataframe.info. And inside info, I'm passing null underscore counts equal true. So what it is exactly giving me, it is giving how many non-null values are up here. So as you can see in QSEC, we have 29 null values. So from here you can say that we have 3 null values in our column QSEC. Okay. This is the data type of each column. The first serial number is of integer data type, next is object, mpg is object, cylinder is integer, and so on. So in total, we have 4 columns which consist of floating data type, 7 columns which consist of integer data, and 2 columns which consist of data of object data type. Okay, and the total memory usage is 3.3 plus KB. Fine, let's move ahead. Now if I want to calculate the mean of my data frame, I can just write DataFrame.mean, which in our case is cars.mean. So as a part of output, it gave me the mean of each column. Okay. Next, if I want to calculate the median, similarly DataFrame.median, cars.median, it gave me the median of each individual column. Okay. Next is standard deviation. Well, for standard deviation, we have DataFrame.std. So if you see the output over here, you are getting the standard deviation of each column. Fine. Next, similarly, you can calculate the maximum value of each attribute by using DataFrame.max. So we have cars.max, for which we are getting maximum of each attribute. So in serial number, we have 35 unnamed maximum value. This MPG, it's 33.9 and so on. Okay. Similarly, you can calculate the minimum value for each attributes using DataFrame.min, and you'll get minimum value for all these different attributes. Fine. Next is DataFrame.count. So if you want to count the total number of non-null record in each column, then you can use DataFrame.count. So which in our case is cars.count. So here as output, we are getting how many non-null values are in each column. So here in QSEC, you can see that we have 29, which suggests that we have only 29 non-null records and there are 3 null values in it. Okay. Next is the DataFrame.describe function. Well, it is used to print the descriptive statistic summary. If you don't want to calculate each of the feature individually, you can just write DataFrame.describe, and this will give you the output of count, mean, standard deviation, minimum, maximum, 25 percentile, 50 percentile, and 75 percentile values of all the different columns. Okay. So these were the various attributes you can use it for analyzing your data set. Okay. So without delaying any further, let's see what exactly is data cleaning. So data cleaning or data cleansing is a process of detecting, correcting, or removing corrupt or inaccurate records from a dataset, table, or any database. It also refers to identifying complete, incorrect, inaccurate, or irrelevant parts of our data and then replacing it or modifying it. This is what a data cleaning is. So let's see how we can clean our data. So the first thing that we can do to clean our data is we can rename the column. Okay. So in our dataset, we had a column as unnamed. Right. So instead of using the column name as unnamed, we can replace it by name of the model, which represents the exact name of the column, as the column contained different model of the car. Right. So here what we are doing, we are renaming the column unnamed to model. So as you can see here, as an output, we got model up here. Okay. So this is the very first thing that you can do while cleaning your data. You can rename the attributes. Next is, what if you have some null values in your data? So for treating null values, what you can do, you can fill the null values with the mean of the column. And this is how we do it. So cards.qsec. So as we have analyzed in our previous session that qsec had 29 non-null records, right? So which it meant that it had 3 null values in it. So we replaced all those null values with the mean of the qsec column. So what we did, we took the mean of the entire 29 and whatever value we got for the mean, we replaced all the null values with that particular value. Okay. So replacing the missing data with the mean value will help analyzing the data in a better way. Okay. So this is how we can replace the null values with the mean of the column. Next is drop the unwanted column. So here we can drop all those unwanted columns which do not add any value in analyzing the data. For example, we had serial number previously, right? But the serial number was not adding any value to our analysis part. So for the further processing of the data, we can avoid or we can drop the column of serial number. Okay. So how we can drop any column? So for dropping any column, what we have to do is DataFrame.drop, and inside that we have to mention the name of our column, just like this. Cars equal cars.drop, and inside this columns equal, we are mentioning the name of the column as serial number, and it got dropped. So as you can see here in the output, we don't have the column as we used to have it previously. So here a serial number column is dropped. Well, next is finding correlation matrix. Well, this correlation matrix will help you to find how a variable is correlated to other variable. So if the value of correlation is high, so that means the two variables are highly correlated to each other. That is, changing one variable by a factor of x changes other variable by a factor of y. Okay. So here as an output, we got a correlation matrix, right? So from here you can see that cylinder to cylinder, it's highly correlated. That is one, obviously. Cylinder to displacement, it is 0.9. So it means that cylinder equals 0.9 times of displacement. So it's like if you increase cylinder by 1 unit, your displacement would increase by 0.9 unit. Okay. So similarly for DRAT, you can see that cylinder equal minus of 0.69 times of DRAT, which means if cylinder increases by 1 unit, it means the value of DRAT would decrease by 0.69 units. Okay. So if while finding a correlation matrix, you get a very small value of the correlation. For example, let's consider this. So here correlation between carburetor and DRAT is minus of 0.09. So it means they are very weakly related to each other. So it's like if the carburetor is increased by 1 unit, so it means that if the carburetor is increased by 1 unit, then DRAT would decrease by 0.9 unit, which is almost very less, right? So by finding correlation matrix, you can define the correlation between the variable, and from here you can decide which attribute to choose and what not to choose while working on the problem. Okay, fine. Let's move ahead. Next is changing the data type. Well, initially MPG was of data type string, right? Well, MPG had some float or numerical values into it, right? But with the string, we cannot manipulate it, or we cannot perform any calculation on the string data, right? So MPG has to be converted to float in order to perform some data manipulation on it. So here we are converting MPG from string to float. So how we can do that? So it's DataFrame.mpg equal DataFrame.mpg as type, and inside that we are mentioning the data type which we want to convert to, and here in this case is float. Well, now if you want to see the change, you have to see cast.info null underscore counts equal true. So from here you can see that my MPG has been changed to floating data type, right? And even for the QSEC attribute, we have replaced all the null values from its mean, right? So here it's giving me 32 null values. That is, now it is not having any null values in it. Okay, let's move ahead. So again we are finding the correlation. This time the MPG part is included as it has become of a floating type. Remember, while calculating the correlation between two attributes, both the attributes should be numerical in nature. No correlation can be found between attributes of string data type. Okay, if you compare it with our previous correlation, you can see that there was no MPG value, right? As initially the data type of MPG was string, right? Now since we have changed the data type of MPG to float over here, so next while finding the correlation, we are getting MPG value. Okay, now Python is treating it as a numerical attribute and it is using it to find the correlation. Okay, so this was all about how you can clean your dataset. Okay, so in this session you will learn about how to perform indexing on the dataset, how to set a value for a column, how to manipulate the data using lambda function, how to sort a column, and finally you will see how to filter your records. So without delaying any further, let's start with our first topic, manipulating dataset indexing by position. Well, what if you want to view a single column? So how will you do that? Well, Panda gives you a functionality of iLog function in which you can specify the parameters to view a single column. So for example, I want to view HP column only. So my HP column belongs to 4th row, right? So I mentioned the iLog colon, which means row. So entire row, comma, 4th column. Okay. So what it will give me? The 4th column of the dataset, which is nothing but the HP column. Okay. Let's move ahead. Next is, what if I want to view first 5 record of the HP column? So in it, I'll mention this is the number of row. So iLog row starting from 0 till 5. Okay, actually 0 till 4, just before 5, and the column 4th. So it will give me the first 5 result from the column HP. Okay, next is, what if I want to view all the rows and all the columns? So all you have to do is iLog colon comma colon. Okay, first colon means all the rows, second column means all the column. So it will give you the entire data set. Next is, let's see I want to see all the column from HP to cow and see all the record from index number 6. So how will I do that? So for that I have row start from 6 till the end. and column start from 4th till the end. So 4th column till the end and row from 6th column till the end. Okay, let's move ahead. So now we want to look at all the rows from the first column. So again, so here inside iLog I have mentioned colon. So this represents the row. So we need all the rows. So for representing all the rows we have colon. Okay, and the next parameter is the column number. So our column number is 1. So as you can see in the output, we got all the rows from our first column. Okay, let's move ahead. Well, you can even view your record on the base of the name of the attribute. Okay, so for example, I want to see all the record of MPG column. So how will I do that? So instead of iLog, first of all, I'll be using lock over here. That is location. Okay, then inside that the row and the column. So colon includes all the rows and the column is MPG. So what it will give? It will give me all the rows from the MPG column. Okay. Next is display the record from index number 0 to index 6 from MPG column. So similarly, so lock starting from 0 until 6 and from which column? In MPG column. So it gave me records from index number 0 to index number 6 from MPG column. Okay. Next is to see first 7 record from MPG to QSEC column. So here what I'll do, so inside location what I have mentioned, the row. So starting from 0 till 6. So how many records are over there? It's like 0, 1, 2, 3, 4, 5 and 6. So in total there are 7 records. And from which column? So a column should start from MPG and it should end till QSEC. So from MPG to QSEC, I need 7 rows over here. Fine. So this was all about how you can play with index values while manipulating your dataset. Okay. Next is setting the value. Well, if you want to set a specific value to the entire column, so you can do that easily using Panda. So here cars is our data frame. So what we are mentioning, cars of AM. So AM is what? It's a column name. Okay. So data frame of AM equal 1. So what it will do, so it will assign value 1 to the entire column of AM. So even in the output, you can see that AM has all the values of 1. Okay, let's move ahead. Next is applying function. Well, now what if I want to double my record? Well, for that I can use lambda function over here such that x is x multiplied by 2. So whatever value would be there, it will just double it up. So cars of AM equal cars of AM dot apply f. Okay, f is our function, this. So as you can see in the output, we got all the double records in AM. Okay. Next is sorting the data. So what if I want to sort a column in ascending order? So for that I have dataframe.sort_values and inside this I'll mention the name of the column. Okay. So for example here my data frame is cars and the name of my column is cylinder. So I'm mentioning cars.sort_values by cylinder. So as you can see here, my cylinder column has been sorted in ascending order. Okay. Next is descending order. Well, all you have to do is add one more parameter over here, that is ascending equal false. And as you can see here, my column has been sorted in descending order. Okay. Next comes filtering the data. Well, what if I want to view the record which are having more than 6 cylinder? So how will I do that? So for that I have cars of cylinder is greater than 6. So wherever the value of cylinder is greater than 6, so we are getting a true value over there, and apart from that all are false. Okay. Now what if I want to filter my records and see only the data or only the model which are having more than 6 cylinders? So how will I do that? So for that I'm storing the value into filter 1. And next I'll apply a filter to my entire data frame. So filtered new equal cars of filter 1. So what it will give me? It will give me all the true parameters from my data frame or from my filtered cars of cylinder greater than 6. Okay. So when you view the output of filtered new, you can see that we got all the values in which the value of cylinder is greater than 6. Okay. Next, what if I want to filter my record and check for the model which are having 6 cylinder and horsepower more than 300. So for that we added this condition over here. That's it. That is cars of cylinder is greater than 6 and cars of HP, that is horsepower, is greater than 300. So we are using AND operator over here. Okay. So this will give me a true result only if both the parameters are true. And again, same, we are filtering the data frame and displaying the filtered data. So as you can see here, we have only one model, Maserati Bora, which is having a horsepower of 35, which is greater than 300, and number of cylinders as 8, which is again greater than 6. So both our conditions are true. So there's a filtered data over here. So our today's session is on Introduction to Machine Learning. In today's session, you will learn about how you are surrounded with machine learning, what exactly is machine learning, and what are the various myths related to machine learning. So without delaying any further, let's move ahead and see how you are exactly surrounded by machine learning. The first one we have is product recommendation. So have you ever shopped online on Amazon? So while browsing through the product, did you notice that it recommends you a certain list of products which are quite similar to your interest? So how do you think Amazon is doing this? Well, it is one of the applications of machine learning used in Amazon. Amazon is using the technique of machine learning to build a recommendation engine which recommends product to you. Okay, let's move on ahead. Next is Amazon Alexa. So how do you think whenever you command Alexa, it performs a particular function? Like, hey Alexa, play a music. So it plays your favorite music for you. Or hey Alexa, turn the light on. So it turns the light on. So how do you think these actions are performed? Well, this is again one of the application of machine learning. Or movie recommendation by Netflix. Again, one of the application of machine learning. Or Google traffic prediction. So how do you think when you're using Google Map to navigate from a place X to Y, then it suggests you route and it predicts the traffic on that particular route. Like from point A to point B, it will be huge traffic and that is mentioned in red, and after that there would be no traffic. So the pathway is shown in blue. So how do you think this traffic prediction is done? Well, it's also an application of machine learning, and these are the use cases which you are using in your daily life. Right, so these are the use cases of machine learning which you are using in your daily life. So now let's just move ahead and start with Introduction to Machine Learning. So what exactly is machine learning? Well, machine learning is not just about the robots, right? Machine learning is a sub-branch of artificial intelligence which focuses mainly on machine learning from their experience. It is a subset of artificial intelligence which gives the machine the ability to learn without being explicitly programmed. Here, the data is the key and the learning algorithm. The data is the most important part of the machine learning algorithms. The machine trains itself according to the data provided to it. Let me explain you this with an analogy. Consider a newly born human child who starts learning in his primary and kindergarten. The child initially knows nothing, so the teacher starts with the alphabet. The teacher shows the picture of A to the child and tells him it's A. The teacher repeats the process again and again till the student learns all the alphabet. So this was teacher teaching the student. Now once the training is complete, teacher conducts a test to verify how accurately his student has learned. If the test score was not good, means that student has not learned. So more training is required in that case. Now compare this human child with a newly born machine. The machine doesn't know anything, right? So you start training them in a similar way the teacher taught to the child. Initially, the machine has no idea about what is A or what is B. So you start by showing your machine various pictures of A and telling that it's A. Now once the training is complete, you can test your machine by showing it different images of A of different fonts and style. If the machine is able to predict the image A with higher accuracy, then in that case you can say that your machine or the model is trained. Alright? So this is what exactly is machine learning. So now the question arises, how does the machine learn? So when you have the data set, you start by dividing your data set into two parts, the train and the test part. First 80% of the data is the training data, and rest 20% we use it as a test data to test our model. So you train the machine with 80% of your data and create a machine learning model. Now once the model is created, we bring in our test data and test our machine with it. If the accuracy is not good enough, then we repeat the process again and again till we get a final trained and tested model. Okay, this is how a machine learns. Fine. So this slide says that machine works with more data. So it's like more data you provide to the machine, more accurate it will get. For example, here on the screen you have some images of Chihuahua and Muffin. Okay, so you can see that they are quite very similar in their appearance, right? A human can easily tell that yeah, it's a dog or it's a muffin. But when it comes to the case of machine, it is really very difficult to tell which one of them is dog and which one of them is a muffin. So the more data you provide, the more accurate your machine get, and more easily it will be able to identify between dog and the muffin. Okay. Next, So I'm assuming that almost all of you must have come across this verification step from Google, right? Where it asks you to select all the images, for example, here of a fire hydrant. So what you do, you just click on the picture of fire hydrant to verify that it's not a machine, it's you. But who knows, we are actually training a machine and telling the machine that these are the images of a fire hydrant, right? It might be possible that we are training a machine for something very big. Okay, let's move ahead. The machine learning popular myth. So let's bust out some of the popular machine learning myth. So the first myth that we have is most of the people consider that all the AI, machine learning, deep learning, all these are same. But just to tell you, there's a significant difference between them. So just to tell you, AI is a broader umbrella under which machine learning and deep learning comes. And deep learning is a subset of machine learning. Okay, so let's see them one by one. Starting with artificial intelligence. Well, artificial intelligence is an area of computer science that emphasizes the creation of intelligent machines that works and react like human. Well, it's a broader field, or you can say that the theoretical concept of machine learning and deep learning comes under AI. So the presentation part is AI and the actual implementation part is either machine learning or deep learning. Okay, next comes machine learning. Well, machine learning is a subset of AI which gives the machine the ability to learn without being explicitly programmed. Okay. Next is deep learning. Well, it's a subfield or subset of machine learning which is concerned with algorithm inspired by the structure and function of the brain called artificial neural networks. Fine. So get this thing clear that AI, machine learning and deep learning are not at all the same. Okay. So I hope now you know what exactly is AI, machine learning and deep learning. Okay, let's bust out another myth. So next myth that we have is robots will take up our job. So most of us think that robots is gonna take up our job. Let me give you a scenario. Every one of you know about Uber, right? Uber is using machine learning algorithm to simplify your life. So what do you think? Uber has taken up the job? No, right? So instead it has generated so many n number of jobs for the people out there. So many needy people are hired every day as Uber driver. So here my point is, machine learning or the robots might take up your current tedious job, but instead it will open up with thousands of opportunity for you and will definitely make your life more easier. Okay, so robots are not going to take up our job, but instead they are going to generate more jobs for us. Okay. So in today's session, we'll learn what exactly is supervised learning, one of the type of machine learning, what are the real life use cases of supervised learning, what is unsupervised learning, what are the various real life use cases of unsupervised learning, what is reinforcement learning, and finally what are some of the real life use cases of reinforcement learning. So without delaying any further, let's start with types of machine learning. So in general, we have three types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Let's see them one by one. So starting with supervised learning. So supervised learning is the one in which we have a training data set, or you can say in which we have a labeled training data set and the machine is trained on that particular label. For example, so there's a teacher or there's a supervisor who supervises the entire process and trains the machine according to the label. For example, you can see up here, here's a teacher on the screen who is teaching the machine by showing different images of the apple. So once the machine is trained, so in future, when we show a different image of an apple, the machine can easily identify that it's an apple with some accuracy. Okay, for example, the image shown up here is an apple with 97% accuracy. So this is supervised learning. So let's see some of the use cases of supervised learning. So first we have a spam classifier. So how do you think your mail is getting classified as whether it's a spam mail or not a spam mail? Well, the spam detection basically works on the basis of filter. These are settings that are constantly updated based on new technologies, new spam identification, and the feedback given by Gmail user about potential spammers. Spam filter uses either text filter or it eliminates the thread based on sender and their history, whether the sender was previously reported or not. Okay, so there are mainly two types of filters: text filters and client filter. Text filter work by using algorithm to detect which word and phrases are most often used in the spam email. Phrases like lottery or you won or free Bitcoin are often an immediate flag for removal by filters. Spammers have gotten wise to this and often use blunt misspellings or even substitute of characters like free dollar character in order to make it pass the filter. Fortunately, the modern spam filter can also make allowances for these type of misspellings, and if a word comes up, even with character substitution, the message will still be blocked. Next is the client filter. In addition to the simple text filter algorithm, the top spam filter uses client identity and history to block malicious or annoying spam email. Now, how does a spam filter work? Well, this is done by looking at all the messages of a certain user which he has sent out. If they send out huge amounts of email constantly, or if several of their messages have already been marked as spam through the text filter, in that case their email will be blocked entirely. So this brings us to the use of blacklist. Spam filters also include a blacklist. Blacklisting is simply the process of adding the known email addresses of a spammer to a list. This list prevents any inbound messages from the email address going forward. If you have marked something as spam, it will directly go in this blacklist. And it also helps Google to make a note of certain keywords found from that particular spam mail. So that's the outline of spam detection. The real-time process are a lot more complex and consume a lot of data. Okay. Next is fingerprint analysis. So for fingerprint analysis, what you do, you save your fingerprint in the machine as a record. So the machine checks the data and verifies whether this particular data belongs to you or not. Okay. So once the data is saved into the machine, so from next time, whenever you put your fingerprint on the machine, what the machine does is scan through all of its data. And if the data is matched, then in that case, your fingerprint is verified. This is another application of supervised learning. Next we have is unsupervised learning. Well, in case of unsupervised learning, there is no teacher and there is no label. What the machine does, the machine identifies clusters in it. It finds similar images and group them into a cluster. For example, over here, seeing some pattern in different images, the machine divides the entire image into 3 different clusters. Okay, cluster 1, cluster 2, cluster 3. But the machine doesn't know that cluster 1 is an apple, or cluster 2 is an orange, or cluster 3 is a banana. All it knows that cluster 1 consists of similar item, cluster 2 consists of other similar item which are not at all related to cluster 1. And similarly, cluster 3 consists of different items which are completely different from cluster 1 and cluster 2. And cluster 3 consists of other similar items which are completely different from the item of cluster 1 and cluster 2. Okay, so this is what unsupervised machine learning is. So one of the use case of unsupervised learning is voice-based personal assistant. So the device which you are seeing on your screen is Amazon Echo, and the brain or the voice of Echo is known as Amazon Alexa. The device has many smart built-in to do a number of tasks like playback music, make the light blink. It also recognizes the name Alexa. It's like when you say the word, it recognizes the word and start recording your voice. Amazon calls this word as a wake word. So it's like when you have finished speaking, it sends the recording over to the internet to Amazon. The service that processes this recording is called Alexa Voice Services, or AVS. It's run by Amazon, thus converts the recording into commands that it interprets. It's more than a simple voice-to-text service. It is a fully programmable service that can work with other online services to do a large range of things for you. Once authorized by Amazon, anyone can use this service for free to build a homemade Echo. Amazon has also offered sample code for building an Echo using a Raspberry Pi, which is a simple $30 computer. It might sound extremely selfless of Amazon to provide the service for free, but as always, they have their reasons. Amazon want others to build their service into their product so that they can sell you this stuff. So every product that has Alexa built in is a device that can be used to buy stuff from Amazon. These commands that Alexa interprets can be very simple. It's like if you ask for a time, the AVS sends back an audio file to Alexa telling you the time, which the Echo plays back. They can also be more complex. If you ask Alexa to play a Pink Floyd, AVS will search the music service to have you set up for Pink Floyd, and then send a command back to the Echo that sets it playing the requested music. Alexa can also work with other technologies in your home. It's like you can even set up your Philips Hue smart lights to be controlled with Alexa. You can ask Alexa to turn on the living room lights, and the Alexa will send a command to the Echo that sends a command to these light bulbs to turn on. It can also work with various online services. You can link Alexa to Uber, and you can request Uber by simply asking Alexa. You can link it to Domino's, and you can just order a pizza with your voice. So this approach means that Alexa can do a lot of things for you. And the list is just getting longer. Amazon is adding more features and skills to Alexa. And if you are smart enough, you can build up on their own. So it means that you can use Alexa to control things that are not even on the list. Okay, well, however, Alexa needs internet connectivity and AVS to work. If your internet connection is slow or it's not working, then Alexa won't be available and your Echo will be useless. So if Amazon decides to charge for a service or just close it down, then in that case, you'll be just left with a useless device. Well, Amazon is not the only one in town. We have Google, Apple, and Microsoft, which offers similar services that can perform tasks by voice command in the form of OK Google, Siri, and Cortana. They use similar approach, voice commands that are processed in a cloud service. But most of them are not as flexible or as integrated with other services as Alexa is. So whichever of these services end up being the one we all use, hopefully they will be as polite as Alexa. I'll just give you an example. When I asked her how she works, she replied, "Lots of people had worked hard to teach me, and I'm still learning more. Wouldn't it be nice if all of our appliances were that modest and polite?" Right? So let's move ahead. So another use case of unsupervised learning is Netflix recommendation. So more than 80% of the TV shows that you guys watch on Netflix are discovered through the platform's recommendation system. That means the majority of what you decide to watch on Netflix is the result of decisions made by a mysterious black box of an algorithm. Let me just give you a brief of how it works. Well, Netflix uses machine learning algorithm to recommend you the list of movies and find shows that you might not have initially chosen. To do this, what it does, it looks through a thread within the content rather than relying on both genres to make a prediction. So this explains how 1 in 8 people who watch Netflix Marvel shows are completely new to comic book based stuff on Netflix. Let me tell you about a guy named Todd Yellen. He's the Netflix Vice President of Product Innovation. He has explained the working of Netflix as a 3-legged stool. The 3 legs of this stool are Netflix members, the tagger who understands everything about the content, and our machine learning algorithm that takes all of the data and puts them together. So Netflix has more than 100 million worldwide users. If we count the multiple user profile for each subscriber, it comes to around 250 million active profiles. Now Netflix uses different kind of data from these profiles, like it keeps a track of what you guys are watching from your profile, what do you watch after completing your current video, and even what you have watched earlier. It also keeps a track of what you have watched a year ago or what you're currently watching and at what time of the day. Well, this data is the first leg of the metamorphical stool. Now what they do, they combine this information with more data to understand the content of the show that you are watching. The data is generated from dozens of in-house and freelance staff who watch every minute or every show on Netflix and tag it. Now all these tags and the user behavior data are taken and is fed to a very sophisticated machine learning algorithm that figures out what's most important and what should it weigh like. Or how much should it matter if a consumer has watched something yesterday? Should that count twice as much or 10 times as much compared to what they have watched a whole year ago? How about a month ago? Or how about if they watched 10 minutes of the content and abandoned it, or they binged through it in 2 nights? So how do we weigh all that? Well, that's where machine learning comes in. What those 3 things create for us is taste communities around the world. It's about people who watch same kinds of thing that you watch. Viewers are fit into thousands of multiple taste groups, and it's these that affect what recommendation pop up on the top of your screen. The tags that are used for machine learning algorithm are the same across the globe. However, a small subset of tags are used in more outward facing way, feeding directly into the user interface and differing depending on a country language and cultural context, as the tags have to be localized in a way that make more sense. For example, if you know English and you're watching Hollywood movies or movies in English, then in that case, Netflix won't recommend you German movies or Chinese movies or Japanese movie. Alright, the data that Netflix feed into its algorithm can be broken down into 2 types, implicit and explicit. Explicit is, for example, you give a thumbs up to the series The Friends, so the Netflix get it, okay. And implicit data is mostly the behavioral data. It's like you didn't explicitly tell Netflix that you like Black Mirror, but you just binged on it and watched it in 2 nights. So the Netflix understands that behaviorally. So the majority of the data is implicit. So this was about how Netflix is using machine learning to recommend you the movies. Fine. So next we have is the reinforcement learning. Well, in reinforcement learning, what we have is the agent and the environment. The agent selects some action using some policies. So there is no teacher in this case for training the machine. If the machine makes a right decision, the machine gets a positive point. If it makes a wrong decision, it gets a negative point for it. So repeating the process again and again and again, the machine learns it. So this process is of reinforcement learning. So let's take the example of a self-driving car over here. So initially, when the car was trained, so the car didn't know what way to choose. Okay. So what it did, it made an action, but the action it performed was wrong. So it got a penalty of minus 50 points for that. So from the next time, car realized that what it did earlier was wrong, and it updates its policy and then iterates the process. Okay. So this is reinforcement learning. So let me just explain you reinforcement learning with the concept of how Pavlov trained his dog using reinforcement learning. So there's a famous example of how Pavlov trained his dog using reinforcement learning. So it's like initially Pavlov gave food to the dog. So in response to the food, the dog started salivating. Okay, this was before conditioning. Then in the next phase, what he did, he just rang a bell for which the dog did not respond anything. Okay, then the third phase, what he did, he rang the bell and then gave him the food. So seeing the food, the dog started salivating again. Then after that, he repeated this third step again and again and again until the dog learned it. Then after conditioning, whenever Pavlov used to ring the bell, the dog started salivating. He understood that whenever the bell is going to ring, his master is going to give him the food. So this is how Pavlov trained his dog using reinforcement learning. Okay. One of the application or the use case of reinforcement learning is self-driving car. A recent study has shown that over 90% of road accidents are caused by human error. To err is human, but behind the wheel, mistakes are often more catastrophic. Accidents have led to a massive number of unnecessary deaths, lives that could have been saved otherwise through self-driving. So this is where self-driving cars comes into picture. The autonomous car or the self-driving cars are much safer than human-driven car. They are unaffected by factors like driver fatigue, emotions or illness. This makes them very safe. Self-driving cars are always active and attentive, observing the environments and scanning multiple directions. It would be difficult to make a move that car has not anticipated. So how does a self-driving car work? Well, self-driving cars mainly rely on three technologies: IoT sensors, IoT connectivity, and software algorithm. There are many types of sensor available for a self-driving car. For example, sensor for blind spot monitoring, forward collision warning, radar, camera, lidar, and ultrasonic. So all of these IoT sensors work together to make navigation of a self-driving car. Next is the IoT connectivity. Self-driving cars uses cloud computing to act upon traffic data, weather, maps, adjacent cars, and surface conditioning among others. This helps them to monitor their surroundings better and make informed decisions. And next is the software algorithm. All the data the car collects need to be analyzed to determine the best course of action. This is the main function of the control algorithm and software, and this is where reinforcement learning comes into picture. This is the most complex part of the self-driving car since it has to make decision flawless. A flaw like in case of Uber's self-driving car can be fatal. Okay? In today's world, the most famous self-driving car are those from Tesla and Google. Tesla cars work by analyzing the environment using a software system known as Autopilot. Autopilot uses high-tech cameras to view and collect data from the world, same as what we do with our eyes. It's called as computer vision or sophisticated image recognition. It then interprets this information and makes the best decisions based on it. So this was one of the use case of reinforcement learning. Okay.
To start with this linear regression, right? You all must be remembering the linear equation that we have, right? So what was that linear equation that we used to have in our school days? It was something like this, right? Y equals mx, sorry. So the form was y equals mx plus c, right? So the form was y equals mx plus c, right? This was the form of the equation that we used to be getting in our getting for a linear line, right? So we had this kind of line from that equation, right? It might be, but depends on the value of m and c. I am taking c somewhere is there, so this kind of lines we will be getting. And here, let's say this point is x1 y1, so for this one is x1, so this point up here in the line will be x1 y1, right? This point up here will be x1 y1. So for the value of x1 we have this value of y1. So in here, if you see this variable, this was used to be called dependent variable, right? Dependent variable. Why dependent? Because it always changes with the value of x, but x doesn't have any limit. So this is called independent variable, right? This is called independent variable. So x is independent, y is dependent, right? So that kind of equations we used to have. Okay, and this aim here, right? This aim here, this aim used to be called slope of the line, right? This was used to be called slope of the line. This c was some constant which can be zero also, right? C is some constant which can be zero. So that's what we had in our linear line equations. Now the thing is, how do we use this for our class, like for this linear regression models to be built? Okay, so the entire thing is based on this concept only, y equals mx plus c. It is as simple as that. So we will have some kind of a equation which will be in the form of y equals mx plus c. We will predict the values of the data points that is being sent to our data set when it is deployed, and then we will get the values of y. Okay, so that's what is the whole concept of machine learning, linear regression. So linear regression is a technique to find relationship between two or more variables. Yes, right? So if we have more than two variables, then how the equation will look like? It will be, let's say y depends on more than one, right? So it will be mx plus ny, sorry, nz, something like that. So mx plus na plus let's say pc plus d, kind of this kind of equations, right? So here it will have three variables, three independent variables, x, a, and c, right? Three variables we will be having in that case, right? Three variables we'll be having in that case. So that's where this machine learning comes into picture, and that's how this machine learning thing works. Okay, that's how the machine learning works. Now let's see how we are going to use it for our model. So that's why, so this is called linear because it is based on the equation of a linear line. Okay, it is based on the equation of a straight line actually. Okay, so as I told, change in dependent variable is associated with the change in one or more independent variables, right? So that's the basic concept of the equations. Okay, next is this picture. This is called Rex Thor, the dog bearer. Okay, so if you see the right hand side, guys who are aware with Avengers, they must be recognizing the right hand side guy is some kind of a Thor. It look like Thor. He carries a dog, right? Instead of carrying a hammer, he carries or a stormbreaker. He is carrying a dog, right? So he is named as Rex Thor, the dog bearer. So there is in the, we know, right? There are seven stars in the planet which has some kind of a shape. So it is one of them. Okay, this is a star pattern actually. So why we are taking this here is, this is the data point, right? In the left hand side, this is the data point, and this is how the thing looks like. So if you draw this line, then this is, I mean, you see like there is a lot of difference between lines, right? So that's how it looks, and there is a concept of r square. R square means mean squared error. Okay, that is also known as goodness of fit. Okay, that we will be covering in the next sessions. So you will see when r square gets minimum, that means the model has huge error. So here see the r square value is pretty small, right? It is 0.06. That means this line up here doesn't at all represent this model. Okay, so that's how this linear regression works, and with the help of this goodness of fit r square value, we can somewhat check the model's performance also. So that is a statistical test. At the end of the class, I will be telling you that, like the theory behind it, how those are calculated, and those part. Okay, so that is what is about linear regression. It's that much easy only. Okay, it's nothing more complex. More, not much of a complexity is there in the in this linear regression. So it's far too easy. So next there are a few examples of linear regressions. Okay, so where, yeah, I told, right, Ravi? So r square I will be coming later. It is a mean squared error. So it is a goodness of fit test. That is a r squared test, you can tell. So I will be coming to that in the last part. Okay, I will tell you the theory and everything also. No need to worry. Okay. So this is the regression is a technique that displays the relationship between y and x, as you already know. So if temperature drops down, the guys will start putting more jackets, more jackets to avoid the cold, right? To keep them warm. So that's a straightforward relation between two variables. This is an example of linear regression. Okay, temperature versus number of cones sold at the ice cream store. If it's gets hot at outside, then the number of ice cream sold will be more, right? Inches of rain versus new cars sold. So that means in the rainy season, guys would like to avoid going out without their car, right? So that's how. Daily snowfall versus number of skiers. So if snowfall is higher, number of visitors at the skiing park will be increased, right? So that's how this works. Now this is the base of it. So if you think there is a relationship between two things, regression would help confirm it. That means if at all there is a relationship between those lines, let's say I will draw you a plot first. Okay, so let's say here is a plot I am drawing. Come on, why it is too large? I want something smaller. So if you see there is some data points, let's say this one, say this one, say this one, this one. So see here is a perfect relation, right? But again, this is not a linear relation, right? So if you draw it otherwise, if we say there is kind of a this line goes in, so this is the best linear regression line that can be fit in, then also this doesn't seem to be a good relation between them, right? So linear regression will help you to understand if there is any relationship between two variables or not. Okay, so that's how linear regression works. So you will build a model. If the model performs poorly and no ways you can fine tune the model, that means there is not much of a linear relation between them, right? If there is a linear relation, then it will look good, right? So the goodness of it would look good. So here is an classic example. So if you see, the values here are categorical, right? Why categorical? Because y only has two values, y0, y1, right? Only two values. So in this two values, if you see, they are categorical values, and it comes under a lambda shift function, right? I mean, sorry, sigmoid function, this kind of right, s kind of a function. So this is called sigmoid function, right? So that's how this thing goes in. Okay, so here if you draw the linear regression line, it will fail miserably. Okay, because if you calculate the r square fit for this, it will be too low number, because it is not at all a good fit, right? So this one is example of linear regression, this one is for logistic regression. So to see how this linear regression helps here, if you draw this line, if you build this model using this line, then only it will be cleared that there is no linear relationship between these two data points. Okay, these two data points. Okay, so that's how it goes. Okay, so next we will be going to a few scenarios when we can use linear regression, and when do we go for logistic regression. Okay, these are a few types or a few factors which will help us deciding that. Okay, so see here, first of all, it will be continuous. For linear regression, the variables has to be continuous. That means it shouldn't be categorical or skewed at any 2 points, right? So it will solve regression issues. That means it should be a good fit. Okay, good fit to a point to some data points. Okay, and it should be somewhat it should be represented by a straight line curve. Okay, so in this case is match, so then it will be a perfect fit for linear regression. So it has to be continuous variables. That means the spread of the data, it shouldn't be skewed, so it should be somewhere it should be spread out evenly among this in the xy plane. Actually, it should have a straight line kind of a relation between them, and it should solve regression issues. Regression issues means where we have a lot of data, we churn those data to find out some basic data, basic inference. Actually, when I say this, both of these are supervised learning algorithms, so don't confuse that. So here what we'll have, we will be for both the cases, for both the cases we will be having this values, right? Like we will be having training values, right? But here we will have some output, that will be spread throughout the I mean that will be somewhat significant, not some classification things like 0 and 1, the gender split, male or female. It is a classification issue, a spam or not classification issue, predicting housing price, linear regression. Okay, this kind of things comes under linear regression. So if you see if you build a model of housing price predictor, there has to be some kind of a relation between all the variables, right? But for classification, it has to meet some criteria. There won't be any relation between those criteria individually, but there should be there should be a skewed value, and the variables will be categorical. Okay, when I say variables, so can anyone tell what is a variable? When we are telling variable, which one we are telling, like what we are actually trying to tell here when we are telling continuous variables and categorical variables? What are those? So if you get a data set, let's say there are 10 rows with 15 columns, so which one are we are telling about target variables? Okay, those parameters which impact the outcome, like dependent variables. So let's say if we have 10 rows and 15 columns, then 14 columns in that will be independent variables. Those are x values, they can go anywhere. Okay, the variables, the target variables will be the dependent variables, right? When we say continuous and categorical, that is the dependent variables, that is the y values, that is the outcome values, right? Because independent variables can be anywhere, right? It can be anywhere in the plane, correct? So that's why when we consider fitting a model, we shouldn't be looking at the feature first, we should look at what kind of output we are expecting. So is the output is somewhat categorical or regression? What is it? The outputs will be in continuous variables. Let's say housing price. If you have 10 lakhs rows of data, so you are most probably will be having all the numbers between 20 lakhs to 1 crore, right? Depending on the scenario. So that's a continuous space, correct? But categorical things, when we are deciding on mail classifier, spam classifier, right? Spam or not, it's two values, 1 0 or 1, right? So categorical things, right? So that's how we decide on this linear regression and logistic regression. Okay, so it's y here, it's Nancy, it's y here. So when I tell the outcome, that is the y, right? That independent variable. For x, those will be independent ones, they can go anywhere. Those will be the features of your data set on which you will build the models. When you say y equals mx plus c, this x will be independent one, it can go anywhere, right? So you really can't judge from that, right? Because for a categorical, if you think for a spam classifier, what all things can be there, what all things okay, let's forget it. Okay, think about Titanic survival dataset. So let's say you have the dataset of surviving from Titanic mishap, and you have all rows in there, right? So the values will be like sex, age, which parts they were in, right? So those things will be there, right? So let's say we have a housing price dataset. Okay, so in the housing price, what kind of columns you will have? Let's say area. So let's say we have a point called area. Okay, we have something called garden space. Okay, we have number of flats, amenities. These all can be realistic features. These all can be realistic features of your housing price predicted dataset, right? So with the help of this, we will predict a housing price, correct? Let's say we have a survival dataset. Let's say cancer dataset. Okay, so for predicting cancers, we have a dataset like that. For that, we will have internal or external. Let's say some kind of some things like that. Come on, again it went to scratch mode. Internal or external, right? Then we will have a size, we will have malignant or benign, etc. Okay, so what it will predict, yes or no? So you have a gland growth, is it a cancer or is it not? So yes, no. These variable types are called categorical ones. Okay, this kind of variables. So let's say if you are trying to buy a house somewhere in Mumbai, this value will range from 1 crore to 5 crore, and you are most likely to get this area because of this different size, different types of area values. You will get almost all the values between this range. Let's say 1 crore to 2 crore. Let's not go to 5, let's go to 2. Okay, so you will get all kind of values. So this is the things. Okay, so that's how you need to predict which one to use, right? So usually fixed number or possible. No, Saran, actually categoricals will be skewed. Okay, so it can be more than one also. Let's say we have, when we are thinking about this kind of categorical problem, it can be yes, no. It can be yes, no, or moderate, like that. So it can be anything. It will be fixed. Okay, as you rightly told, it will be fixed. But for continuous, it will vary. It will be in a range. Okay, so that's how we decide if the data set that we are having is categorical or continuous. Okay, so based on that we decide, is it a regression problem or is it a classification problem, and based on that we are going to choose our models. If it's a regression, then we are going to go with this linear regression. Otherwise we are going to go with logistic regression, naive bayes, or xyz. Okay, that's how. Okay, let's go for go for some let's advance with the course actually. So here is something that I have already discussed, right? We have already discussed, and that's why I took some time, because this thing. So that's the line equation. These are the some variables. These are called observables. This red points. This line is called line of linear regression. That means this is the outcome of your model. These points will be observations, right? And this will be regression line. And how do we decide if the regression line is a good fit or not? We use least square method. Okay, least square method that we'll discuss. Okay, so how do we do that? It's time to discuss that. I will show you with the graph. So let's say we have this kind of a line. Okay, let's say we have a point here. This is x1 y1. Okay, we have a point here. This is x2 y2. Okay, we have a point here. This is x3 y3. Okay, let's keep it to 3 lines. Okay, and somewhere down here, based on this line outcome, okay, this one is regression line. This will have separate kind of xy value. So for this one it will be somewhere here, for this one it will be here, and for this one it will be here. So these are like, here is the y value, here y value for this will be somewhere here, for this value will be somewhere here. So mean of them will be this one. Okay, let me change the color. Okay, mean of them will be this 3, so somewhere around here. This is the mean. Okay, this is the mean of y. Okay, which will denote as y bar. Okay, we will denote as y bar. Okay, now see the basic concept. How do we calculate? Okay, the basic concept of how do we calculate this? Okay, how do we calculate the r square? So these points, if you see, these blue lines are called error from line. Okay, error from regression line. Okay, if I write the equation, that is, we are going to, so as you know, the point distance, how it looks like, x minus x1 y minus y1, right? So that is basically this. So here x1 will be common in both, so it will be the value outcome of this AC line, that is squared error SE for line SE. I am scrolling it a bit up. So we will, what we have, SE of line will be y1 minus y squared plus y2 minus y squared plus y3 minus y squared up to n. This is the standard line error, because this is, if we consider this as y1 and all these values are x's, right? So when I write x, when I write y, that means y actual. Okay, when this y3 means y predicted. Okay, so sorry, I just reverse it. Okay, this is y actual, this is y predicted. So when I say y1 y2 y3, these are these points, right? So these are the original points that we have, so it will be y actual. Y means y predicted, that is outcome from this line. Okay, so y actual, y predicted, like that. Okay, for x1, for x2, for x3. Okay, this is what is denote squared error from the line of linear regression. Okay, this is what is denoted by this. Now I will change the pen color. So if we see squared error from y bar, that is y mean, that is from this red line. I was using a red, let's go back. So this is the point, this is the red line. So this one is the squared error from line. So here is the point. So this one will be the squared error from the mean of the data set. Okay, this is the squared error from the mean of the data set. So what we will have, we will have y1 minus y bar square plus y2 minus y bar square plus dot dot up to n, right? Now understand one thing, this value over here is how likely, what is the error between the linear regression line and the data points, right? This value up here is to find out the central tendency of the errors, right? So if you find out mean of these values, this y predicted values, and if you find out the difference between the actual points and the y predicted mean values, that means this is the variance. Okay, this is the distance and this is the variance. Okay, this part is the variance from all y values, this is the distance from each and individual y values. Now in order to get the r square estimate, that is the good fit line, or if it's a good fit or not, what we do, we calculate this value, that is se line divided by se y bar. Okay, we have this kind of a value. So what this denotes, how unlikely the line matches the actual values. Okay, this is what we denote by this part, right? Now if you want to know how good is the model, what we do, we subtract it from 1. This becomes our goodness of fit. For statisticians named it as r squared, or it is also known as least, this is also known as least squared error method. Okay, so this up here denotes goodness of fit, that means how good our model is. Now see what happens to this. Okay, after this I will pause for questions. So the value that we have, right? So the value that we have is somewhere like 1 minus SC line. So 1 minus SE line divided by SE y bar. So if AC line is pretty smaller, right? What does that mean? The line is a really good fit. So this is small divided by SC y bar. This will also get very small, right? If the difference between the each and individual data point is small, this will also get somewhat small. A small number by some number will yield you a small, even a smaller number, right? So that will approx reach to 1. Okay, but if for this equation, the the SE line gets higher and we have a CY bar which will get even higher, which will get somewhere around this, right? So, but it shouldn't be, as this is the higher but less than SE line, so we will have a high value up here. In the SE line we will have a high value. Okay, so this so how it works, this AC y bar, let's say for this equation, if we go back, if the points are even more down, right? So from, if the point is somewhere here, so somewhere here, all the values will be bigger, right? Based on this AC bar and the AC line, all the values will be bigger. So when we divide two big values, it will almost come to 1 and r square value will approx to 0. Okay, so that's what means when r square is small, bad fit. Okay, when r square is large, good fit. Okay, that's why this value r square is named as goodness of fit. Okay, so that's what is about this goodness of fit equation. Okay, these things I already told, this xy things. Now here is an example for you guys. Okay, so we have a few data points, we have plotted all this in the plot. Okay, we have plotted all these data points in here. Okay, now we will see using linear regression how do we calculate this. Okay, so x bar y bar is there. That is the mean of x and mean of y. Mean of x is 3, mean of y is 3.6. Now this is the line, this is the line, and this is the mean point is described with this red point, and this line, right, this green line is for the I mean the mean line. Okay, this is the mean line that we have, that is the y bar that we have. This is the mx plus c line that we have drawn till now. As we know from maths, this is the equation for m, that is the slope. That's how we calculate. So once we calculate m, you will see the value here. I am just scrolling through. Okay, these are some calculations, so I am not wasting time. So that's how we find out the value of m. Okay, so what does that mean? Let me show a few use cases. So if this is the line, now we need to find out value of m. M is x minus x bar into y minus y bar divided by x minus x square, x minus x bar square. Okay, now if we go in, so x minus x bar, when we calculate, that is the difference of the data points from its x mean. Okay, x mean. So these are the data point differences. We calculate this here. We put into the equation. Then we go for difference of y, that is y bar, because we need to calculate y minus y bar here, right? So this will be the differences. So this one will be the difference, this one will be the difference, like that we will calculate. Okay, so that's how we will have y minus y bar. We already have x minus x bar, we will square it out here. Then we will find out m by summarizing all this. We will sum all these things up and we will divide it by sum of this thing, and we will get the output. Okay, we will get the output. So here m value goes to 0.1. Okay, now y will be 3.6, m will be 0.1, x will be, let's say for 3 we are calculating. Okay, for 3, x equals 3 we are calculating, because as we see, for x equals 3, the mean is 3 and 3.6, right? So for x equals 3, the mean, we are calculating based on the means here. Now we will get the c value here, that is 3.3. Okay, so our straight line equations now becomes y equals 0.1x plus 3.3. Okay, so that's how we do calculate our linear equations. Okay, so this is the linear equation that we got from this data set. Okay, now what we will do, we will try to predict the values of x equals 1 2 3 4 5. Why this formula? That is the formula for m, actually, I'm code, that's why. Okay, so that's how. So now what we have the straight line equation. We have the actual values of x and y's from this data set, that is from x equals 1 2 3 4 5. We have the values of y 4 3 4 2 5, right? Now we will predict using the equation that we got to test our model how good it is, how good our model fits our actual data points. Okay, so this is the line y equals 0 points y equals 0.1x plus 3.3. So 1 2 3 4 5 we have. Now if we go on calculating all these values, we will get something like this. Okay, so this is again calculated wrong, this will be 3.4. Anyways, just leave it. Okay, no need to worry about it. The values here are might be here and there, values here might be here and there, don't think about it, it's fine. If they have made some mistakes might be, so just ignore this. So we will have this values as an outcome from our model. Okay, now we will find out the r square. Okay, we will find out the r square. Okay, so we will go to it and we will try to find out the r square values. Okay, so as you know, I told yp minus y bar square by y minus y bar square, right? That is r square, and it should be 1 minus. Okay, that's what would be r square. So y predicted minus y mean divided by y minus y mean square, like that. So okay, it is somewhat okay, got it. So in this equation that I have shown, if you subtract 1 from it, it will be something like this. Okay, if you subtract 1 and if you solve the equation, it will be something like this, or else you can go with the equation that we have taken also, both are fine. Okay, this is the minimalized version. So when we say that, that means, when I say that, so we have 1 minus AC line by AC y bar, right? So if we solve this, it will be AC y bar minus AC line by AC y bar, right? So what is AC line is y1 minus y square, right? What is AC y bar? Y minus y1 minus y bar square, right? If you equate how it will look like, if you equate how it will look like, it will look like y1 minus y square divided by, sorry, how it will look like is y1 will cancel out, so we will have, sorry, I wrote it wrong. What we will have? We will have, sorry, y minus y bar square divided by AC y bar. What is that? That is again y1 minus y bar square, right? That's what we will have, right? So when we do this, we get this equation. Okay, so that's why r square is written like this. Okay, that is also an equation. So if we go and calculate, we will see the r square value what we are getting. It is 0.36. Okay, so that is a small value, so this line is not good. So in the next step, what we will do, so we will just turn the line. Okay, we will just change the line equation, and we will just try to check how our model performs. Okay, so till we get a good r square value that is almost equals 1, we will keep on rotating the line till it fits the entire data point. Okay, till it fits the entire data point. Okay, that's how this goodness of fit works. Yeah.
Can you just take out to the slide where the M formula is given? It's a statistical formula. Something
Yeah,
x
right.
minus x. Yeah, can you just check it out?
Yeah, 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 this one, right? X minus x bar,
Yeah,
y
right.
minus y bar by x minus x bar square. Yeah,
So when I'm changing n, I'm changing x even, right? If I change it, I'm thinking very mathematically. If I change
yeah,
m, the formula,
yeah.
my x values should also change as well as the y values.
No,
That's
no,
big
no,
since
no.
the
Only
formula
y
is
value
dependent.
will be changed, right? No, no, no. Only y value will be changed, right?
Okay, so
So
means
when we
only the
say
y minus
y,
y bar section will change
correct.
in
Yeah,
that
think about it.
formula.
Think of just if you go mathematically, x points won't associate. This is, I mean, if you try to fit it with the, I mean, see, so if someone is from stats background, he will get this far too easily, or if someone has done some study before coming to the class of stats, it will be really easy. If you think from the maths point of context, then we are not at all worried about goodness of fit, right? We will get some equations, we will find out m and c values, and we will just go ahead and fit the line, right? That's it, our job is done. We no need to check, even we no need to check if it's a good fit or not. Correct. Now this goodness of fit testing comes into place when we are working with a set of data points where we are worried about the model that we have created, the hypothesis that we have taken. So this is basically the null hypothesis. You can consider it like that if you go to the stats. So see, when we come to machine learning, one thing has to be remembered. It is, I would say, for my experience, it is 50 to 55% of stats, 30 to 35% of algorithms, rest of the portions are for your intuitions and programming. Okay, so that's how it works. So that's why stats needs to be crystal clear for machine learning. It has to be. So what happens is, when you try and predict the values of y, and if you try to see if the model fits well or not, right? So you now, here comes the picture. So how you can change the line to fit, make it better. Okay, how you can change the line? X value won't change if you, because x values will be fixed, because you have already been provided with a data set. What it can change is the outcome values, right? X will fix, but the outcome from the linear regression line, I am not talking about the target variables that is already there in the data set. Okay, I am talking about the predicted values that you are predicting with your model. X won't change, this y alone can change. That's what the concept of linear equation, right? Y is dependent variable on on x, right? X won't change. So if you change x, the whole data set will be lost. So what it will do, you can change the m and c values to find a good fit for y. Okay, x bar won't change, Azam, because x will always be fixed. Y bar will be changed because the output of your linear regression line will be changed. Okay, so that's how we keep on changing our models. We keep on changing the hyperparameters. That's what these are called. This M and C are called hyperparameters to a model, right? So when we change M and C, the entire equation of y equals mx plus c will yield you some other result. So that's how you can tune in y, the output value. You can tune in to try and match with the exact data set that you have. So if y bar changes, y will automatically change, right? So that means it will help you in two ways. It will help you in reducing the squared line error also. Also, it will help you in reducing the error between the mean and the data points. Okay, that's what this works. That's what this linear equation works. And for that to change, you need to change the M and C values. The hyperparameters will get changed. Then you apply the goodness of fit. You will see if the value is coming near equals 1, then it would be a good fit. If it doesn't, then it wouldn't be a good fit. You would need to go for another iteration. Okay, so that's what it go that's how it goes in. Okay, that's what the concept of this is. Okay, so is this clear now, guys?
No, here m is a mean, right? This m point 1 is a mean, right?
No, m is the slope, right?
Slope.
from
Okay.
the from the from the straight line equation y equals mx plus c, the m is the slope, right? M is not the mean.
Okay. How about the c? How are you going to calculate c here?
That's a random variable, right? You can change it according to your need. So if you need it bigger, so it is a constant, but it can be changed also, right? You can change c, because c, if you want to change the line, how can you change it? You need to change m and c. So let's say some point is sits at 0 0, right? So you need to make c value 0. Simple. Yeah, c equals y minus mx, correct? So once you find out the m values, you can find out the c value. So c also will get changed if you change m, right? That's what the idea is. Okay, so that's how this things works. Okay, so
So
that's how it is.
so basically, you will try to fit all these points in that good fit. So based
Not
on that,
all, but we will try
makes
to maximize the r square value. Okay,
so whichever the good fit from there, will take the value of c.
correct,
That
correct.
okay.
Now I will go to how it is applied to machine learning. Okay, this is all the stats one. It is not, machine learning hasn't started yet. Okay, now I will show you how you can do this. Okay, so let's go ahead with this. So as you might be already aware, I discussed in the last class about the terms like features and there are a few terms, right? Features, target variables, outcomes, hypothesis, and all those. Now you will see those in action. Okay. For machine learning, what we have for linear regression, actually, what we have, we take for machine learning in general also, we take a hypothesis. Okay, and hypothesis will be h theta x. Okay, and when we write the equation for linear regression, it should be theta 0 plus theta 1 x. This theta 1 is equivalent to m. This theta 0 is equivalent to c. Together, this theta 0 and theta 1 are called hyperparameters. With trial and error, we can change these values of theta 0 and theta 1 to get a good h theta. That is, this h theta value will be the predicted value. This will be the predicted value. Okay, so that's how this predicted value will be calculated for a machine learning. For machine learning, that's how this h theta of x will get calculated. Okay, so h theta of x will be equals theta 0 plus theta 1 of x. Okay, that will be the equation when we come to the machine learning world. So what do we do now? How do we apply x? So when I say x will be the feature vector. That means columns of a data set, right? That's what is called feature. So this h theta x we will calculate based on the features. So everything here is a vector. So when I say theta 0, this is constant, plus theta 1 x1 plus theta 2 x2 if we have more than one feature, theta 3 x3, and this will go up to theta n xn. Okay, that's how this equation will look like when you try to write this in a machine learning format. Okay, so this h theta x will be our hypothesis. This will yield you the values of predicted y, values of predicted y, right? What will be the equation? This will be the equation. So if you carefully see this equation, x1 can't change. What can change is theta 0 and theta 1. So in real world, how do we go of it? First of all, what we do, we take a constant value of theta. That is theta 0, we can make it 0 or 1. 0 is the standard approach to start with. So then what we will do, we will calculate, we will take some arbitrary values of theta, okay, to calculate this equation. We will take out the h theta of x, that is our predicted value, using this equation. This theta vector is based on, we will take some, so this theta vector is also called weightage vector. Okay, what do we mean by weightage vector? Think about survival data set. Okay, think about house price, house market, I mean, what should we think about, let's say, I mean, housing price calculator. Let's go with the classic example only, housing price. Now for housing price, just, I mean, for housing price calculator, as this matter that what color is the building, what color is the building. So when you are going to buy a flat, will that matter to you? If the building that you are going to buy, I mean the price of it can matter to you, that's obvious, but will the price depend on this? What color is the building? Price won't take this into account, so we can vanish this variable. So we can take theta of color to be 0 because this is nowhere related in the data set, right? But if you see area, that is a huge point, so we will give it a good weightage. So let's say theta a, we will give it a good weightage. So that's how you need to, yeah, you can have it 1 also, you can have near to 1, anything. So it will be depending on your model, I will come to it. So this theta values will be calculated based on the model that we have. Okay, this theta value we will keep on changing. So in order to, so what is the basic? Again, I am repeating these things. Luckily, you no need to code it, or you no need to do this manually. This will be taken care by Python itself. The scikit-learn package will take care of these things, this tuning, this theta parameters. Okay, our objective would be to get a good fit of our model by changing this theta parameter. Let's say if by mistake, so this color variable, right, this will have some arbitrary values, right? So what we will do, we will have pink, green, black, like this. We will convert this into categorical values. So there might be hundreds of colors from 0, 1, 2, 3, 4, like that. So if you by mistake apply a very high weightage to this color variable, this color vector, so let's say theta color, if you have taken a very large value, so when the color value reaches about 100, it will hugely destroy your model, right? Because that is not at all taken into account while deciding the price of the house, right? So in the next step, what you would do, you would do this theta hyperparameter tuning. You will check for this unusual, I mean, check for the values when you won't be getting this kind of a error, and you will try to get a good fit of the line. Okay, we will try to get a good fit of the line. So when the algorithm works, what it does, it will take into account all features, then it will predict value, then it will check for fit, good fit line will be returned, the best fit line from all the equation will be returned. So all this feature vectors that we have, all the theta vector that we have, it will change on its own, and then it will return you the value. Okay, so that's what will be the task of this linear regression equation. Now as a machine learning engineer, what would be your say in this? Your say will be to check these things, okay, to check the values. Do we have this colored data set? Remove that. No need to give machine the extra headache. So how does the model react? How you can make the performance better? For this house, one thing we all check for, right? Price per square foot, right? We always check for this one, correct? If this value is not there, if the feature is not there, introduce it. It will hugely increase your your model performance, correct? If you don't have this amenities field, amenities does make your house price go from zero to hero, right? Because if you don't have a library in your if you don't have a library or open playground in your complex, versus if you have it, your model will change radically, right? So amenities will play a good role. So amenities, if the number of more the amenities are, the bit higher the prices are. Okay, so that's how, and that's what will be your job, to check the values that is being returned. And yes, exactly, we would need to select a proper model will be selected by the machine learning algorithm only. We would, yeah, your task will be to validate the requirement, validate the model. Theta value will be linear regression, yes, right, by the algorithm itself. This theta value will be taken into account. Okay, your task will be to prune that algorithm, because the machine won't have the domain knowledge, the machine won't be having those much of knowledge as of you, right? So that's what will be your task. Your task will be to tune the model. Your task will be to find the best fit. You can introduce features to the dataset also, right? We have seen, like, we can do that. I have shown you, right? So these things will take into account. These things will help you in deciding all these things. That's how you will decide the h theta that you are going to take. You will, that's how your machine will help you. That's how your algorithm will help you to decide this. Okay, we can change the base alone based on our knowledge, yes, right, but this will be taken care by the model itself. Okay, the model will return you the best fit. So no need to worry. This theta values manually will be changed by the algorithm, and it will return you the best fit. So how it will return the best fit? It will use two concepts called cost function. And so when I am saying the model will return you these things, it will use these functions to return you the good fit. Okay, these things just remember. Okay, these things just remember. Or what you can do, if you forget this, just go ahead and Google this a bit. You will have a really good picture of it. Okay, so that's how this thing works. Okay, that's how this machine learning things works. That's how from y equals mx plus c can be transferred to a multivariate machine learning, and you can apply it to apply the machine learning model to it. Ankur, all variables can change. You need to figure out the best variable. Okay, the best variable that will introduce more. Like for approving a loan, you will take credit score into account, right? Credit score into account. That will help you in applying the loan. You will need to check if the guy is salaried or professional, right? That will help you. Okay, so these kind of things you need to check to do build a good model.
So you want to say that
Okay.
which variables are the related each other, so we have to find it out, and so that it will be good. We'll get a good fit line, right?
Yes, correct. So how you can find that out? You can find that out with correlation matrix, right? If
Yes.
there is any relation or not, right? So that's why I am trying to focus on this, trying to focus on the stats concept hugely. What this correlation means, how this machines can be treated, how this R square value can be calculated, like that. Okay.
So one thing here, before starting anything, so we have to first check is to go to the check for R square, correct? Whether data is good or something is there, right?
If you don't have a model, right, how can you check it? So first task will be to build a model. Then you can check for
Correct.
the R square value, right?
Mm-hmm.
Related values should be passed as dependent. Yes, right, Ravi. So that's how. So you need to find out which values. So see, this will come in two ways. First, stats will help you. Next, your domain knowledge will help you. Okay. Once you have this two, this will help you to get the good model. Okay. Okay. So that's how.
Okay.
Yes, Nancy. So hypothesis is just a random guess. Okay, let's say the thing I was telling, like India will win the World Cup. That is a hypothesis. Okay, it's a random guess. So if you are familiar with mathematical induction, right? How we used to do, we used to take a null hypothesis that will be true for x equal n equals 0. Then we will prove it for n equals 2. Then we will prove it for n minus 1. Then we will say it is true for n also, right? Like that, we used to do mathematical induction. So all these things that we take into account is a hypothesis. So that's just a wild guess. So when you are saying h theta x equals theta 0 plus theta 1 x1 theta 2 x2 like that, so that becomes our hypothesis, because we don't know the values of theta 0 theta 1 yet, and we are going to predict something. So now, based on our testing, the goodness of fit testing, or how we do it, I will show you right now. Goodness of fit testing, how good the model is, how good the hypothesis is, that's how it works. Okay, so it is basically just a wild guess. So it will be the first equation that you derive from. So this is theta was theta 0 theta 1. Well, you need to start from some value, right? So that's what I told, like you using trial and error, you will visit all the values of theta for which the cost function will get minimized. Okay, so the first hypothesis will be the null hypothesis. So for that, let's say we are taking theta 0 as 0, so that will be the null hypothesis. Okay, then we will keep on continuing this. So that's what is about hypothesis. Okay, so that's how we have it. Yeah, no mentions. Okay, so now let's see what is cost function. Okay, so we have seen this r square, right? R square is goodness of fit that we have seen, right? If you now, what we will do, we will calculate cost function of h theta x. What will be the cost function? How do we go about it? So if we have m number of data points in our bucket, then this will be the equation of cost function. Okay, so what is it? R theta is square. This is for each and individual point value of r square, we will sum it up and will divide it by twice the number of data points. Now our target will be, our model's target will be to minimize this, to get the best model. Okay, we need to minimize this cost function value to get a good model. Okay, so for that, what we can do, as I was telling, for goodness of fit, we need to change theta values to achieve this. Now graphically, if you see, I will draw some kind of a plot which will be known as, which is known as contour plot. If you don't know it, don't think of it. Okay, this kind of plots are called contour plots. Sorry for my bad drawing. So let's say this is the mean of the data point. Some data point is in here. So by changing the theta values, we will come inside. We will come here, then we will come here, then we will come here, then we will come here, like that. Okay, so this is called gradient descent algorithm. This is not at all required, just telling you the basics. This gradient descent just to show you what is it. So using this gradient descent, we try to arrive at the minimalistic cost function. Then we will have the values of theta, like from the gradient descent algorithm itself, we will get the values of theta for which the cost function gets minimized, and then we will apply those theta values into this equation. So that will yield you the machine learning model that you are trying to build. So the concept is, using gradient descent, we will minimize the cost function for the data set. And after that, once we get the hyperparameter values, that is the theta values, we will replace those in the main equation, which will yield you the best possible values, the best possible equation that can be derived from the model. Okay, so that's how your entire linear regression algorithm works. Okay, so how do we go about it? Let me tell you in 3 simple steps. First step, we will take a null hypothesis that will be theta 0 theta 1 x1 theta 2 x2, like that, based on the number of features that we are going to supply to the model. We will find out the value for the predicted value, that is the value for the h theta x for all the data points. Then the next step will be to calculate the r square value for each individual sets. Okay, so we will have some kind of theta 0 values, right? So for that, we will calculate the r square values for all theta sets. We will sum it up and then we will find the minimum value. So how do we find the minimum value? We do it using gradient descent. So gradient descent itself has a very large base. I am not going into that much detail, that won't be required. So it will be, there will be derivatives and all involved to get you the minimum value. Okay, to get you the minimum cost function value for some theta value, you will get the minimum cost function, which will then yield you a good result. Okay, which will then yield you a good result. So using that you can, so using that you will get the value of it. Okay, so using this using those theta values that is returned by the gradient descent algorithm, you will get the model equation. So you will arrive at your original model, and after that you can start predicting. Okay, after that you can start predicting with that model. So whatever unseen data comes into picture, it will be predicted, and with the help of this gradient descent and goodness of fit test, it will yield you the ideal theta value of theta. Okay, ideal value of theta. Okay, so that's how we have it. Okay, that's how we have it. That's what is about this linear regression as a whole.
Regarding the hypothesis equation, we saw that h naught x is equal hx is equal to h naught plus h1x, and as well as it goes on, right? So if I
Yes, h theta x equals
want to
theta 0. Yeah, right.
right. So now we are right now my objective is finding out the theta naught values for individual prediction for x, right? Is
Yeah,
it what I'm doing? Okay, fine. So after that we are trying to minimize it, right?
we
That's
are
what
trying
gives
to
me the best
minimize
prediction.
the cost. We are trying to minimize the
Cost
cost
function, right?
function. That is, we want to minimize
Okay.
the error in the model. That's why
We want
we are not
we want to
minimizing
minimize.
the theta values.
Okay, so how it is different from R square, what we did earlier for the linear regression model? Like in R
It's a
square, I was seeing that we were trying to make it as nearer as to 1. But right now I'm
yeah,
like trying to decrease it to almost nearer to 0. So
yeah.
how it
So
is,
if you
how can I relate
see, right, yeah, if you see here, I have taken a summation of it, right, and I have taken a summation of it and I have divided it with a 2m. So that is what the cost function look like. So it is nothing but finding the best R square value. That is R square, if it goes near equals 1, then that will be the best fit of the model. And if, as I am dividing it with 2m, it's a very large number, so it will be minimized, right? So that's why we are telling that we need to minimize the cost function. As we are taking the summations, that's why it is like that. So when I say summation, that means for each an individual point we will be calculate this r theta square values. Okay, so if what is the thing is, if we have this fancy equation of r square, right, this AC line by AC y bar, right? So here now for AC line, instead of y minus y1, we will have a theta value included, right? So where is it? Yeah, so y actual minus y predicted is now h theta x. So we will have a theta component for each of these equations, right? So that's why I have written it as r theta j. Okay, so that doesn't mean that it is for all other points, but it is for the entire equation. Okay, so if I calculate this value, this r square has to be somewhere near around 1 to get a good fit. Okay, so that's why we are, when I say minimizing the cost function, means not the value. Okay, it's the whole idea that r square has to be near equals 1. So that's what is referred to as minimizing the cost function. Okay, it is not like that we are reducing the value of r square. We are not looking for a small value. When I say minimize this, that means we are minimizing the value of cost function to get a good fit. Okay, so that's how the things are. The
uh,
r's
just to add up, Abhishek, so what you consider better, like making r square almost equal to 1 or cost factor almost equal to 0? Which one would be I would be considering as a better fit, or
for
is
same
it
thing, right?
interdependent? Is it interdependent? Like if my r square will be almost equal to 1, then my cost factor automatically will go down to 0.
So that won't happen, right? From the equation only you can see. So the idea is you need to have a r square. That's what I am trying to explain, right? When I say minimize the value of cost function, that means get the best fit out of it. So how you can get the best fit out of it? By getting this r theta square as the highest, right? So that's what it is. Okay, so it is, we are not like that cost function value we are trying to reduce it to 0. we want to find out some cost function value for which the R square will be near equals 1. So that's how it works. Okay, minimize, don't take it as the term goes. Okay, but cost function, as the name indicates, we should take its minimum value. Okay, so minimum value means best case. For R square, that is, there are other estimates also for this error. Okay, R square is not the only one, so we have log likelihood and others also that you will see in the later classes. So in the all the cases I will use the term like minimize the cost function. So when we say minimize the cost function, that means try to get the best fit out of it. So for R square, that is least squared error, when R square is really equals 1, and as we are dividing it by 2m, right, so it will be smaller. So that way we need to calculate. So R square has to be 1 for getting a best fit. R square has to be near equals 1. Okay, so that's how it works. Okay, so is this clear? That's not much we are doing. What we are doing, we are at first we are calculating the coefficients. Okay, the theory part that I have told till now, it is just to visualize that. So if you see, we are taking a data set that is x equals 1 2 3 4 2 1 to 10 and y some arbitrary values. We are trying to calculate our line from it. Okay, we are trying to calculate a line equation from it. So see, for the first step, what we are doing, we are trying to calculate the coefficient of it. So from the formulas that we have seen, np dot mean x, np dot mean y, like that, those things we have calculated, and we have calculated using the same formula that we have. So ssxy divided by ssxx, that's how the formula was, right? That's how the mathematical formula of slope is. So b1 here refers to the slope, okay, and b0 here refers to the coefficient, so that is y minus mx, right? So these things we have calculated, b0 and b1, and then we have plotted this x, y, and b, right? We have passed in x, y, and b to the plot regression line function, in which we have calculated the predicted y values, that is b0 plus b1x. Okay, then we have plotted those values of x and y predicted with a green line. Okay, with a green line. So this is the predictor line. Okay, in the x-axis we have set the size, and y-axis we have set the cost, and we have shown the line. So that's how your models will look like in the real world. Okay, so these data points will be your feature vectors, and that's how your model will look like. Okay, that's how your model will look like. And and we have printed the values of estimated coefficients as well. Okay, so that's how you by yourself can build this. Now in the next step, what you can do for getting linear regression, you can try adding the R square to it and looping it through. Okay, looping it through all the steps, but that won't be required as we already have this functionality available in scikit-learn package. Okay, in the scikit-learn package. So when we see examples of logistic regression, I will show you this. Okay, so we have seen two kinds of linear regressions, right? For one type of linear regression, I have shown you like theta 0 and theta 1 x1. Okay. For the other one, I have shown like there are x1 to xn values. So the first one is called single variable linear regression.
So y equal to mx plus c is a single variable linear regression, correct?
Yes,
And
yes,
theta
correct.
1 is the multi-variable linear regression.
No, not like that, not like that. It will be always of the form, mx plus c. Okay, so if you have only one independent variable, that is single variable linear regression equation. If you have multiple, univariate and multivariate, right? So for multivariate, you will have more than one those things, right? Those what are those called? Those are independent variables. More than one independent variables. Yeah, so more than one independent variable, multivariate, a single only one value we are taking, that is univariate. Okay, now we are looking at this fancy Boston house data set. Okay, so this is for calculating house prices. So if you see here, these are the data description. So see, this is our target variable, median value of owner occupied home in thousands. So whatever values you see, those are in thousands. Okay, so LSTAT is percentage lower status of the population, and all those kind of stuffs are there. There are some fancy explanations are there. So what we will do for the first example, we will take these two variables like LSTAT and MEDV. Okay, so let's see how it works. So also in order to go through that, checking correlation is a very important thing. Here it is not given, it is just to illustration purpose, but in the real world you will need to do it. Okay, you will need to check that. Okay, so here is the data set. As you all know, we read it using pd.read.csv. We read that, we check the step, we check the first 5 rows, then we are checking the mean, median, mode, and standard deviation, this equations. So now what we are doing, we have taken out the the dependent and independent variables. So lstat here will be independent variable, and MEDV will be dependent variable. So this is what we are going to find out. So here is how we read the files, right? Read.csv. Then we are seeing this data.shape, head, and all those. Then last we are checking the distributor stats. Now here we are taking out the independent variable here and dependent variable here into another data set, because this is a univariate example. So we will take only 2 data points. Okay, we will take only 2 data points. Now see here, I am we are seeing a kind of a, we are now plotting the data points, right? We are plotting the data points. So see, this kind of equations are there. Now there you can see the some kind of straight line will get automatically fit here, right? Let's see how it works. Okay. Okay, next is preparing data. So what we are doing now, we will be, what will be our next task? Our next task will be to prepare the data to see if there are any anomalies or not. So we have taken out lstat and MEDV, these 2 points from the data set that we have, okay. Then what we are doing, we are now doing a train state test split of 80-20. As I shown you in the last class, we are taking out the split. Now see the size, it is like that. So we have 404 values for training and 102 values for testing. Okay, so when I told you, right, for scikit-learn we have everything handy. See now what all we have wasted time for last 2.5 hours comes down to this single line: regressor is equals linear regression. That's it. All the things that I explained is there inside this linear regression model. Okay, linear regression function. What we are doing, we need to pass the x values, x and y values. So x train it. So next line, what we are doing, we are fitting the line, right? Regressor dot fit x train, y train, right? So now we have a model ready. That is the theta parameters and everything, those things are done already, and we have a linear regression model in hand. So now we can use this to predict the outputs. So see, these are the coefficients and intercept values that is being calculated from the model itself. Okay, these are the regression coefficients. So if you count the the regression coefficients are basically the values of theta that it has taken for all the iterations, and intercept is the intercept value that it has chosen. Okay, now we have this y predicted. What is the y predicted? 13 1 not aligned. What is it?
So you want to say the C is the coefficient, that is the constant, right?
Yeah, 1 second. Y pred equals predict progressor dot predict x test. Yeah, so what is the problem? Yeah, sorry, go ahead.
That coefficient is the C is the constant, right?
Yeah. So again, I told, right, like piped white is not okay. Okay, see, so coefficient is fixed for a iteration, right? But we can change it. That's what
Correct.
the whole idea is. So that's what
Yeah.
is regression coefficient. So these are the iteration values for each and every iteration. This type of values got changed. Okay, so that's why this matrix is thrown out. And intercept is 37.9. That's how. So next task will be to get you the predicted values. Okay, we will now predict the x test. I mean, predict the values using this model. Okay, so that's why. So but this is not working somehow. I'm not sure why. It was running before. I think I haven't run something. That's why. Let me run this once more. Yeah, okay. Oh, okay, not x test. Sorry, I messed it up. Sorry. Yeah, see, this regression coefficient is single value, right? The earlier why it was showing multiple values, because I ran these examples also, this multivariate examples, right? So those regression coefficients were for all the terms that we have, that I will come to later. So this regression coefficient, as you see here, returning single value, right? So this is the regression coefficient value that you have. Okay, so that's why it was not running. Okay, so this is the value for regression coefficient for the single one. I was just out of context. I was thinking that I am explaining multivariate, but this is a univariate one. So that's how it will be. Okay, so for a univariate one, it will be returning one value. That is it. This is the last value of regression coefficient. Okay, m is the intercept value. That is what is called intercept. Is m is called intercept. Okay, so that is the value of m. So now our equation be like y equals 34.33 x plus c. X is LSTAT, like that. So next, what we have done, we are seeing the y predicted values. Okay, and we have y test values. Okay, now what we can do, we can plot this also. Okay, we can plot this also. How do we plot it? We can plot it like this. Give me a few minutes. What is happening? There's no attribute ends with. What does that mean actually? Again, same error. Okay, give me a second. I will fix this. Just a second. Oh, okay. No. Why we have this ill start? Okay, 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 okay. Why train name is also coming, right? That's why it is not taking into account. So why that is coming? Okay, xtrain axis caps and xtest axis caps. Yeah, fine. So next, if I print xtest, what is happening? Okay, I'll start that first column is coming, right? So leave it. First row, leave it. Still start is coming. So what I was trying is I was trying to plot the x predict and y predict values to show you guys how good the predictions are. Okay, anyways, that is not being and that is not happening somehow. I might be doing some silly mistake. I will check and tell you. Okay, not an issue. I will check and tell you. So the let's move on for now. So
Yeah,
yeah,
can you please explain that parameters for the linear regression? What is
which parameters?
yeah, that those parameters were passing through. So is there an additional parameter we have to pass, or this is the minimum parameter we need to pass? X
These are the
copy
minimal
to.
ones. These are fine. These are fine. No, these are
First we
not
have to.
not anything. Okay, these are not anything. These don't think about it. This is the model that is being returned. Okay, these are the models that is being returned. That will always be true. So these are some of you advanced level of things. So this we can check later on only. Okay, so these are some advanced levels we can check later. No need to think of it now. So just think one thing. This is the line that we need to write. Okay, x train y train value you need to pass. Then the linear regression model will pass you this kind of a linear regression model. Okay, this equation will pass you this model. Then you can have this. So these are controlled. You can control this by passing the parameters explicitly here, but that is not advisable. You should leave it up to the machine. Otherwise, the machine performance might get might be hampered. Okay, so that's how. Okay, it will return you some intercept and coefficient values. So next step will be you can predict the values of x test and y test like that. So that's what it is. Okay, so that's how this works.
So X
Okay, so
test
that's
is
how
a
it
user
works.
defined. So X test is the user defined parameter, or it is
Yeah,
by
so
constant
this is the
variables?
trend. This is the trend test value, right? So why should it be constant? You need to pass it, right? So when we discussed yesterday that we need to split the data set into 80-20 percentage of X train, Y train, and X test, Y test. So these are the value names, right?
Okay.
Right? You got it?
Yes, yes. Thank you.
Yeah, I understand this part. Like the phase that you are going through is because you are seeing too many things that you are getting confused, right? I know that. No issues. It happens.
So basically, what we are trying to do, what is our problem here? Like, what problem statement between the two
So that's it
two?
told, right? We need to find out this MEDV value. That's what we did, right? For all this long. That's what I explained. So see here predicted value is 27.37. Here it is 28. So I was trying to plot this, but this is somehow not happening. So here it is 23.9. Here it is somewhere around 27.6. So I will plot this. You will get a clear understand. I will plot X test, Y test, and this X test and Y predicted, so that you can get a clear picture of it. Okay. Okay. So that's how is about linear regression, univariate linear regression. Okay. So now if you check the statistics of it, so that's how you check it. So from scikit-learn, you need to import the metrics package, and in the metrics we will have mean absolute error, mean squared error, and so these things we will have. So first one, see here the mean squared error that we have, root mean squared error, it is too large, right? So this is a good fit for our model. So okay, so this is a good fit for our model. So that's how these things are calculated. Okay, so that's how these things are calculated. Okay, next
No,
is linear regression.
one question. Like, see, we are plotting with between the two,
Yeah,
like LStat and MEDV, right? LStat is our X.
MEDV, right?
LStat is our X,
Yeah, yes,
independent
right,
variable, and MED is a dependent
right,
variable.
correct, right,
So based on that value, we are trying to figure out what is the corresponding value for MEDV, whether it is going up or down.
right, right. So here is the equation will be. Yeah, for multiple linear regression, again, we will have the same thing into picture. Okay. Here, instead of taking one, we will take all, and we will see how the things differ. Okay, how the things differ. We will see that now. So let me run it once more. So we are reading the data here. Okay. Next step, we are dumping the last last column, right? In the first one we are dumping the last column. Why we are dumping the last column? Because that is going to be our target variable, so we won't be having it in the train set. So we have dumped it over there. Okay, we have taken out the y variable, that is the last column, in a separate list of y, and in the x we have all the features. So x is becomes our feature vector, y is our target vector. In the next step, again 80-20 split. Okay, again we have 80-20 split. Okay, then we have we are printing the values, 80-20 split we have. Now the difference is here we have all the variables in x train and y train. Okay, we don't, I mean in x train we have all the features. In the earlier example we had only one feature, but here we have all the features. Yeah, so in x train now we have all the features now we will pass the x train and y train values, and we will run these things. Okay, we will run these things. So see here we have created a regression line. Again, as a similar way, we have taken the regression coefficients, and we have taken the regression coefficients. Here we have multiple columns, so multiple regression coefficient will be there, and we have the column names also. So that's what we have taken. So 12 columns, 12 multiple regression coefficients will be there. So these are the theta vectors. Okay, these are the theta 0, theta 1, theta 2, theta 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, these are the theta vectors here. So if you see, there are some negative weights also, so that means these are insignificant. So they are I mean for those the values got I mean what, for larger value of those the value got decreased. So that's why we have a huge negative parameter for those. Like let's say for 4 NOx, for this NOx, what is NOx? If you see here, nitric oxides concentration parts per 10 million, so that is toxic, right? So if the value is more, the housing price will go down. So that's why it has a huge negative parameter. Okay, so that's how in the real world machine learning models work. I will start with logistic regression session. Okay, so one thing to understand, first thing is regarding machine learning, right? So broadly there are two types, like supervised learning and unsupervised learning, right? So for supervised learning we will always have a definite objective. It can be something a continuous set of variables or can be categorical variables. Okay, and for like unsupervised learning algorithms, we will always be having a indefinite output, let's say cluster of points kind of things. Okay, that will be I mean, for supervised algorithm, whatever data we use, it will consist of a level. It can be a continuous set of variables or it can be categorical, that doesn't matter. Okay, so it will always be the data will be definitive. It will give you some kind of a output. Now if so why do we need this kind of a different set of algorithms, right? When we are dealing with linear regression, why don't we have, or why do we have this logistic regression, which is a classification algorithm? So the thing that you need to understand, for linear regression, if the data is continuous and spread across a good amount of range, then only the line can help you in predicting the values, right? But instead, if it's a categorical problem, like where the data is skewed in two ends or two three ends, like let's say values of 0 and 1 are the best scenarios that we have. So typical examples of logistic regression would include, typical examples would include like uh, tumor prediction, is it a malignant or benign one? Okay, it would be spam classifier, it will be fraudulent transaction detection. All those kind of things will come under logistic regression. So as you can understand from the name itself, here the data will be too skewed, right? It will either have a yes or no value, or you can say it like 0 and 1. So if you have, let's say, 10,000 data points skewed between 0 and 1, there cannot be anything which sits in mid of it, right? It cannot sit between 0 and 1, right? So it should be at the two fag ends. So if you draw a line from two ends, what would do, that would be horrendous for a linear regression model to fit in, right? So why so? I Unweighted decision tree is something else and the logistic regression is something else. So it's those two are different, the different things. So don't just confuse the algorithms. Okay, so when I am going with one algorithm, stick to that. If there are any relations between them, I will also cover that, which is sadly there are nothing. Anyways, so to continue with it, for this kind of logistic regression problems, the data will be skewed between 2 points, right? So if we draw a line between point 1 to point 2, if it's a straight line, then also it won't fit the data. When I am telling this, what do I mean? I will shortly show you that. Okay, so what do I mean with that? The data will be skewed and the line can't fit it, right? So let me open this. Okay, when I say that the it cannot fit the data, right? We saw for linear regression how the models worked, right, and how the data points look like. But let's say what we are talking about today is, it will be some kind of a graph like this. If you plot the observations, right, then I mean when you plot the outputs in a graph, in yesterday also we did the same thing and we saw there was a continuous set of variables. But here what it will do, yeah, so it will be, let's say these are some data points which will be near 0, right? These will be some data points. So the output of this will always stack to 0 and output of all this will be stacked to ones. Like that, this kind of a set will be there. So if you draw a straight line, it would only fit 1. It can fit max of 2 values. It can fit max of 3 values, like that, right? So in that case, what would happen? The model will fail radically because the error percentage will be huge, right? And it won't be fitting a good model. So that's why we won't be able to use linear set of regression, linear set of models to fit in this kind of a requirement. Instead, we would need this kind of a curve, right? See, now this fits in perfectly, right? This fits in perfectly in the under training example. So this curve is again called, sigmoid function, right? This x-shaped curve, S-shaped curve. So what is the features of it? It is an asymptotic curve, right? When do we say asymptotic? That means it will never reach 1, it will never reach 0. Okay, so what it will do at positive infinity, at positive infinity, it will asymptote to 1. At negative infinity, it will asymptote to 0. Okay, so it will never match the lines, but it will be asymptotic. So in this kind of shapes, we can have some kind of a good fit for this kind of classification problem. Yesterday's thing was based on a straight line equation, right? It was a y equals mx plus c. This kind of a straight line equation was yesterday's topic of discussion. But today's topic of discussion will be this kind of a asymptotic curve. Okay. So before going to this, I will be covering one more. Okay, I will come to that later. So this curve equation is this 1 by 1 plus e to the power minus x. So this curve, as you see, it will asymptote at the positive and negative infinities, right? So if you see e to the power minus x, then if you set the value of x as minus infinity, what would happen? A very large number will come at the denominator part, which will force this value to go to 0, but it won't be 0. But as you know, infinity is a big number, so infinity plus everything will be infinity itself, right? So it will be very near equals 0. But if it is positive infinity, then e to the power minus negative infinity will be too small to be considered as 0, right? So this value will asymptote to 1. So that's how the sigmoid function works. And we will establish our logistic regression functions and everything based on this function itself. Okay, this function itself. So now what I will do, I will go to the PPT and will cover the things that are there. Okay, then I will again come back to the curves and all. So this is how the basic concepts of logistic regression stands. So this is how this sigmoid function comes into picture instead of a linear regression line. Okay, so I explained the basics of it. Now let's see with an example. Okay, so someone is asking you to, hey, see, I want to buy a property which will have a bigger garden area for some amount of money. Okay, so what we will do, we will do a simple linear regression, right? So what we will do, we will have the dependent variable as property size. So we will have an independent variable of money. So it's obvious, right? If you want bigger garden area, that means your property size has to be bigger, right? So you need to spend more money than before, right? So again, it has many other many other criteria, but let's have this fixed. Okay, let's say the locality is fixed, the area is fixed, that the village or the town or the city is fixed where they're trying to find the house. So if you consider there are only two external variables, that is money and dependent property size and money, then in that case what we will have is we will have a linear equation between these two, right? So there linear regression will perfectly fit in. Yes, Giri, so that's what I told. So property size, so that's how it is. So next point will be, so bigger garden area means there will be smaller house area. So we are I mean, what we are doing here, we could have taken a multivariate solution here, but we are going for a small part. So we are breaking it into chunks. Okay, so when we are searching for bigger garden area, what does that mean? That means the house area will be smaller, right? So in a property, if a house is there, let's say we want to buy 1,000 square feet of 2,000 square feet of property. In that garden area we want of 900 square feet, so the house area will be shrunk to 1,100, right? So that's how. So here also a linear equation exists between them. Why? Because if you make the garden area large, the house area will come down, right? So house area and garden area size will also have a linear kind of equation. This can be solved using linear regression. So this kind of problems can be solved using linear regression, because this is not categorical. The data will be continuous. So the value, the size values or the price values, when you plot it, it will be, so it will be linearly dependent between them, and as it is a continuous value, so linear line will fit it. There might be errors, there might be estimation errors and all, that's fine, but it will fit a linear model, so we can predict those kind of things using linear regression. So what we can say from this, like if the guy who is asking you for buying a house, if he spends X amount of a money, he can buy Y area of a house. Okay, Y property area he can buy. So this one you can comment from linear regression. But let's say the guy wants to ask you, so the property will have a good neighborhood, will the location be noiseless suburb or a busy bustling city, So how the properties, what is the location of the property, that kind of preferences someone wants to ask you, then you will be in a soup. So see this problem statement, will the property have a good neighborhood or not? What the values it will have? It will have a categorical value 0 1, right? So again, if you plot here, if you plot those 0 1 things here, like I saw, like I described in the plot before, it will be skewed in 2 points. So if I draw a linear line, it will feel radically, right? You can't predict it. So if I go back to my plot, let's say we are trying to deal categorical problems using a linear regression model. So I will draw it again. Okay, so let's say these are a few values. Okay, these are zeros, these are one. So I have a data set where this neighborhood is also given, and neighborhood is given as like good neighborhood or bad neighborhood. So this is good, this is bad, this is bad. Now let's say I draw this line. Okay, so now let's say some property is bad. So but what it will do, let's say we want to know if the property has this kind of a value, then what is it? So it will predict the values in here, the y value will predict in here. So will be this one will be your value. So what can you comment on this? So the value coming will be around 0.3 or something. So there will be a lot of error, but it should have been coming as 0. It will get worse till you once you move to the top of the line. So it depends on the line that you draw actually. So come on, why it is not going? Yeah, so let's say some point here for x here, the value will be coming up here, right? So this will again go to a good property, but there it should have been a bad property. So this kind of problems won't be, you won't be able to solve using linear regression models. Okay, this kind of problems you won't be able to solve using linear regression models. So in this case you need that funky S-shaped curve, the sigmoid function curve that we shown here. Okay, so that's the whole idea. So now we will see how we can have it. Okay, so this kind of a classification problem linear regression won't be able to answer. So you would need to apply logistic regression models to this, and this will help you in answering classification problems. So this is the never ending loop that it will go on. Okay, so will the property have a good neighborhood? Will it rain tomorrow or not? Is the mail spam or not? This kind of small questions, this kind of small classification questions it can answer. Okay, so let's go ahead with this PPT. Okay, so see, machine learning, supervised, unsupervised. Supervised is again divided into two broader categories: regression, classification. Regression we already covered, linear regression. Today we are going to cover logistic regression. That's another classification problem. There are many others. We will come to those one by one, but these are some major chunks. Okay, so a statistical classification model, as you already know, this machine learning, heart of machine learning is stats. Next is deal with categorical dependent variables. Explain this. Could be binary or dichotomous. So that means it should be having two values, not more than two. It could be multinomial. Yes, obviously it can have only one feature of x. It can have multiple features x, right? So yesterday we saw how it does for univariate and multivariate machine learning linear regression models, right? Same thing applies for logistic regression models also. So x can be only one feature or x can be a set of features. So that's where that way it can be either multinomial or it can be univariate. Okay, it can take both continuous and discrete input data. Yes, because this kind of a S-shaped curve can also fit continuous data also, but again in that case it will have a lot of errors, right? So continuous variable, if you plot using a S-shaped curve, it will be giving you some model, but the error will too high to explain. Okay, so that's why we don't really specify it. So we only consider of this categorical data. Okay, for continuous variable also you can plot this, but it won't be helpful because it will be having some problems, right? Because it won't be able to take care of continuous variables. Okay, so that's why we have linear regression models. Yes, sure. So for multinomial, it is like, let's say we are trying to find what should we find? Spam classifier. Let's go ahead with the example that we have. Okay, so for spam classifier, if we think there is only one feature to be, that is count of spam words, right? If we think this is our only feature, so what do we mean by spam words? It will be misspelled words, right? It should have bought like this. It should have sell, buy, money, transfer, bank details. This kind of words are very commonly noticed in spam classifier, right? So if we want to build a spam classifier using only count of spam words thing, right? Only count of spam words thing, then it will be univariate. Now, if you have noticed spam emails, it has one more feature also. Like for spam emails, the sender address will be fishy. The sender address will be fishy. What do we mean by fishy? The domain name will have some absurd kind of a values. It might not be a permanent domain, right? So if we take that also in account for building a spam classifier, it becomes multinomial. Why multinomial? Because okay, let's so why multinomial? Because we know we denote feature vector by x, right? So if x contains only one value of x1, then this is univariate, okay? Because the number of independent variables in here is only one independent, right? So whatever has to change will change with the value of x1 only. But if x contains more than one, that is x1, x2, xn, so it might happen that among these n features, all n features are useful. It can happen, or it can happen some, let's say 10 features are useful, okay? Others might be junks, but it has 10 features, so 10 independent variables, right? So as we have 10 independent variables, what it does, it will have like 10 layers of x versus, so it will have a 10 independent variables. So the y value that we are going to predict will have multiple features in it, right? Will have multiple features in it. So we need to fit in more than one feature vector in our machine learning equation. So if I go back to this equation, like we see here, this is the equation for linear regression, right? So if we have something like this, 1 plus a to the power minus, I will come to the derivative, I mean machine learning form later. Like this, if we have, then it becomes a multivariate problem. This is a univariate problem, okay? So that is how it depends, because here it output of the model will depend on more than one independent variables. So that's why this is called multinomial, okay? So that's what the idea is. That's what is about multinomial and univariate things. So here also we can predict, here also we can have this kind of we can use clustering algorithm to predict the data, okay? We can use this kind of algorithm to predict the data, okay? So for clustering, what happens, as a point came in, I will show you. For clustering, divide data in unique sets, right? So that is what is called clustering. So the sets can be 0 1 also, the set can be cat, dog, fish also, right? So the both type of problems can be solved using clustering, but for classification it won't fit this purpose, right? That is the whole base of our statistics. So for clustering we will have a different set of algorithms there. If you see, there no kind of a machine learning model will be there. There will be a generic set of steps that we need to follow. Stats will be there, but it will be in the minimalistic part, okay? So that's how it works. Okay, let's go ahead. So this is a tool for applied statistics for discrete data analysis. You already discussed. Gives outcome in terms of probability, right? That's what it does, right? So what the model will do, the model will give you a probabilistic output. Like let's say for this email to be spam, the chances are 70%. We will convert that to 1. We will see this, okay? So this is again based on probabilistic models only, okay? So this logistic regression will be, the probability will play a big role here, because see, one thing you need to understand, when we are going for logistic regression problems, yes, this the equation that I have shown, this will be the curve equation that we have. That's true, that's not a problem. But the thing is, when you are predicting the output, so what this value will predict, this 1 by 1 plus a to the power minus x, it will never predict 0 or 1. Perfect 0 1 1 it would never predict, right? Because it is an asymptotic function. So at and infinite values you won't be giving to the function, then the function will stack, the function will be looped in for forever, right? So it will output some values from 0 to 1. So that will be the probability of that problem. Let's say the email probability of probability of email being spam, right? So this kind of outputs it will give. So when it gives greater than equals 0.5, we can consider this to be 1, less than 0.5, we can consider it to be 0. That's how the math tells us. So this is again, this kind of things will predict the probability of the event being happening. So probability theory also will play a big role here. Okay, so that's how this works. Okay, now let's go ahead and take an example of it. So see, spam email classifier example we have. After this example is done, we will go to the maths of it, right? So this is how it is. So this is how the spam classifier we will build. Okay, so there are a series of steps for every machine learning problem. Okay, so understanding the variable, this is always needed. This is always needed, right? Analyzing the variable that I am telling from the first class. To be a good machine learning engineer, you have to do this. Then the stats knowledge will come handy as hell. Okay, so for basic simple problems, you won't be building complex models. The simple linear model will fit in. But when you go for a few advanced field, like researching on this kind of things and all, for building face recognition and all, you will see how complex the stats can get there. Okay, draw regression curve. So if you, whatever model you are doing, if it has a definitive curve, so just draw it. Okay, just draw the data points in it and just try to fit in a line. Let's see how the data looks like, how the model looks like. Does a linear model fits it? Does a logistic model fits it? Or it's nothing, there is no relation, it is a clustering problem. So then this case we need to check always for all machine learning problems. Next is find out best fitted curve using maximum likelihood estimator. So this is basically log estimator. Okay, so this is we find out log of odds to predict the value. That is what is maximum likelihood estimator. So maths behind it, it is a bit complex, so I won't go to that. So just take my words for it. If you want to go through it, you can check it. So maximum likelihood estimator, as the name suggests, it has likelihood, this name, right? So what is a likelihood of an event? I will tell you just a short story. So we all know, right? There are two terms with probability theories, odds and events, right? What are odds? Odds is the chance of event happening, right? That is what we call as odds, right? So when we say that, that means what is the chance of the event being happening divided by chance of event not happening, right? That is what is probability theory. That is what is maximum likelihood, or that is what is odds is called. Okay, that is what odds is called. So this thing, this maximum likelihood estimator is entirely based on that. Okay, so we take log of it to uh, to minimize the impact. So we will see why we take log, we will see later. Okay, for logistic regression, why we take log, we will see that. Okay, for now just think that it is log of this kind of an equation, log of probability of odds. Okay, that's what we take. So that's how maximum likelihood estimator itself uses the log because of that reason only, and that's why we use it. Okay, we will see. Okay, so I will go ahead with the example step by step. So if we see, we have independent variable, we are taking univariate one because solving it manually will be a hectic part. So we will take univariate logistic regression here. So we have count of spam words. Okay, that's what is our independent variable, as I told. So most common spam words will be buy, get paid, guarantee, winner, unlimited, those kind of things, right? If you see, buy this watch for rupees 1, buy this thing for rupees 2, get this thing free, give me your shipping address, like this kind of mails are always spams, right? So that's why we have defined this kind of a most common spam words. So we will restrict our search to this kind of words. Okay, this kind of spam words, we will take some arbitrary counts and let's see how it works. Okay, so now we will have dependent variable, that is probability of mail being spam. So that will be binary or dichotomous, right? So that means it will have either 1 or 0 value, right? It will either be a not spam or it will be a spam. So we are taking some estimates. Okay, we are taking some estimates. Our estimate is, if the value is greater than 4, then it will be a spam. If it's not greater than, less than, if it's greater than or equals 5, it will be a spam, otherwise it will be a not spam, right? So this zone is safe, this zone is red. Okay, now what we will do, we will take 10, 13, 8, 9 mails where, so for the first one we have 2 spam words. So the probability will be 0. This is our label data that we are preparing. This is the label data that we are preparing. So in the real world, you will get this data. So you don't need to prepare this, but here, as we are doing manually, we are preparing this. That I will show you also. That kind of data we have it. Okay. So we have 6 words and the mail is spam. We have 8 words and the mail is spam. 1 word, it's not a spam. 7 words, it is a spam. 3 words is not a spam. 9 words is a spam. 8 words, still it is not a spam. It can be some definitive mails, right? Let's say we are trying to buy a laptop or something. It will be having all those kind of set of words. Buy, it can have in 8 places. So it is not a spam. We can have it, right? We can have it. So that's how our label data looks like. Okay. Now we will plot this. So how we will plot? We will plot this probability of the mail being spam in the y-axis and count of words in the x-axis. Okay. Count of y will be in the x-axis, right? So how the graph will look like? The graph will look like something like this. Okay. So let's say for 1 word the mail is not a spam. Okay. Say 2 words, mail is not a spam. 3 words, mail is not a spam. So we all have y values to be fixed at 0, right? Based on output 0 and 1 and based on the count. So that's why we have this kind of a graph. Okay. We have 8 words, but the mail is still not a spam, right? So we have here. Okay. But here, if you see for value for 3 words, we have a spam. So it is here. For 5, we have a spam. 7, we have a spam. 8 and 9, we have a spam. And 9, we have a spam, right? So we have plotted this line. Now we will draw the regression line. So as you know, this will be, so we will plot this line, right? So why is it blue there? Anyways, leave it. So we will draw this regression curve to see. Okay. So these are kind of outliers to your data. So this has 8 words, but still, yeah, correct. It is outliers, Ravi. So it has 8 words, but still it is not a spam. Okay. So we have fitted this curve in here. Okay. Now next thing is we will draw this log of odds. Okay. Log of the line being spam or not. So we will get this line. Okay. If we plot this line log of odds, we will get this line. How do we get this line? We calculate log of odds of this mail being spam, this mail being spam, like that, and we come up with this line. So this is the line for log of odds. Okay. That is how we draw this line. Now next will be, we have this sigmoid function, we have this log of odds. Okay. So now the next thing that we are gonna do, so that's what we have. We have this log of odds. Now we will have a spam classifier. We will have some kind of a sigmoid function here, right? We will draw some kind of a sigmoid function here, right? So next thing is we will find out individual likelihood of everyone, okay, which will be log of likelihood, right? So we will figure out individual mails probability of being a spam or not. We will figure out that log likelihood. Then we will draw the line in the curve. In the next section, if you see, we will draw the, come on, where it went. Okay, we will draw the log of odds line. Okay, so this is the regression line that we have, logistic regression line that we have, and then we will draw the log of odds line in this case when we are going for maximum likelihood. Okay, so what does log of odd means? I already explained. Still, let's see some examples. Okay, so here, let's say this guy fishing 5 times a week, caught a fish 2 times, failed to catch 3 times. What is the probability and odds of getting a fish for dinner? So probability of getting a fish is 2 by 5, right? The probability of getting a fish is 2 by 5, right? Probability of not getting a fish is like 3 by 5, right? For not getting a fish. So probability, so odds is chances for it. So chances that the guy will catch a fish is 2, and the chances that the guy doesn't catch a fish is 3. So odd for that event being happening is 2 by 3, right? Odd for the event that will happen is 2 by 3. So that's how we have for bettings, right? That's a good example. Betting is a good example of this logistic regression, but I am not encouraging to bet as this is illegal. Okay, so here it is just for an example. So we have odds for every team winning or not, right? So how they do it? We do it using the team chances for being for winning and team chances for not winning. Okay, so that's how. Yeah, so log of odds is will be called the logit function. Okay, so odds and odds ratio we will have. Okay, So probable odds of catching a fish on sunny day is 2/3, and odds of catching on a rainy day is 3/2. That's what is some arbitrary numbers. So log of odds will be log of 2/3, and log of odds of catching a fish on rainy day will be 3/2, because you can really understand, right? So if the day is rainy, then it is a higher chance that we will get the fish. Why? The number of fishermen will be lesser there, right? So now odds ratio will be odds of getting a fish in a rainy day divided by odds of getting a fish on the sunny day. So which will come as log of 0.44, which will yield you some kind of a value. So that's what is about log of odds and log of odds ratio. Okay. So odd means chances for divided by chances against. So what is the chance of some team winning the match divided by what is the chances for that team not winning the match. So when a black horse wins the match, the guys who are doing a betting will be like showering in the money. But when it happens the reverse, the guys will lose all their money, right? That's what happens. So that's how this thing stands for. Okay, that's how this odds thing stands for. So that's how it works. So the higher the odd is, the higher the chances for winning or losing is, right? So that's what it is based on. Okay, that's what it is based on. So now we will see how can we use that in here. Okay, so see the logs or log of odds line we have drawn. Okay, it will be this represents log of odds for every mail being spam divided by chances for the mail not to be spam. Okay, so this measure will be arbitrary. We will for this curve, this is arbitrary, but this can be equally predicted, right? You can easily understand that. So that's how we plotted this log of odds line. When we go to the maths part, you will understand this better. Now let's say log of odds or log of odds will be what? Log of us mail being probability of mail being spam divided by probability of mail not being spam, right? So let's say if a mail is spam, so p of spam will come to 0, and 1 minus p of spam will be 0. So 0 by 0, what it would be? Log of 0 will be, okay, yeah, log of 0 by 0, right? This kind of things will be there, and it will asymptote at negative infinity. The log of adds value or odds value will asymptote at negative infinity, so it will be negative value. So we will consider negative values as 0 only, so we will take it as 0. So that mail is not a spam, because log of 0 by 1 will be log 0 minus log 1, right? From the logs equation we have, and that will be negative infinity, because log 1 is negative infinity, right? That's how, I mean, log 1 is infinity, right? But log 0 is 1, right? So here if you see log of 1 by 0, then it will be a positive infinity. So if the value is positive, then it will be trending to positive infinity, right? So if some mail is a spam mail, for this mail the value will be nearing to positive infinity. That's how this log will work, right? So that's how this log likelihood comes into picture. Now you need to understand one more thing. Let's say our model is predicting this value to be false. Okay, so but the value is true, right? So the value is true, but our model is predicting it to be wrong. So we will use later on, we will use this concept of log of odds to build our cost function. How we will tweak it? We will tweak it like, if our value that it is the model is predicting is correct, that is if the value is 0 and our model is predicting 0, then we will give it a no penalty. It will be a 0 penalty. Okay, but if it is otherwise, then we will give it a high penalty. We will use this concept to build on that. Okay, so that's what will be the function of concept of cost function. Let me show you. This equation is a bit hard to write, so that's why I have it in my PPT. So this one, right? This one will be the cost function for logistic regression. Okay, so this is how this will be. Let me write it also, no issues. So we have j of theta will be 1 by m, okay, summation over I equals 1 to m yi into log of h theta x, right? Log of h theta x. Okay, so why so? I will explain. H theta xi actually, plus or minus, what we have, plus, in plus only we will be having, yeah, right? So we will have 1 minus yi into log of 1 minus h theta x. Okay, so this h theta x is our, what is this called? This is our hypothesis, right? So h theta x our hypothesis, right? So what hypothesis will return? It will return the prediction. So now just pause for a moment and check if this equation makes you sense or not. Okay, so what we have, just try and see. We have 1 by m summation I equals 1 to m. I will break down into parts. Okay, I will break down into two parts, minus minus. Okay, okay, sorry, I wrote it a bit wrong. It will be a minus up here. Okay, it will be minus 1 by m. Why I am coming to it? Why do we use this cost function for logistic regression? Come into it. So the first part of the value is yi into log of h theta xi. So what is this? This is our prediction, right? So log of our prediction, it can be either 0 or 1, right? Let's say we are taking for 0. Okay, and let's say yi value is also 0. Okay, so this first term will vanish, right? If yi is 0, h theta xi is also 0, the first term will vanish to 0. For the second term, if you go, yi is 0, so 1 minus 0 into log of 1. What is this log 1? Log 1 is 0, right? So we will have 0. So if the prediction is correct, okay, if the prediction is correct, that is yi is 0, h theta x is also 0, that is a true prediction, cost function becomes what? 0. So no penalties. We are encouraging our model to use that because it has done the same prediction. If you substitute the values for 1 also, if it is for 1, then also it will be turned to 0. Okay, why it will turn to 0? For yi equals 1, the second part of the function will be removed. Okay, the second part of the function, that is this part, will be vanished because this is 1 minus yi, and if the yi value is already 1, this function will vanish, and this will yield you the result of, and our model has predicted it correctly, so it will yield you the result of log of h theta xi, that is log of 1, that will go to 0. So we are encouraging our function to use this because if it is a true prediction, okay, if it is a true prediction, the cost function becomes 0. No costs are implied on the function, no costs are implied on the model, so we are encouraging our machine, go ahead, use that model. Okay, but let's say we have a reverse case of scenario. We have yi to be 1 but 0, but our h theta x we have predicted to be 1. So for 0, first term will vanish, it will be 0, plus for the second term what we will have? We have 1 minus yi, so 1 minus 0 into log of what we have? We have 1 minus log, what was that? Log of 1 minus, sorry, I just reverse it. Yeah, so what we have? We have log of 1 minus h theta xi. So this is now 1, but this was supposed to be 0. So 1 into log of 1 minus 1 becomes 0. What is it? Positive infinity, right? We are and as we have minus 1 by m at the front, this will become negative infinity. So we are discouraging our model with this kind of a cost. We are telling, see dear, don't use it because it will yield you a high cost, that is of minus infinity. Okay, similarly, if yi is 1 and our model has predicted 0, then also if you put in the equation, you will see there is a huge cost of negative infinity to the model. Okay, so that's why we use this log of odds concept to use it here. Okay, to use it here. Okay, to build the cost function for logistic regression, and this whole concept that I explained is the cost function of logistic regression. So if our model is correct and makes a prediction to be prediction is correct, the the cost function will be 0. If it is wrong, then it will become negative infinity, which will yield you a very high value, high cost value to the function, and that will be dangerous for the model. So the model will try to readjust its theta parameters to find out a nice and healthy equation to fit the curve. Okay, so that's how cost function works. So as we're going through this log of odds thing, just explain this. Later on, we will see the equation for logistic regression also. Okay, so that's why this negative infinity concept comes into picture. Okay, yeah. So that's how we have for cost function. Let's go ahead with this log of odd thing. Now see, we have plotted this log of odds line, which will be negative infinity to positive infinity. It will stretch out. Then we will calculate the distance from the log line and this male classifier points. Okay, we will calculate this error points, right? The distance of errors from each and every point to the log of odds line. Okay, so we will have a sigmoid function. Now here, so here what we will do is we will see what is this sigmoid function and how do we use it here. Okay, so if you see the upper hand of it, L of e to the power k x minus xo by 1 plus e to the power k x minus xo, this is the logistic function in stats. Okay, so this is the logistic regression function that we have in stat. Now L will be curve's maximum value, K will be stiffness, and x0 will be x value at sigmoid point. So x value at sigmoid point will be 0, right? Will be 0. So sigmoid point for a function will be 0.5, right? Which will be a 0 value for the sigmoid function, not the predictions. Okay, not the predictions like that. So we will replace these values. For us, the maximum value that we are going to use is 1, right? We are going to use is 1 for the ideal scenario, and stiffness will also be 1. So we will replace the values in that earlier equation, 1 e to the power k x minus xo by 1 plus e to the power k x minus xo. What it would become, L will be 1, xo will be 0, and so we will have L e to the power x divided by 1 plus e to the power x, which is same as this equation, right? Which is same as this equation that I wrote earlier, this equation, right? So it will translate to e to the power x by 1 plus e to the power x. So this is the equation that we are going to use for now. Okay, it has two forms. I will use the first form for ease of use. Okay, I will use the first form for ease of use. So anyways, you can write it, that's not a problem. So that's how we will have this e to the power x by 1 plus e to the power x, this sigmoid function we will be working with. If we so this thing I already have discussed, right? It will be a S-shaped curve. It will have a finite limit. It will be 0 as x approaches negative infinity. It will asymptote at 1 if it approaches positive infinity, right? So that's how this thing works. That's how this thing works. So what we will do, how we will map with this number, take any real valued number and maps it to a value between 0 and 1, right? It should be x, whatever value of x you give in this value, right? So let's say e to the power 8. Okay, let me show you in a calculator also. So if we use e to the power 8, it will be 2980. If we divide this with 1 plus e to the power 8, then it would be say 0.9999, which is almost equal to 1, right? So if you give any real world number to the sigmoid function, it will yield you a value between 0 and 1. Okay, so that's why we use this sigmoid function, because it will map you to some value between 0 and 1, and based on the 0 and based on the output value, we can relate that to either 0 or 1. Okay, this will be so we will get the classification thing done very easily. So that's what is the main reason for using this kind of a sigmoid function for logistic regression. So there are two things. So first, whatever values of x you give, it can be continuous or categorical, but it will give you a value of 0 and 1. Second, linear regression can't fit this kind of a curve, because it won't always predict 0 and 1, right? It will predict a continuous set of data. So that's why we use linear regression in here. It is in the other words, in the other words, this is how the sigmoid function works. That's where the power of sigmoid function comes into picture. Okay, that's why in classification problem we use sigmoid functions. Okay, so next step, we have drawn the sigmoid function here. but this is probability as we discussed. So e to the power x here will be log of odds. Because why log of odds? Because we want to see what is the error in it. So that's why for instead of x we have put in log of odds. Okay, log of odds. So as I told, it will map it to a value between 0 and 1, right? So we can say either the mail is a spam or the mail is not a spam, right? So for the first, if you say for this example, we have 3. Okay, we have 3, right? Log of odds for this example will be minus 3.2. That's an arbitrary value, don't think of it. Okay, so let's say for this mail to be spam, we have a log of odds value to be 3.2. This mail being spam, log of odds is 3.2. If we substitute, this will be 0.03, right? So what will happen for this 0.03? This model will fail, right? Because 0.03 equals to 0. So some spam mails, we are calculating it as a non-spam, right? So our model will fail. Our model will fail. So see here, we have a wrong prediction. So this log of odds line that we have drawn is not correct, right? So the theta parameters need to be adjusted now. Okay, so we need to rotate the log of odds line now. Okay, see for this one, for this mail to be spam or not, it still predicts this mail. Actually it still predicts correctly. So it is correct, but this one is a wrong prediction. So we would need to give it a shot, and we would need to try. And so the steps will be, first we need to calculate log of odds for each and individual values. Okay, each individual mail values. So whatever values we get, and we can really easily understand that this value is not going somewhere, this value is getting reversed. So we are having too many bad predictions. So first we will calculate log of likelihood for each of the mail being spam. So as I explained in the example, it is failing radically, right? It is failing radically, and the spam mails are translated to being not a spam, right? So next will be, we will calculate this kind of a likelihood function. Okay, so why this kind of a likelihood function? Because for the first mail, when we have the 0.01, that is the probability of the mail not being spam, right? That's what we have calculated for the first email, because it predicted wrongly, right? So we will subtract this from 1, and rest we will multiply. So that's how we get total value, and then we put a log on it. Okay, we put a log on it to find out log of likelihood of the entire data set. Okay, of the entire data set that we are working on. So we will calculate all these log values, we will sum it up, and we will see the log of odds value is 0. minus 0.084. So that means this is not a good fit, because we have a very really small value that is coming into picture. So this is not a good fit of the model. Okay, next we will rotate the line to find the best fit. So when we rotate the line, we will take each individual examples in there, we will calculate their individual likelihood for each email being spam or not spam. We will keep on rotating the line till we find the best fit. Okay, that's how the algorithm will work. We will keep on rotating the line till we get the maximum log of log of maximum likelihood. Okay, so that's how we will do. So that's why that's how we will do this. That's how we will find out the logistic regression outputs. That's how we will find out the best fit line. Okay, so that's how this thing will work. Okay, so that's what is sums up this example. Now let's see how the cost function, I mean how the logistic regression function looks like. So as you have already seen, right? Yeah, so logistic function, right? What do we have? We have a to the power x 1 plus a to the power x, which again translates to 1 by 1 plus a to the power minus x. Now guys, now my question to you would be, how do we apply the theta parameters, like the weighted average to it, right? So for linear regression, we have seen that we have applied some weight to the theta parameters. Here also we will have the same thing. How do we have it? This is the equation that we use for machine learning. Okay, this is the equation that we use for machine learning. So here this x is feature vector, this theta t is theta vector, let's call it. Okay, y transpose here, because theta will be a vector of theta 0, theta 1, dot dot dot, theta n, right? Theta will be the vector like this, right? And x, the feature vector, will also be like this. So x0, x1 till xn, right? So in order to apply these two together, we would transpose theta. So how the theta transpose will look like? The theta transpose will look like this, theta n, correct? So now if we calculate theta transpose x, it would become theta 0, theta 1, theta n multiplied by x0, x1, xn. What is the output, guys, for this? Theta 0, x0, theta 1, x1, theta 2, x2, like this, right? Till theta n, xn. Here always we have x0 to be 1, which would make this equation to be tan xn. Okay, this will be the equation for this. Now if we substitute this equation in this equation, 1 plus e to the power minus theta o, theta 1 x1, theta 2 x2 plus dot 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 theta n xn. Okay, that's how this equation will become. Now if you go back to the cost function objective, so if we have yi to be 0 and this model has also predicted to be 0, so h theta of x will predict 0, so the cost function will be 0. So the theta parameter values that we have chosen will be correct. But let's say yi is 1 but h theta x becomes 0, so it based on these theta values, right? So if I go back to the cost function, you will see when we have log of h theta x, that will be in terms of theta, right? So here how the original equation will look like, it will be yi into, again you no need to do this, okay? I am just explaining for your ease of understanding. 1 by 1 plus e to the power theta transpose x minus, right? So that's how you will put these values, right? So this equation will yield 0 for correct prediction, so this theta values can be unchanged, theta can be unchanged. But if it's negative incorrect prediction, it will be a high value, right? So negative infinity means a big penalty, right? So this will enforce the model to change theta. Yes, Rabi, this is the hypothesis is h theta x will be 1 by 1 plus a to the power theta transpose x. This is the hypothesis for logistic regression machine learning model. Okay, this will be the hypothesis. So theta transpose x calculation I have shown. How we can put this into this value I have shown. So that's what is the concept of theoretical mathematical concept of hypothesis and of logistic regression looks like. Okay, that's what is about the concept of logistic regression looks like. Okay, so the next thing that we will do is we will check the demo of logistic regression. Okay, after this I won't be showing you the entire thing, I will just show you the basics of it. Okay, so I will just touch the basics of it because you will rarely do it manually, but just for showing you how this mail classifier or some other example can work with this, I will just show you. So we have this kind of a data set foo, where are something with 1, 2, 4, 5 values. So then we will plot the lines between A and B. So why this kind of lines are given? Yeah, till here it is starting. Okay. So see what we are doing. We are creating a logistic regression function. Okay. We are taking rho, that is the feature vector, and coefficients, that is theta. Okay, so y hat we are taking as coefficients 0. Okay, y hat means the first prediction. Okay, now for all the features we are calculating this y hat plus equals coefficients I plus 1 star rho 1. Okay, so then we are substituting this value. Okay, because this is theta transpose x into x, right? This line we are calculating theta transpose x, right? So theta 0 plus theta 1 x1, theta 2 x2, theta 3 x3, like that we are calculating here in this line, right? This is the y hat, that is the theta 0. Okay, this is the theta 0. Now we are returning this function, right? 1 by 1 plus e to the power minus theta transpose x. So we have theta transpose x in y hat, so e to the power minus y hat. Okay, we are returning this function, so this is our predictor function. Okay, now we are, anyway, so this is our theta transpose x. Now we are creating a trained data set. See, we have some arbitrary values with label data set, right? We have two features in here. So we will estimate the coefficient using stochastic gradient descent. No need to go into details, this would be not be needed. So stochastic gradient descent, when we say, okay, let me tell you one more thing. It will be asked frequently in interviews, why can't we use maximum, like a mean squared error in logistic regression? Okay, good point came in. I will explain this. Yesterday I have told you a concept of gradient descent, right? So gradient descent will be when you are trying to find out the minimum value, when you are trying to minimize some value, you will use contour plots. That is the gradient descent algorithm. So you will step down the curve according to the gradient of the curve. So let's say, do I have it in my PPT? Just let me check. If I have this curve, then it will save a lot of drawing efforts. Let me see. 1 second. No, I don't have it. Okay, I will just quickly draw this. Okay, so the cost function that we have for linear regression is mean squared error, right? So for categorical data, for this kind of a data where the values are categorical, if you draw that cost function, then it will yield some kind of a curve like this. Okay, this kind of a zigzag curve you will get. Okay, for the mean squared error function, why you will get? Because our hypothesis is 1 by 1 plus e to the power theta transpose x, right? So if we try to find out mean squared error, as we don't have a continuous set of value, the mean will always be in between 0 and 1. So it will it will always be shifting in between 0 and 1. It will never yield you a positive value. That's why you will some kind of get this kind of a zigzag curve. Now let's say you want to use gradient descent in this. So you are in this point. Okay, you want to find the minimum value. We can see this is the minimum value, right? So now gradient descent, it will descend, it will change the theta value, it will come to this point, it will come to this point, then it will start descending, it will come to this point. So this point, if you see, okay, let me take from this point. 1 second, this is a very short line. Let's say you are at the starting point here. Okay, so here if you see the value, it will see the value is not minimum. Okay, so it will change the theta, it will change theta, it will come down, it will come down to this point. It will see it is observing a decrease, right? It will even slide even more down, it will come to this point. Okay, this will be coming to this, then it will change the theta, it will see it is coming to this point. This point, as you see, has a lower value. When I say lower value than this point, then it will try decreasing theta again, so this will be higher value. So the gradient descent will now be a fool, it will be fooled up, it will be stuck in this local minima, whereas this is the main local point, right? It will be the main local it will be a local minima. So these points, this one, this one, this one, this one, and this one, these are called, these points are called local minimas. Okay, so if you use the cost function for, if you use cost function of linear regression for this logistic regression, your function will get stuck into local minimas, which will be dangerous for you. It will yield you wrong values, you will never get the values that were truly correct. Okay, that were truly correct, so you will never reach to the actual minima that the model will supposed to have. Otherwise, when you see, instead, if you draw the cost function that we have shown you, right? So don't go for the cost function basic. I have proved also, right? It will asymptote to negative infinity at 0, and it will asymptote to positive infinity when it reaches 1. So this will be something like this. So from this also you can see the same thing, right? You can see the same thing. Like this is the cost function that we use. So here we will have a good minima which we can find out using gradient descent. So it will be these 2 points. These two will be minimum. This will tend to converge to positive infinity. This will go towards negative infinity. This will never merge. Okay. And for wrong values, this upper parts, these parts will go to mid positive infinities. Okay. So that's why we use this kind of a function for this kind of a cost function for logistic regression. It is a very frequently asked questions in interview. So answer it like for just draw this graph, they will get impressed first. Next thing will be answer them. The for logistic regression cost function can get stuck into local minimas, so that won't be yielding the right values of theta. Whereas for logistic regression, if we go ahead and do use this cost function, write down the cost function, then it won't be getting stuck in local minimas, as the lines are pretty straightforward, right? So for sigmoid function, we cannot use the like cost function of linear regression. So that's how we have here. Okay, so that's what sums up the theory part. Okay, so let's go ahead with this. So so this is the gradient descent formula that we are creating. Okay, because this is not we are supposed to be used. Okay, so now if we run it, it will have some kind of a error value kind of thing. So I am not explaining this. Now we will apply the same thing on a data set. That is the data set that is supplied with your material. That will be some kind of a diabetes data set, I believe. Do I have the file name hard coded? Okay, now we put all this into account and see we have a 874% of a accuracy score. Okay, we have a mean accuracy of 77.124 percentage. Okay, so how do we calculate this kind of a, how we are doing this? We are doing this with confusion matrix and all. So that's what basically is with this logistic regression demo. Okay, we are using n folds, that is 5. So that means for the gradient descent, we wanted to descend for 5 times. So you see we have accuracy 5 times, we have accuracy, right? 5 different accuracies. Okay, we have it from this. So the mean accuracy is 77%. So this is just we implemented. This is the basic, just to implement the basic concepts. So if you see, for predictions, we have this kind of logistic regression function, the like what we had yesterday, I mean the sigmoid function. Then we have calculating coefficients also, right? Coefficients also we have. Then for prediction, we have the sigmoid function again. Okay, so that's how this works. So no need to go much detail into it, because we are not going to write this algorithm on our hand. So we will basically do one thing. We will go for a demo with proper files and proper data, but the data might not be meaningful. That's fine, leave it. But you will see what kind of a thing what kind of a value it yields, and how do you use scikit machine learning, this one actually. Okay, this example. So how you can use scikit machine learning package to work with logistic regression thing. Okay, so now what we will do, we will see how you can apply logistic regression to this. You will see getting done in 1 minute, right? One line of code. So that's the main funny part of machine learning. Even if I skip it, then also you can write the code, but you won't get the basic of it. So that's right. Anyways, so let's see, we are going to do with a heart disease data set. Okay, I will open that up for you. Where it going? Come on. Yeah, I have this, I have this. Okay, so we for this example, right, we will be using a heart disease data set, which will have 303 rows and 13 attributes. When I say attributes, that means the features. Okay, in this example, we are going to build a classifier, so which can predict if the person has a heart disease or not. Okay, if some person in our data set has a heart disease or not. So when we say the target has a heart disease, the value for that would be 1. Okay, and when we say the person doesn't have a heart disease, the value for which will be stacked to 0. So that's how we are going to build the house predictor, I mean heart disease predictor classifier using logistic regression next. Okay, next is we are loading the heart data set here. Okay, pd.read csv, we are taking a glance of it, we are printing the shape and taking a glance. Okay, we are visualizing the target variable that we have, how it looks like. Okay, then we will be creating dependent and independent variables like we did. I am going to the example shortly, so I will example line by line, not an issue. This is just to give you a brief overview. Okay, we will divide the data into independent and dependent variables. Then we will split it into train and test set of 80-20 percentage, right? We will do that. Then we will train our model using these lines. So using scikit-learn logistic regression model, we are going to train our output model. Okay, then we are going to predict our values. Okay, we are going to predict our values. So next will be calculating accuracy. We will use some precision recall and confusion matrix. I will cover that. Then I will tell you how do we calculate the accuracy. Okay, then using ROC curve, we are going to ROC means receiver operating characteristics. So this kind of graphs, electronics guys must have been pretty well known curve for them. This is some kind of a frequency thing. Okay, frequency graph. So this graph will help you to understand what percentage of the data is covered under the logistic regression curve. Okay, so that's what we are gonna do next. Okay, that's what we are gonna do next. So ROC curve, if I tell it shortly, it plots the true positives and the against the false positives. Okay, so when I say true positive, false positive, what does that mean? I will tell you when I explain this confusion matrix. Okay, then you will have a clearer picture of it. Okay, so true positive, false positive, these are some things of like a classical confusion matrix. Okay, let me tell you first, then we'll go to the example. Okay, so last concept for the day will be confusion matrix. Okay, so confusion matrix, do I have this ready or I need to write? Let's see. Yeah, I have it. Yeah, so this is basically confusion matrix. Okay, so how does it look like? If you see, so the left hand side of it, right? So this part. Okay, so we have actual no, actual yes. That means the label data, the output of the label data that we have. So actual no's and actual yes. Then for this part we will have predicted no and predicted yes. Okay, this is our model output, this is our prediction output. Now if the model is if the actual is no and the model is predicting no, then that is a true negative because the answer matches. So when the answer matches, it will be true. So true negative, true positive. Okay, when it doesn't match, so no and yes, so false positive and false negative. Okay, right? So false positive and false negative. So these are what these are what some values are. Okay, so these are what some of the values are. Okay, so these are just random values, don't think of it. So how the namings will be done? It will be true negative, it will be false positive, it will be false negative, and it will be true positive. So how the namings are done? If the prediction matches, then it will be true, t will be at the beginning. Then what is the predicted value? Based on that we will calculate. So true negative. Okay, if it doesn't match, it will be false by default, false positive. Okay, here false negative, here it will be true positive. Okay, this will be some kind of a measures. Okay, next we have accuracy. Accuracy will be total correct predictions by the machine, that is true negative and true positive divided by total number of samples that we have, total number of data points that we have. That will be the, Ravi, we have this in the data set, right? These things we will have on the data set, correct? From Excel file we can get it, right? From Excel file we can get the count of zeros and ones, right? So that's how. So it will be divided by total number of predictions that we make, so that will yield you the accuracy. Okay, next is precision. Precision will be correctly predicted positive observation, that is true positives divided by total positives. So total positive, how much it will be? It will be false positive and true positive. So it is a measure how the machine is performing on the positive results. Okay, the next is recall. This is the sensitivity. You can this is the, I believe, no, Rohidas. So it will be, it is in the, so guys, can you confirm if you are able to see this confusion matrix in screen or not? Yeah, fine. So recall is for sensitivity. So when we say sensitivity, that will be correctly predicted positive observation divided by all actual positive. What is that? So how many correct positive prediction the machine has done, that is a TP, right? Divided by what is the actual positive, what is the actual positive outcomes that machine should have made. So those will be false negative, right? Because false negative will be those cases where the machine predicted it to be negative but it was positive, right? So false negative plus true positive, here the machine predicted correctly. So we are getting a measure of correctly predicted value in precision and recall. Then F1 score will be average of these two, okay, weighted average of these two. When we write F1 score, it will be 2 into recall into precision divided by recall plus precision. Why? Because in this we will take into account the true positive predictions of the machine, okay, and we will find out a ratio of it. So for accuracy, calculating accuracy of the machine, we use this formula, and for calculating F1 score we use this formula. So F1 score indicates how good the machine is at predicting true positives, right? Why this F1 score is needed? Because sometimes it might happen the accuracy is too high because it has predicted all the negatives correctly, but some positives got left out. But F1 score will point you out that error. Like, okay, I see your accuracy is fine, but your F1 score is not good. So you are not doing correct positive predictions, which will be a problem. So let's say when you are predicting some heart disease, okay, and you are telling, hey guy, you hey, see here, you don't have a heart disease, right? But think of a situation when the guys, when that patient originally has a heart disease, but you fail to recognize that. That will be a huge penalty kind of thing, right? That will be a huge loss for the patient's family. So that's why this F1 score is into picture, which will yield you the weighted average of precision and recall, so that you can understand how the model performs overall for positive and negative production predictions, and how the model works for positive predictions alone. So that's how F1 score will be there. So we will use both this for calculating accuracy of the graphs. So when we go through the example, we will see how it does. Okay, how we do. Okay, so moving ahead, we'll go ahead with the example now. Okay, the hands-on example that we have. So this is the data set that we are going to look at. Let me show you once. Okay, so this is the hard data set that we have. So we have a few columns: age, sex, CP, TREST, BPS, cholesterol, FBS, REST, ECG, and all those kind of XYZ kind of things. Okay, how many peaks are there, slopes, and all those kind of medicinal terms. So for now, no need to understand go into detail of these terms, but when you build a real model, you need to understand each one of this. Okay, we will just this is a very old and very cleaned up data set, so we won't need data cleaning also. So I won't be showing you the data cleaning part, because there are no actually there are no errors for this, because this is a very finely cleaned data set. But when you go for real world, when you work with real data, always go for data cleaning. That's the first part of it. That's the first part of machine learning. In the example, I won't be having a dirty data, so I won't be able to show you, but always remember that never take it as granted that the data will be fine. You need to observe the data. Okay, so always remember this part, because in net, whatever data set you get, it will almost be clean. Okay, only small things will be there, but that also won't be having much of here and there values. Okay, so let's go ahead with this. So pd.read CSV, we are reading the CSV file in it, right? We are checking the value. Then next, what we are doing, we are printing the shape. See here, 303 by 13. Okay. Next, what we are doing, we are checking a value count. So see, the target value has 165 ones and 138 zeros. Okay, 165 ones and 138 zeros. Okay. Next, what we are doing, we are plotting the values in a bar plot. So see, this has a value of 138, this has a value of 165. So just to visualize the data, okay, just to visualize the data, how the data looks like. Okay, how the data looks like, we will do that. Okay, next we will split the data into features X and target Y level sets, right? So we are creating a feature vector here. Yes, Veena, C1 is also a type of a plot. Okay, You can use matplotlib or seaborn plot, but seaborn is not much used. So seaborn is a plotting library which was built on top of matplotlib to give you a for these graphs. Okay, so that is not much of a used. So for nowadays, okay, matplotlib is the most used plot that we have. Okay, that's how. Okay, so Seaborn was developed based on Matplotlib only. It is not higher or lower kind of thing, Ravi. It is just a separate mapping. Sorry, what is this? Plotting library, separate graphing library. It also has the same kind of features as of Matplotlib, but it is not much used. So see, one main thing in Python is open source, right? So you also can go ahead, take the matplotlib out, and you can build your own like some kind of a library and name it Ravi library. That you can do. Okay, so that you can do. So that's why this kind of things came out. Okay, this not much has a significance for us. Okay, so it also no need to go into detail. Chittaranjan, this is not a histogram. This is a bar plot. How histogram shows is different, right? Histogram will be showing you the frequency. It won't show you the count. It will show you as a frequency basis, right? So it is not a histogram. It is a bar plot. Okay. Okay. So next part is we are splitting the values into feature vector. That is we are separating the last column. That is the target value column from the data set, and we are passing this as a feature vector. So we will have X as a feature vector, right? Y as a target vector. So if you remember the slicing concept, so in the first line, what we are doing, dataset.ilog, then within square braces, we have colon, that is all the rows, then colon -1. That means remove the last row, remove the last column, right? So we have now feature vectors in hand. So that will be removing the target vector. That is the outcome vector that we are going to predict with the model. Okay, so we are removing that. Next step, we are taking only the last row, last column, that is dataset.ilog. Then with this square braces, so colon, comma, -1. So that means colon means all rows, -1 means the last column. So in Y, we will have only the last column. Yes, Rahul, X is multivariate. So this is an example of multivariate linear logistic regression that we will see. So the earlier one that I have just skipped and showed you, I will revisit that once also. Okay, let's not worry about it. I will show you this, then there I will show that one also. Okay, so we have a feature vector here. Then next we have a target vector. Okay, we have a target vector, right? We have it. Then we go into creating the model. So here is the model that we have create. So sorry. Next is we will go and create. We will go ahead and create a train test split. Again 80-20 split. Again 80-20 split of the data set, right? 80-20 split of the data set. So from sklearn.model selection, import train test split, xtrain xtest, ytrain ytest, and then we are splitting the data into 80-20. Okay, we are splitting the data into 80-20. Okay, so we have now splitted the model. We will use this xtrain and ytrain to train our model. That is to create our model. So from sklearn.linear model, we have imported logistic regression. Okay, we have named our variable log model equals logistic regression. We have created an empty logistic regression model. Then we have created log model dot fit xtrain and ytrain. That's how we fit a model, right? So when you fit this model, it will return you all this basic all this outputs. So it is basically a model, okay, which has all the theta parameters of theta parameters absorbed and all those kind of details. It has, the model has it. Okay, so now using the model we will predict x test. Okay, we will predict x test. So y prediction will be our x test. Okay, so for finding the accuracy, we have a function called score in the log model. So when we pass x test and y test, it will automatically calculate the predicted values, that is y predicted, and it will yield you the result. Okay, so what it will do, it will take the x test, that is a feature vector, into account. Okay, then it will apply the logistic regression function that you have already created or fitted. Then it will automatically calculate the y predicted value, will compare with y test and give you the percentage. Okay, it will give you the percentage. Ravi, the model won't work because this is a pandas data frame, right? So it won't work because if you have any data, let me show you. That's a good point you made up. So let me just quickly run it. See here, it is not able to predict it, right? Because input contains NaN infinity or a value too large for D type, right? So it has Na, so it is failing. So why it is failing while predicting? Because the Na value was in the later part, right? So it came into picture when we went ahead to predict the values, right? If we put the Na value somewhat up higher, then it would be failing while fitting the model. Okay, like that. So not showing here, showing that, I believe you must have got it, right? So that's what it will happen. So here only numerical values will work. So just to tell you one more thing which this dataset doesn't have, instead of 1 and 0 in sex, right? If you have male and female, okay, this you will also see. You will have strings. It won't work. Okay, it won't work. So what you need to do, you need to convert those string values into categorical values. That is a part of data pruning. I have shown you that also when we covered the pandas basic, right? I have shown you that also, how to create categorical values, right? Just revisit the example if you don't remember. Okay, so these things, this data pre-processing, data manipulation and wrangling, you would need to do in each and every step of your data scientist of your journey as a data scientist. Okay, so that is pretty much needed. That is the first step. I am repeatedly I will tell this: building a fancy model won't yield you good result. It is the good data that will yield you the good result. Okay, that it will be the fresh clean data which will give you the best result. It won't be the fancy model. Okay, because here the program is data driven. Okay, so if you don't give it good data to eat, it will be it won't be able to eat the data, and it won't be able to give you the outputs, right? So that's how. So the petrol that you supply to the machine learning model has to be clean. Okay, that has to be clean. Okay, that shouldn't be having any kind of a dust. That's why we have petrol pumps for our cars, right? The think like that only. Okay, so it has to be clean thing. Okay, so that's how you need to keep your engine clean. That's it. So next thing is confusion matrix. Okay, so that is a true positive and true for true negative, false negative and false positive. This kind of values are there. So this is a confusion matrix that is being printed out. Okay, next thing is we are getting a classification report. Okay, so this is the all the values that you have seen: precision, recall, F1 score and support. All the values that you see are printed out using this classification report function. So what you do, you just pass in the predicted value and the actual values. It will print you all these things. So these are based on those formula only. You can recheck also. Let's say let's go for precision. Okay, what was the formula for precision? It was true positive by true positive plus false positive. So 20 by true positive, 20 plus 25. So 20 by 45 was a, what is it? Sorry, I made a mistake, I believe. This will be true positive, true negative. Okay, what is the total of it? Okay, true positive, false positive. Sorry, 20 by 26. Where is it? Yeah, so the precision is true positive divided by true positive plus false positive, right? So 20 by 20 plus 6, that is 26, right? So 20 by 6, 20 by 26 yields you 77, right? So that's how you calculate precision. Recall and F1 score will also match your formula. So for recall, it is 67 because it is true positive plus true positive plus false negative. So it will yield you around say 67% like that. So this will match. Okay, this will match the formula that we have. So that will print this output. And this is the last thing. So this is from sklearn. We are having a ROC curve. Okay, that is receiver operating characteristics. So how our model performs. Okay, what is the percentage? Okay, what is the percentage? So if you see, not going into this detail, this curve you will really plot. Okay, not going into the detail of it, just I will just give it an overview. FPR, TPR and threshold, these are some terms for ROC curve, no need to go into detail. So if you pass the y test value and the predicted values, then it will give you all this. FPR is false positive rate and TPR is true positive rate. This is again based on confusion matrix only. Okay, so no need to go into much detail on this. So then we are plotting the true false positive rate and true positive rates, and we are checking the value under the curve. So this is the value under the curve. If you go ahead and calculate, it should be 0.74 as this curve tells. So our curve, that our model that we have built, has an accuracy of 74%, which is good enough for this. Okay, so that's how we have. Okay, that's how we have, and this is the best accuracy that we can achieve from our model. Okay, so that's how this logistic regression works from scikit-learn. From scikit-learn, that's how you can use logistic regression to work. Okay, so see here we have some Pima Indians diabetes data set. So this will be this one. So this is this data set. Okay, this is the target value of 1 and 0. These are some fancy column names. Okay, so we have this data set. Okay, we are reading the data set. We are loading the CSV file. Okay, so load CSV. Let's go to the definition. Load CSV will be for reading the file, right? This will be this one. So pd.read CSV. It's nothing else. Okay, then next will be for I in range ln of dataset 0 str column to float dataset comma I, because here we have some column in string. Okay, some column we have in string, so we are converting those to float in order to have it in so that we can apply machine learning. This is not at all required for pandas. So just this is just to make the model work. We have did that, but this is not really required. Okay, so then what we are doing, this part ignore this, not required. So here we are passing it to evaluate algorithm, data set, logistic regression, n folds, L rate and n epoch. Okay, now let's go to evaluate algorithm. Let's see what that. Okay, normalized data set, what is that model? Then it will be zero best index, actually 0 1 2 3, like that it will rename. Actually Ravi, the pandas will do it like that. Okay, so here what we are doing in the evaluate algorithm, we are creating folds. Okay, so we are creating clause validation split and we are creating n folds just to run the data set 5 times. Okay, so for fold in folds we have train set and test set split. Okay, then we are predicting the value using this algorithm. So in this algorithm, the algorithm would be written. Okay, where is the algorithm now? Actually this file that I have, it is not the correct file. That's the problem. Okay, so this is the algorithm. Okay, logistic regression algorithm. We have train data, we have test data, and all those things. Okay, so see, here is the curve. Y hat will be predict row comma coef. Coef will be coefficient. Okay, first let me go to this. Coef will be coefficients SGD, that is stochastic gradient descent. Train, L rate and n epoch. Okay, these are theta values that we are passing. I mean theta values we are trying to calculate. These are just variable names, no special significance. So once we go to coefficients SGD, this one. So see, for the theta 0, I am initializing it to 0. Okay, that's what we do. And then for the vector, for the number of vectors, right, number of features that we have, we are calculating the coefficients. Okay, we are calculating the coefficients. Okay, so this is the value of coefficient. If you go into the maths, then if you calculate the theta values, this will be how it is coming. Okay, we're using the gradient descent formula. This is how it will be coming, and this will be the gradient descent formula for calculating coefficient. This is not required, so no need to go into detail, just see how it works. Okay, so here it is calculating the each of the coefficients. Okay, each of the coefficient is calculating. So this is the theta vector. So see, this is the basic thing. Using gradient descent, we will calculate the theta so that it returns you the optimal theta value. Okay, so that it returns you the optimal theta value. So that's the idea. So how we are using gradient descent here? We are calculating the predicted values. Okay, we are getting the predicted values using this line. Okay, then when the predicted value is here, we are calculating the error for it. Okay, error is we haven't put in, so we have find out the difference, that is 1 minus that thing. Okay, 1 minus that thing that we have in our data set, right? In our cost function we have yi log of h theta x. So this is what is this. Okay, so this is the yi, this is the h theta x. Okay, so if it is 0, then it will be h theta x. If it is 1, it will be 1 minus h theta x. So this is that term. Now in the next part, we are calculating the coefficient from that. Okay, we are calculating the coefficient from that, and this is the theta value that we are calculating. That's how coefficients SGD function works, and will return you the theta values. Okay, after that, see, come back to here, you will see after calculating the theta, we are passing it to predict the output value, because now we have a predict value. See here, here is the sigmoid function. Okay, Ravi, you are asking about sigmoid function. This is the sigmoid function. So y hat equals coefficient 0. That's what we do, like theta 0 equal to coefficient 0, that is theta 0. Then for I in range len of rho minus 1, we are keep on appending the values, that is theta 0 plus theta 1 x1, theta 2 x2, theta n xn, right? So here we are doing that. Okay, so coefficients I plus 1 means theta 0, theta 1. From theta 1 we are starting, because theta 0 we already have it, because x0 will be 1, so we are skipping it. So it will be theta 0, that is this one is theta 0, and this one is from theta 1 to theta n xn. This one is calculating that, okay, and adding it. Okay, so theta 0 plus theta 1 x1 plus theta 2 x2 till theta n xn we are calculating in this line y hat. So we have theta transpose x ready now. Okay, then we are passing it here. So 1 by 1 plus e to the power minus theta transpose x, we are passing it here, right? So this is the predict value. So this is the sigmoid function that we are using, and this predict we are also using while calculating coefficients, because that would be needed. So that's what I was trying to explain you. So h theta x we will substitute in the cost function. So using gradient descent we are calculating coefficients values. Okay, and then we are making our predictions, and we are calculating our accuracy scores. Okay, accuracy scores. So that's how this algorithm actually works. So this much of a complex task was simplified by scikit-learn, and you need to write only one line in order to find out the values. Okay, in order to find out the values. So that's how this logistic regression actually works. If you want to calculate, if you want to relate the maths and stats, that's how you can do it. Okay, so decision tree is again used for classification, or it can be used for regression also. The same algorithm, it can work for both. So decision tree is that much of a powerful tool. Okay, so it can be used for both classification and regression, but for ideal scenarios we use it for classification, because it suits it better, in a better way. Okay, regression also you can use, but it is not suited. It will still yield you some result, good result, but still it is not preferred. If you want to go for a regression kind of thing, go for linear regression. Linear regression, that would help you getting much better result than decision tree. Okay, so decision tree can work on basically both continuous values and categorical values. Okay, so it can work on both of this kind of data, and how it can work I will just show you in a few minutes. Okay, so these are just basic things. Logistic regression, the decision tree. So decision tree is nothing but a, so see, how a tree grows, right? Tree has a root at the bottom. Then as it starts growing, it will be divided into branches, right? Branches will again be divided into sub branches, like that a tree grows, right? So here also we have the same approach. Okay, here also we have the same approach. Just a minute. I will take up my pad. I want to show you something. I will just draw a picture that will help you to understand this decision tree clearly, and you will see why the name is decision tree. Okay, why the name is decision tree. So if anyone here from computer science background, you must have learned binary trees or n-ary trees when taking classes, right? When taking data structure classes in the college level, right? So this tree is also similar to that, but there the branching was based on some decision. Here also branching will be based on some decision. Okay, so how the branching is done, we know. If some condition is set to be, I mean, if some value is set to be smaller than the root, then it will go to the left hand. If it's not, if it's greater than that, it's gonna go to right hand, right? That's how it used to work, right? So if I just draw a small thing, so you will see why this name decision tree is so is used here. Okay, you will see that. So let's say we have a root node. Okay, we will have a root node, that is this node will be blank. Okay, this node will be blank, and here we will have it, this is called root of a tree. Okay, in the, it will go to left, it will go to right, it will have some nodes, intermediate nodes. Okay, the values of intermediate nodes, then it will again branch, it will go to left and right. Like that it will go on till it reaches the endpoint, okay, till it reaches the last level. So this level is called root level, right? This is called root level. This is called the leaf nodes. This is called leaf nodes. What do we mean by leaf nodes? Leaf nodes are the end nodes, right? After this, the tree cannot branch anymore. Okay, these are called branches of the tree. These decisions are called branches. Okay, so branches will be based on some decision. Okay, let's say, so if you consider this from a top-down approach, if you reverse it out, you will see almost a tree-like structure, right? First root is there. From that, as a tree grows, it will be divided into two parts based on some conditions. So there will be branches, there will be leaves also. So see, so the tree starts from a root level, right? So root level is the starting point of the tree. Now it will keep on branching based on some XYZ decisions, okay? And wherever each branches ends, those are called all these things, right? All these square boxes are called nodes, okay? These square boxes will be nodes, and each of these nodes represents a scenario, okay? So each of this node will represent a particular scenario, okay? So that means that will be your output. So each of this node means some of the outputs. So let's say the classification problem of male classifier. If I draw it, so it will have a leaf node, right? That male classifier will have a root node. So this is root. Root doesn't have anything. It is just the male object. Okay. So the one of the lines in the CSV. So then it will branch. Okay, it will branch like spam words. We used it, right? So spam words greater than 3, spam words less than 3. Okay. So here if I come, it will be spam, it will be not spam, like that. Okay, it will be not spam. So this is a state, this is a state, okay, this is a scenario. Now if we come here with spam word 3, and if we have some other conditions also, then we will keep on branching. Okay, so wherever we found this nodes will be a individual scenario for that data. Okay, for that data, this nodes will be the individual scenarios. And where the tree stops, okay, where the tree stops, like for this case, if I remove this line, so it's here. So wherever the tree gets stopped, those nodes are called leaf nodes. So they will be your ultimate outputs. Okay, they will be your ultimate outputs. That's why this is called a like decision tree, because this structure branches in and out like a tree. So there will be root, there will be branches, there will be leaf nodes, there will be nodes, and everything will be there. So this is how a tree grows. Okay, now let's go ahead with the PPT. Let's get into detail. How do we use it? So see, this is an example. So age less than 30, if it is a yes, then it's a lot of pizzas. So first we are checking, is a person fit or not. We are checking if the person age is less than 30, right? So if it is a yes, then we are checking if he hits a lots of pizzas or not. So generally less than 30 guys will be fitter, right? So if he doesn't eat some junk foods daily, so that's what we are checking. If he eats it, then unfit. If it doesn't, he is fit, right? But for less than if it's greater than 30, then you need to exercise, because after 30 your health starts degrading. If you does, you are fit. If you're not, you are unfit. So that's how a decision tree grows. That's how a decision tree works actually. Okay, so for random forest, what we have, random forest will be having multiple decision trees. Okay, it will have multiple decision trees. Then we will be calculating all the decision output of the decision tree. We will take all those, we will merge those to get some accurate and stable prediction. Okay, so this is but what the problem with random forest is, why we don't prefer it, because random forest, as we have multiple decision trees, we will be having a problem of overfitting, because we have n number of decision trees based on number of features. So if we create a decision tree for each of the features that we have, it might overfit the training data. So it is a good algorithm, but for data science or machine learning anywhere, you need to use it carefully. So that's why we kind of try to avoid this. Okay, we're trying to kind of avoid this. So there are many scenarios when you need to include multiple decision trees. There you need to take care of the decision tree sizes and all. Okay, So that's why for the beginners it is not advisable to go for random forest at the beginning, because random forest can have a problem overfitting. As you can see, if you have 5 features in a data set and if you create decision tree for each one of them, right? Let's say for age. So here we have seen age less than 30. If you try and create a larger decision tree, if you start from age less than 10, then 50, then 15, then 20, 25, 30, if you keep on growing the age group like that, if you, let's say in the data set you have, so in this you let's say you have something called like age, and in the data set that you have number of, let's say, a number of age groups, and you are creating models for, you are creating nodes for each of the age groups. So then that data will be overfitting. Okay, naive bias is another like classification algorithm. Okay, so naive bias, as you know, right? In the probability theory we have conditional probability theory, we have it, right? Bayes theorem. So that is what is the basic of this naive bias theorem. So what we have, probability of A given B has happened, then the how we write the formula, probability that B probability of B given that A is happened multiplied by probability of A divided by probability of B. This is what is the basic of naive Bayes theorem. Okay, so this is this takes into account some historical knowledges. Okay, so as you see, you are trying to predict probability of some event A with respect to probability of and you know that that B has already happened. So you are taking this as a historical factor, probability of B given probability of A has probability of B provided A has already happened. So this is a historical factor. So you need this historical knowledge in your when you have this historical knowledge, then you can go for naive Bayes theorem. Like let's say for cancer prediction, right? So it doesn't mean that a test, if it comes to be positive, will definitely mean that that someone has a cancer or some other diseases, right? So what you can do, you can I mean, if you have this so let's say in past you have seen like guys like 70% of guys who has a positive result in the test. So let's say in past you have seen the 30% of the guys having positive test means they have a cancer. So in those cases, naive bias you can use, because you need to have a historical thing. And next thing that you need to take care of is the features in the data set should be unrelated to each other. Okay, it shouldn't be related, because as you can see, like this depends on some other, so feature X depends on feature Y, the probability of feature X depends on if feature Y is present or not. So that's why the features should be like unrelated to each other, otherwise it will be a problem and this the theory will fail. Okay, so this is a classification based on Bayes theorem, as I already told. Presence of particular feature, this also I told, right? So presence of a particular feature in a class has to be independent of any of the classes. So any calculated feature shouldn't be there, otherwise this will fail, because that probability it will yield as 1. So see, probability of disease you know as 0.1, and probability of disease bar, that is 1 minus probability of disease, is 0.9. So you know that probability that someone has tested with positive, given that he has the disease, is 80%, and it is the reverse, like probability of negatively tested having a disease is 20%. So this kind of historical knowledge you will need. So these are the historical knowledges that you have. Okay, so let's say you are running a diagnostic clinic, so you are gathering this historical data to find out the actual values. Okay, so that's what we have. So this is what is the basic of this thing. Now first we will go for decision tree, then we will be going for the example. Decision tree and logistic regression you can use anywhere, so you just need to practice it, you will get the idea better. So whatever can be solved with logistic regression can be solved with decision tree also. Okay, but building decision tree takes up some time. So for beginners, go for logistic regression, try to move into decision tree slowly, but decision tree will yield you accurate result, but you might run into overfitting problems also. Next is, let's say we are doing fruit classification. Okay, so we have color and diameter. Okay, we have color and diameter, these two labels. We have color green, mango, yellow, lemon, and all these things, and diameter of those are 3 and 1. Okay, so this data set is not clear, so let's just adjust it for a moment. I will explain how it works. Okay, So before that, I will show you all this. So how this decision tree works and how do you know when to stop, right? So we have a factor called entropy, information gain, and Gini impurity. Okay, so you need to check those things. So if you remember the laws of thermodynamics, right? What does entropy says? Entropy is entropy will be zero if the set is perfectly ordered, right? Entropy will be zero if the set is perfectly ordered. It will be high if the set is perfectly disordered. So you need to calculate entropy. There is a formula I will show you shortly. So from that entropy, you need to calculate this information gain. These formulas I am coming to it. So you need to go on calculating this. So if any point you see the information gain is not something positive, then you need to stop it, because there is no need of splitting the tree, because that's not gonna yield you something, right? So that's how you need to figure out about this decision tree. So see, this is the ideal scenario. Is diameter greater than equal to 3? Then if it's less than 3, then we have only cherry, right? Because it is a R1 and cherry, so diameter of cherry is 1, so it will be cherry. If it's greater than 3, then we have two options, like mango and lemon, right? Like mango and lemon. So now we will be checking color. So if the color is yellow, then we will say it's lemon. If not, then we will say it is a mango. Okay, so that's how this decision tree works. That's how the decision tree is built. Let's see with the example now. Okay, before that, these are a few terminologies: root node, leaf node, parent, child, and branch and subtrees. You can see like these are all related to the like present world only. So the root node, leaf node I have already covered. Parent and child node, like the predecessor node is called parent, the successor is called child. It's that simple. Okay, branching and branch and subtrees are, you can see like if you it can have multiple subtrees. So so these are branches, as I told. So this left subtree can be one subtree, this right subtree can be one, this subtree can be one. So it is basically independent parts of the decision tree. Those are called subtrees. As you see from the tree itself, it's identical to the tree. In the real world nature, it's identical to the trees. So that's how. Okay, so next is coming two important terms: splitting and pruning. Splitting means dividing root nodes into different parts or the different child nodes, right? That's what is splitting. So splitting is the heart of decision tree, because if you don't split it wisely, then your decision tree can be a mess. Okay, so splitting is a part of it. So splitting means splitting the root node into splitting the root nodes into child nodes. Okay, so pruning, it will be, and random forest we would be covering in that much detail, so let's not worry about it for now. For now, just have this decision tree into mind. You will see you are getting confused with the decision tree alone. So let's just grab this concept first. Okay, pruning, that's a very important thing. Okay, so if you are trying to build a decision tree, you can run into one of the two problems. Like you can either underfit the training data, or you can overfit the training data. So how does it happen? So if you see, like if you build a small tree, right, then you are not gonna fit the data, you are going to underfit the training data, right? But if you are trying to build a huge tree, like a huge bush kind of a thing, then you will be overfitting the training data, because you will analyze the data, you will break down the data into so much nested levels that it is going to overfit the data. So that's where pruning comes very handy. So for making ideal decision trees, what we do, we don't care about what are the levels, if it underfits or overfits, what it does, we don't care about it. Okay, we let the tree grow. As soon as you have decisions, we let the tree grow. Then we come back and prune the branches where we see the information gain is not that valuable, or where we see the information gain is, or entropy is too low to consider. So those things we can take care manually by pruning the branches. Okay, so that will make the tree shorter, which will in turn give you a good result, which will in turn give you a very good result. Because in that way, what you can do I mean, first you can if you build a small tree, then you won't be able to optimize the tree, right? Because it will be small and it will be underfitted already. So if you build a big tree, a bush you can consider it as, so then what you will have lots of training example, lots of branches, lots of decisions that were there in the tree, and from that you can choose wisely, like which one to use, which one not to use. These are theoretical concepts. Have these things clear, because if when you go for interview, interviewers are not going to ask you how to make a decision tree out of a scikit-learn package. They know you know it, because that's just a one-liner syntax. So they are going to hit you in this core concepts. Okay, they are going to hit you in code concepts. So they can ask you how to solve the problem of under overfitting in a decision tree or underfitting in a decision tree. These things then you need to answer. We can have splitting, we can have pruning, we can check the entropy, information gain, and Gini impurities, Gini index values to check it out. Okay, to check that out. So if it's still splittable, then we can have it go ahead and we can split it. If the information gain is 0, then we can stop. Then we can prune those branches like that. Okay, so that's how. And for all the algorithms, it's the same thing. They will they can, for linear regression and logistic regression, they can ask you why you don't use logistic regression, linear regression function in logistic regression, right? Cost function in logistic regression. Those things are theoretical questions will be asked. So they are not going to ask write a code that will implement decision tree. It's not possible for anyone. It's not possible to learn to write that entire code, but they might ask you for the algorithm. So go ahead and show them this. Okay, like that. You can say like I can show you graphically how a decision tree works, like that. Okay, let's go ahead and see how do we create a decision tree manually. Okay, I mean mathematically. Okay, so see, this is our data set: outlook, temperature, humidity, windy, and play. So these all are features from outlook till windy. These are all our features, and play is the binary variable that we are going to predict. So if the outlook is sunny, temperature is hot, humidity high, windy, it's not windy, should we play or not? So it's a no. So this is our labeled data set that we have. So now let's go ahead and see how do we decide whether we play or not. Given a condition, how do we decide if we play or not? And how do we pick this first and second things, right? How do we pick that? So like which one among them should you pick first? That means we need to start our branching from somewhere or something, right? So should we start branching with outlook? Should we start branching with temperature? How do we go about it, right? So we need to determine the attribute that best classifies the training data. What does that mean? Let's go ahead and see the answer. Okay, I mean, how do we decide where to split? So these are 4 things that we're going to check. Okay, so first one is entropy, that defines a randomness. This is a metric which measures the impurity, right? As I already told, so this is the first step to check the data. So what we can do, we can split the data based on anything, and then we can go ahead and check the entropy, and then we can decide on it. Okay, so and we can decide on it. So that's how we can that's how we can go ahead and do it. There is reduction in variance. So as you can understand, if this like 1 second, getting a call, 1 second. Yeah, so reduction in variance, as you understand, like if you keep on reducing, if the entropy is reduced, then the variance will also be reduced. Okay, so we will be start to split the data based on the lower variance value. Then there is information gain, that is calculated based on entropy actually. And if you see, if where the information gain is highest, from there we will start splitting the data. Gini index is also the same thing. So that is again used in cart model of so decision tree in cart. When we do, like, cart means classification and regression trees. Okay, so when we use cart model of decision tree, then we do it. Then we use this, like what this Gini index to have the Gini index to calculate this. Okay, and the how this Gini index is calculated, we will be seeing that in a moment. So I will write the formula and show you. Okay, let's wait for a few minutes. I will show you all this one by one. So let's go ahead with the example first. Why we using decision tree? Okay, so see, now entropy formula is here, right? Negative P of ES multiplied by log of PES minus P of no into log of P no. So that is how entropy is defined. That means we need to add the entire thing, like, and the probability of both the events multiplied by their log likelihoods. Okay, so that will get you the likelihood of the event. Okay, we need to add those both, and we need to put a negative sign we need to calculate the entropy like that. Okay, so P of yes means probability of yes, P of no means probability of no, like that. And if you going to draw this curve, then you will get, so negative sign is given just to make it positive, because log P can yield you negative result somewhere, because log value will be pretty small, so it can yield you negative. Just to make it positive, the negative sign is given, nothing else. Okay, if you draw this curve of this kind of a function, you will get this kind of a hyperbola kind of a shape, right? So number of yes, if it's 0.5, then entropy will be 1. So as you see, for 0.5, that is the perfect equilibrium, right? When the data is perfectly in equilibrium, we will have the highest value, that is 1, right? When the data, so that means here the disturbance of the data is highest, right? Because it has both the components, right? It is both the components. Why? So true and false are mixed, right? True and false are mixed, so it is the highest of impurity. So let's say if you have a 30% yes and 70% no, then also the data is somewhat skewed to to no part, right? It is not that much of a what should I say? It's not that much of a impure. It doesn't have that much of a impurity. So it's not in the what? It's not in the chaotic state, right? So you will see the value is reducing. So if you have 0 and 1, for this the value is maximum. That is, value is minimum. That is 0, right? Why 0? Because the data is in perfect equilibrium. Because we have either all yeses or all no's. There is no other values. So either all yes or all no. So in that case, it goes to 0. So that is the perfect equilibrium scenario, right? That is the perfect equilibrium scenario. So that's how entropy works. So entropy is a measure of impurity in the data set. So as it lowers, the value of entropy will be lowered. As it gets higher, the value of entropy will get higher. And the 0.5, it will attain its maximum value of 1. Okay. So that's what is about entropy. And how do we calculate? We calculate like that. So P of event multiplied by log of P of event minus P of another event multiplied by log of P of that event, like that. Okay, so is this clear now? Entropy is clear? Then we will go ahead, because we are going to build the entire model based on this entropy only. So if you see, this is the entropy calculation. Let's leave it, no issues. So these are entropy calculations. These things you can easily get, right? I'm not repeating these things, log additions and all. So this is just, we have just proven that this formula can be this formula yields you 0 or 1, 1 at 0.5 and 0 at 1. So that's what. So it's not that much, where you'll just skip it and we will go to this much, right? This one, the main thing that we have in the question. So we have 14 instances of the data here. Now we have 9 yes, 5 no, right? So we have calculated the entropy to be 0.94 here, right? We have calculated the entropy to be 0.94. So see here, 9 yes, 5 no, that is chaotic. So value is really high, right? Value is really high. Now our object is to like divide it into subtrees so that the subtree can yield a perfect value. Let's see how we can do it. The initial entropy value is 0.94. Now we have this concept of entropy. Okay, like information gain, sorry. So information gain will be entropy minus weighted average into entropy of each feature. Let's see, how do we calculate? How many features do we have? Outlook, temperature, humidity, windy, right? 4 features. We will calculate entropy of both, entropy of all. Okay, so here see, now this is the information gain. This is the information gain. How are we calculating? Weighted average multiplied by entropy of each feature. Okay, so we have 4 features: temperature, outlook, humidity, windy. Now in order to calculate like this information gain for some node, we need to split the tree. We need to start it from somewhere. Let's go ahead and start with outlook. Okay, so from outlook, when we started, we have sunny, overcast and rainy, right? Three things. So for each of the features, we are going to do this. We are starting with outlook just as a basic. You can start with temperature also, that's up to you. This is not just that doesn't mean much. Okay, so outlook has 3 values: sunny, overcast, rainy, and it has some yes no kind of things, right? So for sunny, 2 yes, 3 no's; overcast, 4 yes; rainy, 3 yes, 2 no's, right? Let's go ahead and calculate entropy and information gain in this outlook node. Okay, so see, E outlook equals sunny is minus 2 by 5. Why 2 by 5? Because we have 2 yes, 3 no's, right? 2 yes, 3 no's. For sunny, 2 yes, 3 no's, right? So we have minus 2 by 5 multiplied by log of 2 by 5 minus 3 by 5 log of 2, 3 by 5. So 0.97. See, the value is getting higher. So in entropy for outlook equal to sunny is 97. For overcast, it is all yes, so it is 0. For rainy, it is 0.97, right? Because it has same thing, 3 no yes, 2 no's, doesn't matter, it will yield you same result. So this is entropy of each of these subsets. Now we are going to calculate their average weights. Okay, with their we are going to calculate the information gain from the entropy. Okay, so how do we calculate information gain from all this small all this entropies of this outlook feature? As you know, it is weighted average. Weighted average means how many examples you have under sunny as yes no, right? So here see how many of this data has outlook sunny, 2 2 4 1 5. So weighted average for sunny will be 5 by 14, number of that feature occurring in the dataset divided by total number of samples in the dataset, multiplied by what is the entropy of outlook being sunny, 0.97, right? We have calculated the information gain to be 0.693. Okay, this is not information gain, this is the information that we get from the outlook variable. Okay, this is the weighted average multiplied by this. So let me write it down to clear your doubts here. So for information gain, right, we have an equation like E of S, that is entropy of the sample minus weighted average multiplied by entropy of feature, right? So this part is called information, right? This part is called information. Why information? Because if you see this number, what does that mean? That this outlook feature in the data set has a weight of 69.693 in deciding the outcome of the data set. So this is called information that we have from the amount of information that we can get from this outlook value. Now what is information gain? It will be when we subtract it from entropy, right? Because the data set is already impure and we have some kind of information from a feature. If we negate those, then we get the information that is really meaningful to us. Because in this data set, right, in this data set, when we calculated entropy, we taken into account all this, right? All these 14, right? We have taken into account. Now now we have the total entropy, that is the total information, there is a total entropy of the sample space. Now we have the amount of information that we can get from outlook, only outlook, no other parameters are included, only outlook. What is the information that we can have, the amount of information that we saw to seem to be 0.693. But the entropy that we have in that, we already calculated this 693 part, right? We already had the 693 part included, because when we calculated entropy, we taken the entire data set into account. So if we negate this two, then we are getting the information gain of the data set. That means information gain from the outlook is 0.247. That's one measure. Okay, now next what we are going to do, we are going to calculate information gain for all other nodes in the similar way, and you will see the max gain that we can have is 247, right? We can have is 247. So max gain will be 247. So we are going to start splitting with outlook. We will first split with outlook, then we will check for the next is what, humidity, then we'll check for temperature. Like that we are going to create our tree. Now that's where we use entropy and information gain to decide on this data set, and we will keep on calculating this at each level to see if anywhere information gain becomes 0, we are going to stop it. Okay, so that's what is about the concept of information gain and entropy and how we can use it to decide the best feature. Let's go ahead. So for temperature, as you see, we have hot, mild, cool, 3, right? So for hot, if you need to take out these data sets, no, no, yes, yes. So 2 yes, 2 no's. So it's in 0.5. So entropy will be highest for this. Like that, for mild also you can check, for cool also you can check. You can fit in into this formula and you can check the manual result also. That we can clarify the results. Yeah. Okay, so let's go ahead and see how do we split. So outlook, sunny, rain, overcast, right? As you see, that's what comes into picture when a entropy is 0, right? Outlook, entropy of outlook being overcast is 0 because all the examples here are ES values, right? So when we start splitting on the outlook, what we will do for overcast, if the condition is overcast, we no need to consider any other variables into account. We can say the output will always be yes. So that's what happens when entropy becomes 0. Okay, so whenever you see outlook is overcast, tag that to yes. No need to check other conditions. So that we will stop here. If it's sunny or rain, we still need to go for other features to see if it's a yes or no. So let's see how we go about it. So now next is windy. Why windy? Okay, windy we don't have, but windy's information gain is in the second hand. Okay, windy's information gain is 0.048. So okay, so for humidity we have 0.152, right? We have 0.152 for humidity, we have 0.029 for temperature, and for windy we have 0.048. So the next two nodes of the split will be humidity and windy. Okay, humidity and windy. So windy here it is calculated in the same way, not explaining that. Let's go ahead. Then we will be calculating with humidity and windy. Okay. So if humidity is high, then no. If normal, then yes. If windy is strong, then no. If weak, then yes. So if you go ahead and check, let's say humidity high, right? So how can we check this, right? How can we check this? So see here, if outlook is sunny and humidity is high, what is the output? Outlook is sunny, humidity high, output is no. Outlook sunny, humidity high, output is no. Outlook sunny, humidity high, no. Outlook sunny, humidity normal, yes. So if outlook is sunny and humidity is high, we are going to have a default no. So we no need to take into account other variables, right? But if it happened that for humidity high we have one yes, then we would have taken into account the temperature feature. Okay, but here we no need we don't need that. Okay, here we don't need that because outlook and humidity, outlook sunny and humidity combination can yield you a perfect equilibrium state where entropy becomes 0. So you can stop it there. But if you didn't had this kind of a thing, then you would have gone for the temperature variable or the windy the temperature variable, right? So that's how it calculated. Now go for outlook. Is outlook overcast? Always yes, leave it, no issues. Outlook rain and there is a strong wind, right? Let's see. Outlook rainy, windy falls, right? From where it got to strong weak. Okay, windy falls, that means weak winds. We have yes. Outlook rainy, windy falls, we have yes. Outlook rainy, windy, we have no. Outlook rainy, not windy, we have again yes. So if outlook is rainy, outlook rainy, windy true, we have no. Perfect equilibrium, no need of further split. So if we have outlook to be rainy and if the wind is weak, we are going to play. If not, we are going to we are not going to play. So that's what you can see from the data set itself, right? So thus the tree reaches. So if you calculate equilibrium of each of these nodes, you will, I mean, entropy of each of these nodes, you will get a 0 because the subset that the data contains here at this point of time, like what I showed manually, right? If you calculate entropy of it, you will see all the variables are the same result. So it will be having 0 entropy. So the tree stops here. If it didn't had this kind of a thing, we would have gone for the temperature variable, but whereas this is not needed here, this is not needed. Okay, so that's how we have it. Okay, that's how we have it. So humidity and windy, Ankur, will always be on the always be down the outlook, right? That's what it is. So both are on the right left, doesn't matter. You can have it in the any way and anywhere, right? Why humidity below sunny, not windy? Because humidity's information gain is the highest after outlook. Humidity is the highest, wind is the second highest, right? So we will go with the two nodes. When you are going to branch, it will have more than one branches, right? If for overcast it didn't had this, then we would have gone for windy here, here temperature, like that. So when you are branching the trees, you need to select the nodes having highest information gain, okay, and the highest ones will always be on the left. So that's how you can exchange the right and left subtree also, that doesn't matter. It's just a you can take it in any ways, the result will be same. So after humidity we don't need anything, right? So humidity windy combination won't yield you any result, as you can see, because if it's sunny and based on humidity only you will get the perfect equilibrium, so we don't need to go about it. Okay, that's right. Okay, so that's what sums up this example. Okay, okay, so next we have confusion matrix, guys. This we have shown in the this we have seen in the last class, right? So not going to explain this here also, because it will be a repetitive thing, right? So here just a calculation I will show you. So see here we have a expected, so everyone remembers confusion matrix, right? True positive, false negative, true negative, everyone remembers these terms, right? So let's go ahead and see an example here. Okay, so we have a expected and predicted sheet where we have man and woman as predicted. So see, we have predicted three places we have predicted it wrong. Okay, and we have predicted 7 as correct. So accuracy of the model will be 70%. Okay, so as you know that, right? You know that already. So next is men which are classified as men. How many are those kind of instances? Man as man, man. So 3. Woman classified as woman, we have 1, 2, 3, 4, right? We have 4. So sorry, 1, 2, 3, 4. So now if we men classified as woman, we have 2. Woman classified as man, we have 1. So now if we go ahead and build this, so this is your positive, this is your positive. So this one is true positive, that is 3. This one is woman. So this is true negative, that is 4, right? We have this man and woman, so that is true negative, 1. This is woman men, this is false negative, that is this is false positive, this is false positive, false men calculated as woman, false. So false positive 1, false negative 2, right? We have it like that. Now we can go ahead, so this is how confusion matrices are made in the real world. Okay, true positive, false positive, like that we calculate. Okay, like that we calculate. So that's how we have this kind of the confusion matrices. So next thing is naive bias. Before that we will see the example of the decision tree hands on. Okay, so we have a banknote data set. Okay, it will be classifying the banknotes as true, false, like that. Okay, this is a banknote data set. Okay, now we are going to define a function to load the data. So this is nothing but pd.read csv. Okay, this is our own function we have defined. You can go for pd.read csv also. Okay, so let's not waste time on it. Okay, see, these are some calculations of Gini index and all those things. I will come to it later. Let me show you how you can use scikit-learn to. Okay, this is the, what is it? Okay, let me show you. So this is for loading the CSV files, not explaining line by line. This is for converting a column to float, string column to float, because decision tree we will work with data, not string. So we are converting string columns to float, because this is a CSV file, right? All those will be read as string only. We haven't used pandas, we have written our own function. So we would need to do change all these columns to real world numbers. Okay, this is for creating cross validation set. What is cross validation set? Let's say you have 1,000 rows of data to process. You don't feed the entire data to the model at once. Okay, you just you provide the data to the model in folds, multiple folds. What that would do, that would help you in gaining the most out of the model, because in the first model whatever mistakes it does, it will learn, it will go for the second step, like that. Okay, so here we will be splitting the data into cross validation sets. Okay, next will be to calculate the accuracy, that is correct divided by expected by predicted correctly predicted value, number of correctly predicted values divided by the entire divided by the total number of what samples in the data set. So that is for that. Next is for evaluating the algorithm. Here I will take some time to explain this. Others are already you have seen it multiple times, so it's the same thing basically, it's nothing else. Okay, so here you see that 80-20 split that you are seeing. So this is the manual implementation of decision tree. So that's why we are writing all these algorithms on hand. Okay, this can be done with scikit-learn in one liner also, that's also there. Okay, So that's all. Okay, next one is for this evaluate algorithm. We are splitting the data set into cross validation sets, right? We are now we are sending the folds one by one. Okay, we are sending each fold one by one to the machine learning model to predict the algorithm or to predict the output. Okay, so see, we are creating trend test split. Okay, we are creating trend test split of 80-20 in this function. So here we are doing it. Okay, for each row we are copying the row, we are appending to test set, and we are removing it from the train set. Like that we are creating trend test split, and then we are passing this to the algorithm that we have. So algorithm is nothing but the decision tree that I am coming to it. So next is actual prediction, that is there in the data set. That is the last column, and there is accuracy, that is actual by predicted we are getting from the algorithm output, right? So that is a decision tree algorithm actually. Okay, that is the decision tree algorithm that we have. I will show you. So next is actual and predicted. We are just appending the scores. Okay, next is test split. See here, we are creating the test split here. Okay, we will be passing a 20 value here to get the test split. This is for getting the Gini index. Okay, for Gini index the measure is pi into pj. Okay, where for in the all sample it is just pi into pj, that is weight of the group score by its relative size. Okay, so it will always be this way it will be calculated. So it's not much to be understood in detail, because you are not gonna write this algorithms in manually. It's just gonna do, you just gonna you do with like scikit-learn, so it won't be used much. Okay, next is define a function to best split for the data set. So class values will be so we are getting a split here. No need to waste time here. I just I don't want to split the time, spend time here, because you are not going to write this manually. Okay, this is just to show you like how it works. And this is the split algorithm to split the left and right subtree. Okay, you can go through the code, let me know if you have any problem. We are building a tree with the help of the split function, right? We are passing each and every node, we are passing the root node, we are passing the max depth, min size, and we are started splitting this. Okay, we are splitting based on the Gini index. We will see how those are calculated. Next is these are for prediction. Okay, these are for predicted predictions that we have. And now the main thing comes into picture. This is the decision tree algorithm model. Okay, this is the decision tree algorithm model. Now next step will be to read the data set. Okay, so don't no need to go for the details of those algorithms. I will explain how it works in full. Okay, so we are reading the file with the load csv command. We are reading the file. Okay, then we are converting all the columns into floats. Okay, as I told. Then what we are doing, we are creating n folds. We are taking three values: n folds, max depth, and min size. Okay, then we are going to scores. That is, we are going to calling the evaluate algorithm method that we have defined earlier, and from that, using all the concepts that we learned till now, it is passing data set. Decision tree is the algorithm name. So where is this evaluate algorithm? Yeah, so algorithm, it has decision tree. So here decision tree will be put, right? So decision tree we have defined, where we have defined here. So trend, test, max depth, min size, these values it gets. So first it passes the tree to build tree, right? So if we go to build tree, you will see this is the build tree. What it is doing, it is doing root equals get split train, right? So get split, if we revisit now, see here the calculation, if you see, it is calculating the Gini index and information gain for the nodes, and it is deciding the root node. Okay, it is deciding the root node, and based on the root node it will start splitting. Now next we are passing this root will be the feature name. Okay, root will be the feature name. We are passing it to the split function. So this is the root node, and from root we will be start splitting the data into left and right. Okay, we will start splitting the data into left and right. Okay, so then we will return the root, because when we build a tree we always access the tree via root. We don't go to the left directly, that will mess up the tree. So that's what it is doing. So evaluate algorithm again. Now evaluate algorithm, what it is doing, evaluate algorithm here is taking the actual values and predicted values. It is calculating the accuracy, and it is sending it out, right? It is sending it out. So now we have printed all this. we have printed the accuracy for all the folds. Okay, all the folds, all the 6 folds. So see how the accuracy started to slowly improve throughout the folds, right? How it slowly improved, and the mean accuracy that we are getting is 97.299. Okay, so that's how this decision tree works in a real world. So again, this is not how you're gonna use it. You're gonna use it with scikit-learn. So just try one thing. So that's how you can do it. Anvesh and others, for Gini index. Gini index is a measure, again a measure that is used for, like in cart models, that is an metric that is used. It is same as information gain. So information gain and Gini index, anything you can use. But for cart models, basically we use both, but somewhere we use Gini index only. So it is again based on the weighted average. Okay, so it is just a concept of cart models, nothing much. Cart and decision tree are the same, Ravi. Cart full form is classification and regression trees. As I told you, right here, if you have, if you have house values, then also you can apply this decision tree. But that way, your tree will be really big. And if you start pruning the branches over there, it won't yield you any result. So generally, we don't use it, but you can use it for regression purpose also. So there also you can use it. Okay, so that's how we have for the decision tree example, and that's how it works. Okay, no need to go into much depth of these algorithms. The code that we have in this, because it is a high level Python code, so you can try looking through the code and let me know if you have any doubt. And also just try using scikit-learn decision tree algorithm. Okay, so that's what we have for now. Next we will be going to naive Bayes. So let's go ahead with the naive Bayes classifier now. Okay, so what is it? How do we use it? We have shown, right? Now let's get a deep dive into it. So naive Bayes will assume that presence of any particular feature in a class is unrelated to presence of any other feature. In short, we can say in naive Bayes there will be no calculated feature. Okay, there will be no feature engineering will be there, otherwise naive Bayes can't work. Okay, so let's say here we have, for identifying an apple, we have three parameters: red, round, and 3 inches in diameter. So these three all are independent of each other, right? These three are all independent of each other. So here we can use naive Bayes in this case of this kind of scenarios. So why it is naive, right? Because the naive Bayes algorithm will have many limitations, right? It won't be sophisticated, it won't be experienced like that, right? So that means in naive Bayes we are solely dependent on the past data that we have, the historical data that we have, plus we need to use the exact features which are given in the dataset. We can't do feature engineering in that. So in many cases, naive Bayes will fall short. So naive Bayes we generally don't use much, but still in some cases where we have this historical knowledge, in those cases naive Bayes proves to be good, so we use it. But in naive Bayes, prediction accuracy can be really low. We will see that. Okay, next is the fundamental of Bayes theorem and its proof. Okay, so this I have already told. So let's go ahead and prove this. Okay, so calculate the probability of a second event B given that the first event A has already happened. Okay, so that means when this kind of so this is a concept of conditional probability. So how it works? It works in such a case where where we try to calculate probability of some event provided some other event has already been happened. Okay, so drawing a second ace from a deck given we got the first ace, right? So what does that mean? We already have drawn a ace from the deck. We will have 4 aces in the deck, right? So we have already drawn a first ace. Now we want to go ahead and draw the second ace. So it will directly become a conditional probability, right? Why? Because total number of cards in a deck will be 52, right? If we have the deck intact and if we try and draw the ace, in the first card that we are going to draw will be a ace, in that case the probability of it would be 4 by 52, right? It will be 4 by 52. But if we have drawn that card, then we will be have left with 51 cards, among which 3 will be aces. So so the probability of drawing a second days from the deck given the first days is already there will be 3 by 51, that is 1 by 17, right? Yeah, correct. So that way this conditional probability works. So that means finding a probability that you having a disease when you are positive to that, right? When you are tested positive, but the test result can be non-negative, right? So like that. So if someone likes Game of Thrones, what is the probability that he will like fiction movies, right? So this kind of probabilities are called conditional probabilities, right? So here you need to understand, when we apply to data science, we need to have a prior knowledge, right? We need to have a prior knowledge on what has happened in the past. So in that way only we can use this naive Bayes when we have this prior knowledge. In no other cases we can use this naive Bayes theorem, because the entire theorem is dependent on conditional probability, which differs you to have a prior knowledge, a historical knowledge. So let's say we have we want to check if a person likes fiction movies or not, right? So how do we can't apply naive Bayes, right? We don't know anything. So when we know the person has already liked Game of Thrones, then what is the probability of him being liking fiction? That comes a conditional probability way, or that comes to be and that becomes a good example where we can use naive Bayes classification, naive Bayes classifier. Okay, so that's how this thing works. That's how these things work. Okay, so that's how it is. Okay, next if we go ahead and see like event. Yes, Ravi, somewhere it so in movie recommend so for recommenders there is a separate topic called recommendation recommender system, but yes, you can use naive Bayes to calculate those kind of predictions. So given up, if you have the prior knowledge you can use it. Okay, if you have a prior knowledge of the system you can use this concept there also in the classification, I mean in the movie recommender system. Okay, you can do it. Okay, next is so probability of A, given that probability of B is already happened, we can write it as probability of A intersection B. That is probability of both the events, probability of occurrence of both the events divided by probability of B. So that's what is the probability of A given that B has happened. That's what the formula is. Now, so that is the formula, probability of A intersection B divided by probability of B. Okay, that's the formula. So we can prove it like the earlier the formula that we have seen. From that to this we can prove this. There is a mathematical proof, not going into that detail. So I think we have it later. Yes, we have it. We will show you. Okay, for now let's assume this only. Probability of A that B has already happened is probability of A intersection B by probability of B. Okay, now let's go ahead and see some examples how this works. Okay, suppose we have a jar of 6 marbles, 3 black and 3 red. What is the probability of getting a black given the first one was black too, right? Let's go ahead and see how can we calculate this. Probability of A is getting a black marble, probability of B is getting a black marble in the second turn. Okay, so probability of A will be 3 by 6, probability of B will be 2 by 5. So A intersection B will be 2 by 5 into 3 by 6, that is half, so 1 by 5. So probability of B given that A has happened will be probability of A intersection B, that is 0.2 divided by 0.5, that is 0.4. So probability that the second marble will be black when the first marble is already black is 0.4. Okay, that's how these calculations are done. Okay, that's how these calculations are. Okay, next is John's favorite breakfast is cereal and his favorite lunch is pizza. Okay, probability of John having cereal for breakfast is 0.6. Probability of him having pizza for lunch is 0.5. Now what is the probability of him having cereal for breakfast given that he eats pizza for lunch is 0.7. Okay, so see here, when John given that he eats pizza for lunch is 0.7. Okay, pizza for lunch is 0.5. Probability of him having a cereal for breakfast given that he eats pizza for lunch is 0.7. Okay, so probability of John having cereal for breakfast, let's have it as A, 0.6. Him having lunch as pizza will be 0.5. Okay, so probability of B 0.5. Probability of A with respect to B, that is John having cereal for breakfast given B has happened, that is he eats pizza for lunch is 0.7. Now calculate the reverse. Okay, what is the probability of him having having pizza for lunch given he has cereal for breakfast? What is the probability of that? Let's go ahead and calculate that. So if you want to know the probability of having a pizza, given that he has cereal in the breakfast, what is the probability? So it will be the reverse probability, that is probability of B by A. So here in this kind of scenarios, Bayes theorem comes into picture. Okay, this kind of scenarios, Bayes theorem comes into picture. Now Bayes theorem so here if you see both this event, in the first run we were able to calculate A intersection B, right? Because the events are interdependent, right? Because the events are interdependent. So but here the events are totally different from each other, they are unrelated. So in these cases Bayes theorem comes into picture. Okay, so if we have a conditional probability of a when B has already happened, then using Bayes theorem we can find the reverse, that is probability of B given A has already happened. Okay, we can do that using Bayes theorem. So we know probability of A by B is probability of A intersection B divided by probability of B. B by A is the reverse way. From that we can come to this conclusion, like probability of B given A has happened is equals probability of A given B has happened multiplied by probability of B by probability of A. This line at the bottom is called as Bayes theorem. Okay, so this comes into picture when we cannot calculate probability of A intersection B because the events are not the events are not related to each other, they are totally independent, right? In this case or this kind of scenarios, Bayes theorem comes into picture. So probability of A given B has happened, this is the probability that we are going to calculate. Probability of B where given A has already happened, this is the probability of B being true given that A is true, this is the prior knowledge that we have. Probability of A and probability of B, this knowledge will also we have. Okay, so this probability of B by A, this is the historical knowledge that we have. Okay, this is a historical knowledge that we had to have for applying Bayes theorem into our algorithm. So probability of pizza given C as cereal for breakfast is 0.7 into 5 by 6, so that is somewhere around will be 3.5 by 6, so somewhere around 0.6, right? Somewhere around 0.6 it will be. Okay, so where do we use this kind of Bayes theorem, right? Find out a patient's probability of having a liver disease if they are alcoholic. So here in this kind of scenarios we have this kind of Bayes theorem we can use. Okay, so a patient has liver disease, so past data tells you that the probability of a patient having liver disease who walks into your clinic is 0.1. Probability of patient being alcoholic, these are from all past data that you know, is 0.05. And from the patients who are alcoholic, from them the patients who have liver disease, 7% of them are alcoholic. Okay, so this is our B by A. Now we want to calculate probability of a patient who probability of a patient who is alcoholic having a liver disease. What is the probability of a patient having liver disease who is alcoholic? Okay, that we gonna find out. Okay, that we gonna find out. So according to Bayes theorem, 0.07 into 0.1 divided by 0.05, so that is 0.4. That means, so if the patient is alcoholic, then their chances of having liver disease is 14%. Okay, so that's what is we find out using Bayes theorem. Okay, that's what we find out using Bayes theorem. So next slide, it shows you already the things that I have shown. So probability of A by B, this is the posterior, that is the one that we are going to calculate. Probability of B by A, that is the historical knowledge that we have, the prior knowledge that you have, we have evidences of it, we have the past data records, like that. Probability of A, this is likelihood of seeing that evidence of your hypothesis is correct or not, right? That means probability of A is the probability. So this is what we are going to test, right? This probability of A we are going to test, and probability of B is likelihood of that evidence that we are using, that B has happened. What is the probability of that event being happened? Okay, so that's how is Bayes theorem. And it's just a 12th class math. We already have like we all already have done these things in 12, so that's this only. Okay, that's
So
what
it
is.
is a prediction, right? So
Yeah,
it
it
is
is
a
a prediction,
prediction.
right? So it won't be like our absolute value like others, the classifications that we have, it won't be absolute value. We will see. Okay, we will see with an example. Okay, so again the same example that we have. So total sample is 14, total yes is 9, total no is 5. So p yes is 9 by 14, p no is 5 by 14, right? Now, okay, so let's go ahead with the example for now. So let's just focus on this this example. So see, for outlook we have sunny, overcast, rainy. So 243 yes, and 302 as no, right? For temperature also. Okay, so we create this kind of frequency tables for each of the conditions that we have. So for outlook, temperature, humidity, windy, we have created this kind of tables. Okay, now we will calculate the probability of each of the attribute. So probability of an attribute being sunny is 5 by 14, right? Because we have 5 examples for that. So that way we go ahead and calculate each one of them. Okay, we go ahead and calculate each one of this attributes probability. 5 by 14, 4 by 14, 5 by 14, like that. Okay, we keep on calculating this probability for each of the we have this probability. We calculate the probability for each of the attributes individually. Okay, we create one by one. Then so this will be probability of A. All these attributes will be probability of A. Now probability of each attribute, that is probability of B, will be should we play or not. So 9 by 14 or 5 by 14. Okay, now we are going to find out probability of A given B. Okay, that means here when we calculate probability of yes in outlook sunny, that means what is the probability that the outlook will be sunny when it is given we are playing, that is 2 by 9. Okay, probability of no will be 3 by 5, like that. So if we keep on calculating this, then we will have all this p of yes no values. Okay, we will all have this p of yes no values. That means these are conditional probability of the events. Okay, probability of event A happening, that is probability of the event being sunny, the outlook being sunny when we are playing, is 2 by 9. Like that we calculate for each of the steps, each of the attributes, we calculate all these things. Now we have to calculate probability of B that given A is true. Like we will be playing when it is given outlook is sunny. We will be playing when it is given outlook is like overcast, like that. So we will apply Bayes theorem. So probability of outlook equals sunny is 5 by 14, as we know. Probability of temperature being cool is 4 by 14, like that we all know this, right? So now we just go ahead and multiply this result to have the probability of ideal condition, which will be 0.029. That is the probability of ideal condition. Okay, when we multiply all this, so that means those will be the ideal probability for each of the event being happened. Okay, each of the event happening. Okay, so outlook sunny is 5 by 14, temperature cool 4 by 14. So the we will just take the highest values from each of them. Okay, highest value from each of them, we will multiply those, and that will yield you the result of the result of ideal condition. So probability of ideal condition is 0.029. Okay, now ideal condition to play the game. So probability of outlook sunny when and play is given, play is yes 2 by 9, temperature cool, play yes 3 by 9, like that we have. So now we are going to calculate probability of playing a game in ideal condition. Okay, we will again multiply all these values to have a value of 0.033. So see here, we have probability of probability of ideal condition into happens 0.029. We have probability of ideal condition when given that we are playing is 0.033. So we have probability of A by B, and we have probability of A into account. Now we will find out B by A. That means when what is the probability that we will be playing when there is an ideal condition. That will be XES into PES by PX, right? PX is again, PES is 9 by 14. So 0.033 into 9 by 14 by 0.029, which will yield you a 73% of a result. So that's what is about this conditional probability. So we have a 73% of playing when ideal condition is there. Okay, so that's how this Bayes theorem works. Clustering algorithms. Okay, those are unsupervised machine learning algorithms. Now, just to reiterate, what is unsupervised learning algorithms? Unsupervised, as the term suggests, there won't be any supervision for the algorithm or for the model to learn from something. The model won't have a definitive value to predict. The model will try and learn on its own to get the output. This kind of scenarios are called unsupervised learning. That means our model is working on to get something fuzzy, that is the clusters, right? So cluster means, what is clustering? Clustering means to divide data set into groups consisting similar data points. So that means cricket, cricketers, footballers, hockey players, lawn tennis players, they are all players, but we can cluster them like that. Okay, so all the cricketers will have the same kind of attributes, same kind of nature, that they will be playing cricket for their country. They are playing cricket, and they are their profession is playing cricket. So that's what their similarities will be. They will either be a bowler or a batsman, again subclusters among the cricketers. Like that we can think of it as clustering. Okay, so this kind of data sets are random in pattern, and we don't really have anything critical to predict in there, except this clustering. Okay, except to divide those data points into similar groups, as many similar groups as possible. Okay, so that's what the idea of clustering is. Okay, now cluster, if you see here, there are cluster of different colors. There are cluster of different colors of fruit, cluster of different types of garbages. So all this can be shown as clusters. Okay, so these are basically clusters. These are examples of clusterings. Now we will see how do we use it in machine learning. Okay, so use cases of clustering. If you see here, we have Netflix, we have Amazon, right? So there is a concept called recommendation engine or recommender engine. What it does, it recommends the products or movies to the similar type of customers. So what it does, it clusters all the products or all the movies that it has to some specific groups, and based on the liking of the customers it suggests. So if a lady logs in, if she has browsed through some lady's product, it will try and show her those kind of products as a recommendation, so that she might be buying one or two items from that list. Okay, for a man it might be cool, like it might be a belt, a wallet, specs, trimmers, and all those kind of stuffs will be shown for guys, or t-shirts for boys. Like this kind of things will be happening. So these are basically two kind of filtering algorithms are used in this kind of recommendation engines. One is collaborative filtering, and another is content filtering. So what is the difference? The difference is, in case of collaborative filtering, the products that are recommended based on the customer type. Okay, if some customer has liked some product or bought some product, then the similar type of customer, how do they know similar? They take into account many parameters. Let's say age, sex, and their work. Let's say someone is working in IT company and someone is a housewife, so their choices might differ, right? So that's how they show the products into products as an products to the customers, product as a recommendation to the customers. So the customers are grouped, then the products are shown to them. That is collaborative filtering. Content filtering is based on the contents. If someone has bought or liked some product, then the same those items will be shown to other customers, so that they might buy that. So content filtering based on the content, collaborative filtering based on the customer or target group. So that's how you can think of. So these are also some few examples of clustering that is being used in the real world. Okay, this kind of clusterings are being used in the real world. Okay, so Amazon, Netflix, Flickr, and all those places, this clustering is used. Now we can see there are three types of clustering: exclusive, overlapping, and hierarchical. Let's go through those one by one. First type of clustering is exclusive clustering. That means there can only exist, or each data point of the total sample can exist in only one of the clusters. Okay, it cannot coexist in multiple clusters. So k means clustering is a good example of that. So what it will do, it will take the data points into account, the samples into account, and it will split the values based on that, and it will split it into as many clusters as possible. Okay, as many clusters as possible it will split it into. So in all those clusters will be pure clusters, and it will have only one type of data point. How we do k-means clustering we will see in the next few slides. Okay, so that is the idea of exclusive clustering. Now next comes into picture overlapping clusters. So here it will be overlapped in nature. In data science we really don't use this kind of clusters. In our data science the clusters will be based on exclusive, and will be used maximum cases we will be use k-means only. Okay, now for this kind of overlapping clusters, the data points are allowed to coexist in more than one cluster. So that means that means it is some kind of fuzzy clustering logic is being going on the behind of this going behind the scenes. Okay, so that is how this fuzzy clustering is done based on the data objects. It can belong to multiple clusters. Okay, next comes into picture hierarchical clustering. So how it is done, it is so the graph that you are seeing in the bottom of the screen is called a dendrogram. Okay, that is called a dendrogram. So how do we do it? First we group the nearby items that is possible. So if you see the leftmost picture, we have a, b, d, e, c, and f. So a, b, and d, e are pretty close to each other, right? So that A, B will be clubbed together in the same cluster. Okay, so A, B in one cluster, D in one cluster. Now C is near to B, F is near to D. So now in the next step, C will be included in the AB cluster, and F will be included in the will be linked to the DE cluster. So that DE as a cluster, F as a cluster will form a new cluster. Okay, so that's what is being shown in the dendrogram also. So C comes into AB, so that is another cluster, and F comes into DE, so that becomes another cluster. So these are two clusters are there, two definitive clusters are there. Okay, and inside each cluster there are two segregated clusters. Now if you see in here, the distance between C and D is also minimum. So C and D is again clubbed, and again another cluster is formed. So that's what the dendrogram also shows in the bottom and at the end of the picture. So the cluster DEF is pretty near to the point C. So those two clusters are also linked. So if you carefully see the dendrogram, you see there is an hierarchical relation between all this data point in this sample set. So this is again this is an example of hierarchical cluster. Okay, so this hierarchical cluster is also not much used in data science. So we will be only focusing on this exclusive clustering for this class. Okay, so this is what is the example of hierarchical clustering, and we discussed exclusive clustering and overlapping clustering as well. So guys, any doubts in here? So as we discussed, uh, exclusive clustering, and the type of exclusive clustering algorithm is a k-means clustering algorithm, right? So what is k-means clustering algorithm, how you can use it, and how the algorithm actually looks like, we will see that in next few slides. Okay, we will see that in next few slides. Okay, K-means is a clustering algorithm which focuses on to group similar elements or data points into clustering. Now you might be you might be wondering why k and why means, why no other name, right? So k, in the k means represents the number of clusters that we are going to make. Okay, so if a data point has 3 clusters, that means it will be 3 means algorithm. Now why means? Because it calculates mean of the data, distance between two data points, and distance between mean of a cluster and each data point. It calculates the entire calculation of k means depends on the mean calculation, so that's why means. So that's what k-means clustering does. So what does k-means clustering do? K-means clustering clusters the data into k number of clusters. Okay, that's what is the use of k-means algorithm. How k-means algorithm finds finds this how this k-means algorithm how I mean this how this k-means algorithm groups those into different clusters. It uses the difference between the mean of the data points and the difference between the mean of the cluster and the data points, and it keeps on grouping those. Now we will see the algorithm in detail in the next slide. Okay, I have a question like, is hierarchical is used in real world? No, Tom, it is not much used. There are use cases where it is used, but not much used for data science. Those are for astrophysics and high level of physics and maths research that is being used, and there hierarchical clusters do exist. Okay, so for machine learning it is used, but not for data science. Okay, for data science our world is really small. We only play with data, we only play with real world data, so there won't be much of an scenario like this. As you can understand, that's something when you work with electron, protons, neutrons, you might get those kind of things. Okay, that's what. So that's when you get those kind of things. Okay, next is this is an example like pile of laundry, so we just clear this thing. Next is business application of k-means. That means real world scenarios, where do we use it? So we use it for behavioral segmentation, like kids, adults, something like that. Sorting sensor measurements. Yes, we do take the sensor, or we have a lot of sensors, right? So we take those data in and we can parse it using this clustering algorithm. Let's say this is a home, this is a big home, this is a multi-storied building, this is a small home, this is a hut. Like that we can do. Detecting warts or anomalies. Yes, so the behavioral pattern of the users can be clustered, and we can directly see the anomalies when a bot entered in a system, right? Next is inventory categorization. That means we can group different items and we can keep the inventory like that. So how much item is needed for which item is needed in what quantity, we can take into account all those things. And bots and anomalies, we can directly segregate the human behavior and the bot's behavior from the if a bot enters in our system. So in these cases, k-means algorithm is really very helpful to cluster these things. These clusters means a lot. Okay, so that's how it works. Now we will be going through the example of k-means clustering. So any doubts till this point? Okay, let's go ahead with this example. So what do you see here? We see 4 balls in different positions, right? So how many clusters do we have here? 3. 1, 2, 3. So here number of clusters will be 3 and k equals will be 3. So this is what we need to get from the data point. Okay, we need to segregate these 3 cultures based these 3 clusters using k-means algorithm step by step. So this is the final requirement that we currently have. Okay, next is, what is the steps of k-means algorithm? We select the number of clusters to be identified randomly. Okay, so we select a value for k equals 3 in here. Then what we do, we select 3 random data points. Then we measure the distance between the first point and the selected 3 clusters. Okay, so we have k equal to 3. Then we will take a sample data point. Okay, then we will calculate all the distance, all the from that centroid, all the points distance will be measured, and based on the like distances, the clusters will be formed. Let's see how. Let's say we are assigning the first point to the nearest cluster, that is red. Okay, so for this point, this is the nearest cluster, right? So this is red, we are assigning it to red cluster. This we are assigning to purple, and this we are assigning to blue. Now we will see how we can go through step by step, and we can get this thing clustered into this 4 are red, this 4 purple, this 4 blue. Okay, the first step will be we assign the first point to the nearest cluster, that is the red cluster. Okay, that is our first point. Next is we calculate the mean value including the new point for the red cluster. That means this one and this one are the two values. So this will be the mean point of the new cluster that is formed, right? This will be the new mean point of the new cluster. Now, which cluster does point 2 belongs to and how? So this cluster is now for second point, we will calculate the distance between the red second red point. Okay, that is this mean point. Okay, we will calculate the difference between this point. So the idea of key means is, let me show you this first, you will get a clear idea for that. So see, initial cluster center is mu1 to mu k, where this all belongs to random number, I mean real number. Okay, then repeat until convergence. So till when should we repeat and what should we do? For every I, we need to set the distance or the minimum distance between a point and its mean of the cluster squared. And then for each j in the set, we calculate the mu j. Mu j means, so j is the number of clusters that we have, which will run till k. Okay, so we find the mean of each of the clusters. So we find a new centroid, and we find a new centroid, and then we assign that value to some clusters j. Okay, ci equals j, so we are assigning the value to the cluster, and then we are calculating the mean of it. So this is the two-step algorithm that we have shown. How it converges, we might see in the next class, not today. Okay, because this might have you blazing. So what we are doing here? First step, we are assigning this point to red. Okay, this fourth point to red, this point to purple, this point to blue. Now what we are doing next? From the first point, we are calculating the distance from this red point, purple point, and blue point. Nearest is red one. We are assigning this to red cluster. We are calculating the mean for these two. So these two are in a current cluster. So we are assigning a mean for it. So the mean comes in somewhere around here, just an arbitrary value. Next, what we will do, we will find the distance between the next point, that is this point, and all these points from this mean point. So let's concentrate on this point only. So for this point, we will calculate the difference between all these three values that we have for the cluster. So the minimum difference will be this one. So we assign this to red cluster again. Now we have 1, 2, and 3 elements. We shift the mean. So it will be somewhere around here, right? So that would be the next step. The mean now shifts in, right? So mean now will be somewhere around here. So now we are calculating for this third variable. Okay. And again we calculating distance for these three centroids. We find this to be the nearest, and we assign it to red also. Okay. So now the red mean shifted to here. So it is nearer to the red mean. So third point also gets into red point. Now the red mean shifts to somewhat right. Okay, now we calculate mean of this 4, and we have it here. Now we go to the next point. We calculate distance from this red mean point, this purple point, and this blue point. We see the distance from blue point and this one is minimum. So we purple and this one is minimum. So we assign it to purple. Calculate mean comes in here. So this point now, so which cluster it should belong to? Okay. Yes, Tom. Everything has an algorithm. We'll show you. When we go to the coding example, we will show you, but for now please concentrate on this example part. Okay, because if you don't understand the math, it will be difficult for you to understand the algorithm at the later point of time, and the code will just bounce back. Okay, so you need to have it. So to which cluster this point belongs to? This will seem to be this belong to this blue cluster. So this blue is now printed, and now this is the mean. So again, what we will do, we will take this 4. So this all these 4 are located close to blue, right? So we will assign all this floor all this 4 one by one to this blue cluster. So that's how it will look like. So 6, right? So 6 is the 6 values are there in the blue cluster. That is what is the result from one iteration. Now what we do now, how this k means when the convergence comes into picture, just have it in mind theoretically. So when this k means stops, ideally k means doesn't stop its iterations till it has all the data points are in equilibrium. That means the data points are not changing. Okay, so after we included this 4 points to the cluster, you see radically these 2 points distance from this blue one gets increased, right? So this point's distance from purple one now much closer than its distance from blue line, right? So we will mark this cluster to purple. Then this point again this will come to here. We will mark this to this purple cluster. So till like this it will start. Okay. So this time we will that's how we will be assigning the clusters. Okay. So that's how we will have the 3 points in a particular equilibrium. Now if you see here, all the points are located in their nearest clusters only, and we don't have any other alterations won't be there in this cluster, right? So that's what is k-means does. Okay, so first iteration it will do somewhat, second iteration it will do somewhat, and the third iteration it will give you the perfect result. So that is a 3 means. Now the next question comes, how to find the value of k? That's a big interesting question. So how do we know it? Okay, so to find this value of k, what we do, we take a value, we do use Witten trials in here. Okay, so what we do, we take all we take the value of k as 1. That means we think there are only one cluster. Okay, so what we do, we color all the points to red. Okay, because if we think that if we have one cluster, we paint all the points to red color. If we have two, then we have now again I lost my track. Okay, so for okay, let me restart from a bit earlier stage. So but how do we find out the value of k? Okay, how do we find out the value of k? What we do, for the previous example that we have solved manually, we see that k value of k was equals 3. But how do we know it? How do we calculate in the algorithmic perspective? We won't be knowing the data set that we are working on. How do we calculate? Okay, we use it and trial. We start from k equals 1. That means we suppose there is only one cluster present in the data set. Okay, so we paint all this to red, calculate mean. Now next step is to calculate the total variation. So we will calculate distance between all the data points from this mean point. We will see a large variation. We will change the value to 2. Okay, k equals 2. So we will have two clusters like this. So now if we have total variation calculated, then we will see it is somewhat better. Now we go for k equals 3. Okay, so now if we see the total variation, it is much better. Okay, now it will k equals 4, then it will still be better. Okay, so till like this we keep on continue. Okay, but how do we stop this algorithm from growing, right? it might go with all, I mean, it might go, Charu, it's not variance, it is the difference between the distance between the point and the mean point for all the points, and we sum those up. Okay, this is different, this is not variance. And you can, variance won't solve here, so it is the mean distance actually. Now if we try with k, we will see the total variation is still better. But how do we stop? That is the main question, right? How do we stop? How do we know what is the point when do we stop? Okay. Now this is a graph. If you see this graph, this is an elbow shaped graph of cost function for this. So this elbow where it comes in, the curve bends near the elbow. So this elbow point is the best case scenario. Okay. So this is the best number of clusters that can exist in a data set near this elbow point. Okay. So that's where when you see, so what do we point? We just plot the total distortion or the total variation in the data set with the number of clusters. Now if we keep on plotting this, it will bend at some point, and this bend is the ideal number of clusters. So that is 3. Okay. So that's how k-means works. So that's how k-means has its k-means knows where to stop. It has this elbow value. Okay, it has this at elbow point, it stops. So k equals 3 is the ideal cluster number for this. Okay, that's how it works. Y-axis is the distortion. That is the variation that we were discussing. Okay, so if we keep on increasing the clusters, after some point, the variation will be parallel to the x-axis. That is, it will have some definitive value of y. Okay, so it will be stuck at some point. So till which point the variation decrease, that is this elbow point is the required number of clusters that we take into account. Okay, so that is the idea of this k-means clusters. And for this example, if we plot this, the total variation, we will see for k equals 3, it is taking a slight bend, so we stop it right there. So that's how k-means understand where to stop. And at this point, we say k-means algorithm has converged. Okay, so that is the convergence criteria of k-means. So that's what it is. So do we have any doubts in this scree plot? Sorry, so what do we mean by scree plot? So what is your question, Charu? Can you tell me? Like scree plot. Okay, are you mentioning this plot? This elbow shaped plot? Yeah, correct. Yes, that is scree plot. So I was just thinking, where are you getting the term scree plot? Scree plot for this one. Okay, not an issue. Yeah, that is called scree plot. So this is basically used for factor analysis. Okay, so I don't want to go in details actually, but still let me tell you. So for multivariate statistics, right? Not for univariate, but for multivariate. So we have multiple variable values going in here and there. So that is a vector thing is going on there. So this scree plot is basically a line plot, and that signifies the eigenvalues of factors or eigenvalues plotted against their factors or principles. So that is the main idea. But as this scree plot bends in some time, so this is the same thing that we do in here, right? This is a multivariate analysis where we have multiple value of k. This is not univariate because there are multiple values of k might exist, and we are plotting the factor on this. So factor on the y-axis. So that's why this elbow-shaped scree plot is like is a cost function basically. Okay, next is what if we had our data plotted in x and y axis. Okay, so the same thing, right? The same thing. So what we will do, so let's say for here we have shown in a linear line, right? Like a linear plane we have shown. Now let's say the values are in this plane, xy plane. So what we do, let's say we start from k equals 3. So we will take 3 random points in there. Okay, we will calculate the point distance, as you know, that is Pythagoras, root over of b square plus b square. So we will find the distance between these points and its nearing points. We will then assign that nearest point to the cluster. We will calculate mean. We will keep on calculating the means and all and all and all. We will keep on going till this cluster reaches its like convergence criteria, until we have all the convergence criteria are met, until we have this happening. Okay, till we have this thing in till we have the I mean optimal number of clusters as an output. Okay, so that's how we can do. So now to summarize this k-means, that the examples that I have shown you earlier also. So how do we do? We randomly choose k examples as initial centroids, while and we keep on going in an infinite loop. We create k clusters by assigning each example to its closest centroid. Then we compute k new centroids by averaging examples in each cluster. If the centroids don't change, we come out of the loop. If the centroids keeps on changing, we continue the loop. So that's how k-means works. So till this point, everyone is clear. So we won't be doing it manually, Tom. Anyways, that will be done algorithmically, right? So that's no need to be worried. That will be taken care by the algorithm itself. You will see soon. Now we'll have these questions answered. So what is the minimum number of variables or features required to perform clustering? 0, 1, 2 or 3? Anyone give it a try? It's 1, right? Because we can cluster using one variable only, right? If only one is there, then that means one cluster, right? In which of the following cases will k-means clustering fail to give good results? Data points with outlier, data points with different densities, data point with non-convex shapes, or all? Where? Okay, so this is a bit of advanced concept. I will tell you. If there are outliers, then the k-means algorithm will calculate the mean very large, right? So the clusters will get distorted. Okay, so why that's why it cannot be used. Data points with different densities, that means the data distribution is not equal through the plane. So somewhere it has 2, somewhere it has 3. So even if those belong to the same data same cluster with same kind of like attributes, it won't be able to cluster those. Okay, data points with non-convex sets, this is just leave it. It will never happen for this, but just know for theoretical purpose, guys will ask you. So just explain them. So just explain them like this. Okay, so in which cases the k-means doesn't use. Okay, that's how. So for the non-convex part, how do we explain? Non-convex means, so uh, non-convex means where the angles between the if you try and if you try and draw a geometrical figure from the data points, the figures will have some kind of a distorted angle in between them. Okay, you can just search it in Google, like okay, let me show you. So this is what this kind of shapes in geometry is called non-convex shapes, right? Where the angles are distorted. These angles are not equal, these angles are distorted. So that's why we call it as non-convex ones. There are multiple thousands and hundreds and thousands of examples. And these are, so in geometry we call them concave, not non-convex. So these are concave, convex ones, these are concave ones. Okay, so that's how it goes. Okay, that's what is non-convex means. So whenever the data distribution looks like this, we just whenever the data distribution looks like this, we just tell them like the k-means cannot work. Okay, yes, right, we have circle shaped, right? So the angles were perfect, so that's why it is that was not a concave one, that was a convex one, like that. Okay, so that's how. Okay, next one is, assume you want to cluster 7 observation into 3 clusters using k-means clustering. After first iteration, cluster C1, C2, C3 has the following observations. Okay, so these are the C1, C2, C3. What will be the cluster centroids if you want to proceed for the second iteration? Okay, so this is the cluster 1, cluster 2, cluster 3. You can try it. It's maths calculation. So can anyone give it a shot? Like which one is which one? The mean for which cluster is what? Okay, let me show you. This will be the first one, because 2 2 4 4 6 6, 2 and 6 8, 8 by 2 4, right? 0 4 4 0, so 2 2, 5 9 5 9, so 7 7. So that's how you calculate mean. Okay, in real, in simple terms. Okay, that's how you calculate mean. So is this one clear for everyone? Is this example clear for everyone? This third example clear for everyone? Yeah, cool. Okay, next one is customer segmentation is an example of classification, clustering, association. Which one will be the answer? Customer segregation. Yeah, correct, Charu, it's clustering. Okay, next is NK means K stands for number of clusters, dataset error function. What is it? I see max of the guys silent. I will take it as you guys are understanding this. It's wrong. It should be number of clusters. Okay, so that's what sums up this quiz part also. Okay. So now let's go ahead with this demo class. So today I might take 5-10 minutes more. So please be with me. Okay. Let's complete this. Then we can we can wrap up for the day. Okay. So these are the steps and detailed steps that we have already discussed till this point. Okay. Now I will directly go into the implementations. Okay. So give me 2 minutes. The data set that we are going to read is, I have already shown you, but still let me open it once more. So this is the data set that we are going to use. So v1 v2, they are some random points. We are going to cluster this v1 v2. So v1 v2 is x and y coordinates of each point. We will be going to cluster those into different clusters. Okay, so no need to say what is it doing. This is just reading the Excel file. Okay, next one is we are getting the values of v1 or v2 and we are plotting. So you guys can identify there are three non-convex data sets present here. So there will be three clusters. Okay, there will be three clusters. So that's how we see the data points. This is using a scatter plot. Okay, I am not going into the syntax details. You guys should be remembering these things. Okay, so you see here, you can see there are three distinct data sets that you can see in here. Okay, next part is Euclidean distance calculator. We are, because these are the points in x and y plane, right? So we need to, whenever we need to find out the distance between mean of a cluster and between the points, we need Euclidean distance calculator. So that's what we are doing. We are having this Euclidean distance calculator function ready to calculate the distance between the centroids and the points. Okay, now we are setting k equals 4. Then we are getting having random centroids. We are taking random x coordinate for the centroids. Okay, so just we are splitting it. We are splitting into four centroids. Okay, we are taking x and y value of random centroids and we are clubbing them. So list of zip will club them. So see, we have four centroids: 45 70, 10 58, 50 on 64, 60 30. Okay, so we have 10 we have four centroids from this. And how you are getting the x and y values? If you see it carefully, np.random.randint, that means generate a random integer number from 0 in between np.max of x minus 20 size k. That means give me four numbers between 0 and max of 20, max of x minus 20, and divide them into 4. Just assumption, Charu, we can have one also. So we are just assuming that k equals 4. So that's how. So we are getting x and y values like that, and we get four centroids. Okay, now let's plot those four centroids. Can you spot those? 1 2 3 4, right? We have four centroids. 1 2 3 4 centroids we have. So four centroids we have plotted. It is clearly visible these are wrong. So see how we go into the next step. Okay, and how do we do that? So we are here, we are going through all the iterations, four iterations of it, and we are picking the correct centroids and we are centering the values. Now how we are doing it? Okay, So we are storing the old centroids when those are updated. So we are creating a variable c underscore old to have the old centroids stored for comparison purpose, and we are assigning it with 0 values for the first iteration. Then we are creating clusters, that is we are creating labels 0 1 2 3 4 like that, and we are creating of len of x. So x will have len of 4, so that's what the sorry, len of x will be total number of data points. So we are creating those many clusters with zeros. So for the first iteration all will be assigned to the cluster 0. Okay, next we are calculating the Euclidean distance between the current cluster and the older cluster, and we are setting it to error. Okay, so we are calculating difference between the new cluster and the old cluster. Okay, and we are setting it to a variable error. Now we are checking till error is not equal to 0. That means till no clustering changes are happening in the data set. Okay, we are looping through those, we are looping through all the values and we are assigning those to closest clusters. Okay, dist of xi comma c will be calculating difference of each xi point of the plane and their centroids. Okay, then we assign the minimum of distances. So if it has minimum distances in the 0 1 or 2 like that, we are assigning it to the cluster. Okay, and clusters I, again clusters is the our end output, so we are assigning those values to the cluster. Now we are storing the old centroid values, we are storing this centroid values into the old variable, because this will get changed. Okay, because we have assigned new points into clusters in here. In here we have assigned new points in the cluster, so now we will change our centroids, right? We will change our centroid, that's what the point is. So now we take those points in a we take for I in range k means 4. So we take all the four clusters, we run through all the points, and we keep on calculating the centroid for each of the clusters. Okay, then we find the difference between cluster and the older cluster. These are pretty much same things. Then we just give them some colors and then we plot them using this data function. So that's how with iteration you can have clustering using Python algorithm. So this algorithm is built on hand. Okay, this doesn't use the scikit-learn. The next one that we have uses scikit-learn. We will show you, I will show you that, and I will wrap it up for the day. So any doubts in this part, any coding related or any concept related doubts in this part, I will give you 2 minutes to think of, then come up with the questions, and otherwise I will go on with this. So why 4 versus 3? 4 is a random choice, Charu. It can be 3 also. Okay, you can change k value equal to 3 and then you will see how it changes. I will show you. See, now it will change to 3. It's just an assumption. Don't think about, sorry Tom, it was question from Tom. So it is just an assumption, Tom, as we explained earlier also, right? So what's x? X means, yeah, x is the data point, Charu. We already had it, right? Like in here, right? Okay, deep copy is to copy all the parameters and rows from the older array to the newer array. It's similar to copy. Okay. Okay, any other questions? Yeah, because I changed it to 3, Charu, that's why. Okay, no, this is not the actual labels. This is just, yeah. This is just a comment, right? This is not label. So label is here only. Okay. So label is here, not this one is not the label. Okay. Don't think about it. This is commented, right? Need to think of it. Okay, so the thing is we need to be very careful in selecting the value of k. So if we are calculating it wrongly, then we will get this kind of misleading result. See, here we have 6 clusters on their own, right? So that's how it works. Anyways, so now let's go on with this k means clustering. Okay, so see, it is much easier. You have only 3-4 lines to write and your work will be done. So you have 3 clusters out of this data set, just like this. Okay, so these are the centroids that is being printed. So that's how you do k-means clustering using scikit-learn. Okay, yes, right, that will be based on the algorithm. based on the elbow point that we have. So not exactly based on the algorithm, we have a cost function. Yeah, we need to pass some basic values. So from that only the algorithm will start working, then it will change on its own. So we will fit the model, we will predict the model, like that we can do. So this thing can be calculated by a code, like how many clusters are there. You can do a small research also in the next week, and I will show you also. Okay, you can just go ahead and check the internet for these resources. You will have many options. Okay, so how we calculate the number of clusters based on a cost function is there. So that's how it works. The k-means won't do that for you. Okay, k-means won't do that for you. There are separate algorithms which need to be called in to calculate that n clusters equal 3, not k-means. K-means will just cluster it into 3 points. Okay, that's how. Yes, it will be same thing. Okay, if you draw it in the plane also, you will get the same kind of output. Okay, here if you see, like the centroids 40, 59, 9, 10 and 69 minus 10. So see, the algorithm that we have built and the algorithm that k-means has is returning the same results, right? So even if we plot the data, it will be the same output. Okay, so that's what is the idea, and this is how you just can you can use k-means from scikit-learn. So import that k-means module from scikit-learn, call a k-means function with the number of intended clusters that you want to create, then you just fit the model into k-means, okay, with the x data. Then you create the labels for those, like you predict for the x's, and then you print the, you can get the centroids like this, and like this one works. So this is not a very good example. I will try and get you some good examples in the next class. Okay, where you will see how scikit-learn does all its work. So that's how it works. Okay, so any other questions in here? No, Karunakar, it cannot be done using string because, yeah, Karunakar, see, the whole idea that I was trying to explain is how we cluster the things are using features, right? So features won't be strings, feature will always be numbers. Color red, so that I explained earlier also, right? You will need to have those categorical values. If you have strings, you would need to convert those to numerical numbers, right? Red, green, blue, computer doesn't understand these things, right? It understands 1 and 0. So that won't be much of a fruitful things, and you won't be able to fit into, I mean, how do you calculate mean of 3 red objects, right? You can't, right? So that's why you need to convert all of those into numbers. So these things we have discussed earlier also, like why do we need that? Okay, we need to convert the string values into categorical numerical values. So let's say if we have gender, male and female, we will have 0 and 1 for that. If we have color, red, blue, green, we will have 0, 1, 2 for that, like that.
So guys, this brings us to the end of the session, and do subscribe to Intellipaat's YouTube channel for more such informative content.